In segment 1.1, we're going to talk about cryptographic hash functions. We'll talk about what they are and what their properties are, and then later we'll move on and talk about what their applications are. So a cryptographic hash function is a mathematical function, and it has three attributes that we need to start with. First of all, a hash function can take any string as input, absolutely any string of any size. It produces a fixed size output. We'll use 256 bits in this series of lectures because that's what Bitcoin does. And it has to be efficiently computable, meaning given a string, in a reasonable length of time, you can figure out what the output is. So that's a hash function, but we're going to need hash functions that are cryptographically secure. The cryptographic properties of hash functions are a complicated topic in general, but we're going to focus here on three particular properties, and I'll explain in a minute what those are. In particular, that the function is collision-free, that it has a hiding property, and that it's puzzle-friendly. And for each of these, I'll talk about what the property is, what it means, and then I'll talk about why it's useful to have a function that has that property. So first, collision-free. So the first property that we need from a cryptographic hash function is that it's collision-free. And what that means is that it's impossible, nobody can find values x and y such that x and y are different, and yet the hash of x is equal to the hash of y. And so if we look at the operation of the function as depicted by one of these red arrows, here's x and h of x, and here's y and h of y, then nobody can find a situation like this, that you have an x and y that are separate, and yet when you hash them, they hash to the same value. Now, one thing to notice is that I said nobody can find. I didn't say that there is no collision. Because if you think about it, there has to be a collision. Collisions do exist, and to understand why that is, we can use this diagram. Over here on the left, I'm depicting all of the possible inputs to this function, which can be a string of any size. And over here, I have all of the possible outputs, which has to be a string of 256 bits in size. So the right-hand side here, the outputs, there are only 2 to the 256 possibilities. Over here, there are more possibilities. And so if you think that every point over here on the left is going to be mapped by an arrow to some point on the right, you can see that as you go from all the points over here on the left into the right, it has to get crowded, and in fact, that there have to be multiple values over here on the left that map to the same output over here. In fact, in general, there will be a very large number of possible inputs that map to any particular output. So collisions do exist. I said before, nobody can find a collision, and that's the key question. We know collisions exist. The question is, are there any collisions that are findable by regular people using regular computers? Okay. Now, to make things even worse, I said that it has to be impossible to find a collision. Let me tell you how to find a collision, because there's a method that's guaranteed to work. And the method works like this, that we're going to pick 2 to the 130 randomly chosen inputs over on the left cloud of that previous diagram. And if we pick those 2 to the 130 randomly chosen inputs, it turns out there's a 99.8% chance that at least 2 of them are going to collide. And so this is a very simple method for finding a collision. It works no matter what the hash function is, but of course the problem is that this takes a very, very long time to do. You have to compute the hash function 2 to the 130 times, and that's of course an astronomical number. This method works no matter which hash function we're using. There's still a 99.8% probability that this works, and if it doesn't work, just try it again. It'll probably work the next time. But this doesn't really matter, and the reason it doesn't really matter is that this procedure takes 2 to the 130 steps in order to get to that high probability. So we can say something like this. We can say that if every computer ever made by humanity was computing since the beginning of the entire universe up to now, the odds that they would have found a collision is still infinitesimally small. So small that it's way less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds, which didn't happen. Okay, so we know how to find a collision, but this method takes too long to matter. The question is there some other method that could be used on a particular hash function in order to find a collision? And that's the question that is harder to answer. Is there a faster way to find collisions? Well, for some possible values of hash functions, of course there are. For example, if our hash function were to simply take the input modulo 2 to the 256, that is, it just selected the last 256 bits of the input, then we would know an easy way to find a collision. One collision would be the values 3 and 3 plus 2 to the 256. So for some possible values of the hash function, it's very easy to find a collision. For others, we don't know. Now, one thing I need to note is that there's no hash function in existence which has been proven to be collision-free. There are just some that people have tried really, really hard to find collisions and haven't succeeded. And so we choose to believe that those are collision-free. Okay. Now, what good does collision freedom do us? If we can assume that we have a hash function that is collision-free, then we can use that hash function as a message digest. And what I mean by that is the following, that if we know that x and y have the same hash, then it's safe to assume that x and y are the same. Because if someone knew an x and y that were different that had the same hash, of course that would be a collision. Since there's not a collision that we know of, then knowing the hashes are the same, we can assume that the values are the same. And this lets us use the hash as a kind of message digest. Suppose, for example, that we had a file, a really big file, and we wanted to be able to recognize later whether another file was the same as the file we saw the first time. Right? So one way to do that would be to save the whole big file, and then when we saw another file later, just compare them. But because we have hashes that we believe are collision-free, it's more efficient to just remember the hash of the original file. Then if someone shows us a new file and claims that it's the same, we can compute the hash of that new file and compare the hashes. If the hashes are the same, then we conclude that the files must have been the same. And that gives us a very efficient way to remember things we've seen before and recognize them again. And of course, this is useful because the hash is small. It's only 256 bits, while the original file might be really big. So hash is useful as a message digest, and we'll see later on in this lecture and in subsequent lectures why it's useful to use hashes as message digests. So the second property that we want from our hash function is that it's hiding. And the property that we want is something like this, that if we're given the output of the hash function, that there's no feasible way to figure out what the input x was. The problem is that this property doesn't exactly hold. And to understand why that's the case, let's look at this example. So here, what we're going to do is an experiment where we flip a coin, and if the result of the coin flip was heads, we're going to return the hash of the string heads, and if the result was tails, we're going to return the hash of the string tails. And now we're going to ask someone who didn't see the coin flip but only saw this hash output to figure out what the string was that was hashed. That, of course, is going to be easy. It's easy in this scenario to find what the input string was. It's easy to find x. You simply compute the hash of the string heads and the hash of the string tails, and you see which one you got. And so in just a couple of steps, you can figure out what x was. So the reason this example failed, that is the reason why an adversary was able to guess what the string was that there were only a couple of possible values of x. And so if we're going to have a hiding property like this, it needs to be the case that there's no value of x which is particularly likely. That is, x has to be chosen from a set that's in some sense very spread out, so that this method for the adversary of just trying all the possible values of x, or just trying a few values of x that are especially likely, is not going to work. So the hiding property that we are going to need to set up is a little bit more complicated. And the way we're going to fix this problem with the common value x, like heads and tails, is we're going to take the x and we're going to put next to it, we're going to concatenate with it a value r, which is chosen from a distribution that's really spread out. And so this h of r concatenated with x, that means take all the bits of r and put after them all the bits of x. And so what we're going to say is, given the hash of r together with x, that it's infeasible to find x, and that this will be true in the formally stated property that if r is a random value chosen from a distribution that has high min entropy, then given the hash of r concatenated with x, it's infeasible to find x. And what does high min entropy mean? Well, it captures this intuitive idea that r is chosen from a distribution that's really spread out. And what that means specifically is that there's no particular value that r could have had that would occur with more than a negligible probability. So for example, if r is chosen uniformly from among all of the strings that are 256 bits long, then any particular string was chosen with probability 1 in 2 to the 256, which is truly a negligible value. So as long as r was chosen that way, then the hash of r concatenated with x is going to hide x. And that's the hiding property that the hash function will be deemed to have. Okay, now let's look at an application of that hiding property. And in particular, what we want to do is something called a commitment. And this is kind of the digital analogy of taking a value, a number, and sealing it in an envelope and putting that envelope out on the table where everyone can see it. Now, when you do that, you've committed to what's in the envelope, but you haven't opened it. It's secret from everyone else. Later, you can open the envelope and get out the value, but it's sealed. So commit to a value and reveal it later. We want to do that in a digital sense. So to be more specific about what is the API that we're going to provide here, the commitment API looks like this, that there are two things you can do. First, you can commit to a message, and that's going to return two values, a commitment and a key. Think of the commitment as the envelope that you're going to put on the table, and the key as a secret key for unlocking the envelope. Then later, you allow someone else to verify, given a commitment and given a key which you've told them in the meantime, and the message, they can verify that that commitment, key, and message really do go together, and this will return true or false. Okay, now to seal MSG in an envelope, what we do is we commit to the message, and that returns a commitment and a key, and then we publish the commitment. That's putting the envelope on the table. Now later, to open the envelope, what we're going to do is publish the key and the message that we committed to, and then anybody can use this verify call with the commitment that we published previously, the key and message that we just announced, to check the validity of our opening the envelope. Okay. And the property, of course, we want from this is that it behaves like sealing an envelope. And in particular, the two security properties are these. First, given COM, the commitment, the envelope on the table, that someone just looking at the envelope can't figure out what the message is. The second property is that it's binding, that when you commit to what's in the envelope, you can't change your mind later. That is, it's infeasible to find two different messages such that you can commit to one message and then later claim that you committed to another, and the whole thing will verify. Okay, so how do we know that these two properties hold? Well, first we need to talk about how we're going to actually implement commitments. And the way we're going to implement commitments is like this. That in order to commit to a value message, we're going to generate a random 256-bit value and call it the key. And then we're going to, as the commitment, return the hash of the key concatenated together with the message. And as the key value, we're going to return h of this key. And then later, to verify, someone is going to compute this same hash of the key they were given, concatenated with the message, and they're going to check whether that's equal to the commitment that they saw. Okay, so this is a way of using hash functions both in the commitment and in the verification. So now the security properties, if we go down to the security properties that were at the bottom of the previous slide, and we just plug in the definitions of how we're going to implement this here, that is, this used to say COM, given COM, infeasible defined message, we just plug in what COM is. COM is the hash of key concatenated with message. And similarly down here, this is what happens when we take what was written there before and plug in the definition of verify in COM. Okay, so now what these properties become, the first one is given h of key concatenated with message, it's infeasible to find message. Well, it turns out that that's exactly the hiding property that we talked about before. Key was chosen as a random 256-bit value, and therefore the hiding property says that if we take the message and we put before it something that was chosen from a very spread out distribution, like I said, a random 256-bit value, then it's infeasible to find the message. So this is exactly the hiding property. And this one down here turns out to be exactly the collision-free property. So that if someone can find two messages which have the same hash like this, well, then they have an input value here and an input value there that are different, and yet those have the same hash. And so because of the two security properties we've talked about for hashes so far, this commitment scheme will work in the sense that it will have the necessary security properties. Okay, so that's the second security property of hashes, that they're hiding, and the application of that is commitments. The third security property we're going to need is that they're puzzle friendly. And this is, again, a little bit more complicated, but let me just go through it a bit by bit. That for any possible output value y that you might want from the hash function, we're going to use y as an output value of the hash later, that if k is chosen from a distribution that has high min entropy, that is, k is chosen randomly from some set that's super spread out, then there's no way to find an x such that the hash of k and x is equal to y. So what this means is basically that if someone wants to target the hash function, if they want it to come out to some particular output value y, that if there's part of the input that is chosen in a suitably randomized way that it's very difficult to find another value that hits exactly that target. So the application we're going to use of this is we're going to build a search puzzle. And what that means is we're going to build a mathematical problem which requires searching a very large space in order to find the solution, and where there's no shortcuts, a way to find a good solution other than searching that large space. That's a search puzzle. To be more specific, the idea is that if we're given a puzzle ID, which is chosen from some high min entropy distribution, that is some very spread out probability distribution, and we're given a target set Y, which someone wants to make the hash function fall into, then we want to try to find a solution X, so that if we hash the puzzle ID together with the solution X, we get a result that's in the set Y. So the idea is Y is a target range or set of hash results that we want. ID specifies a particular puzzle, and X is a solution to the puzzle. And the puzzle-friendly property here implies that there's no solving strategy for this puzzle, which is much better than just trying random values of X. And so if we want to pose a puzzle that's difficult to solve, that we can do it this way, as long as we can generate puzzle IDs in a suitably random way. And we're going to use that later when we talk about Bitcoin mining. That's the sort of computational puzzle we're going to use. Okay, so we've talked about 3 properties of hash functions and 1 application of each of those. Now let me talk just very briefly about the particular hash function we're going to use. There are lots of hash functions in existence, but this is the one Bitcoin uses, and it's a pretty good one to use. It's called SHA-256, or SHA-256, and it works like this. Basically, it takes the message that you're hashing, and it breaks it up into blocks that are 512 bits in size. The message isn't going to be, in general, necessarily exactly a multiple of the block size, so we're going to add some padding at the end. And the padding is going to consist of, at the end of the padding, a 64-bit length field, which is the length of the message in bits. And then before that, it's going to consist of a 1-bit, followed by some number of 0 bits. And you choose the number of 0 bits so that this comes out exactly to the end of a block. So once you've padded the message so that its length is exactly a multiple of the 512-bit block size, you then chop it up into blocks, and you then execute this computation. You start with a 256-bit value called the IV. That's just a number that you look up in a standards document. And then you take the IV and the first block of the message, you take those 768 total bits, and you run them through this special function C, the compression function, and out comes 256 bits. You now take that with the next 512 bits of the message, run it through C again, and you keep going. Each iteration of C crunches in another 512-bit block of the message and mixes it in sort of logically to the result. And when you get to the very end, you have consumed all of the blocks of the message plus the padding. The result is the hash. That's a 256-bit value. And it's easy to show that if this function C, this compression function, is collision-free, then this entire hash function will also be collision-free. The other properties are a little bit more complicated, so I won't talk about them here. Okay, so we've talked about hash functions. We've talked about what hash functions do. We've talked about 3 properties of hash functions and applications of those properties, and the specific hash function that we use in Bitcoin. In the next lecture segment, we'll talk about ways of using hash functions to build more complicated data structures that are used in distributed systems like Bitcoin. In section 1.2, we're going to talk about hash pointers and their application. A hash pointer is a kind of data structure that turns out to be used a lot in the systems that we're talking about. And a hash pointer is basically a simple thing that we're going to take a pointer to where some information is stored, and we're going to, together with that pointer, store a cryptographic hash of the information. So whereas a regular pointer gives you a way to retrieve the information, a hash pointer is going to let us ask to get the information back. And it's also going to let us verify that the information hasn't changed. So a hash pointer tells us where something is and what its value was. Okay, and we're going to draw a hash pointer in diagrams like this. That we're going to have h of, and then an arrow that points to something. So anything drawn like this, think of it as being a hash pointer to this thing. It's a pointer to where it's stored, and it's also the hash of the value that this data had when we last saw it. And we can take hash pointers and we can use them to build all kinds of data structures. So a key idea here, take any data structure, a linked list, a binary search tree or something like that, and implement it with hash pointers instead of pointers as we normally would. For example, here's a linked list that we've built with hash pointers. And this is a data structure that we're going to call a blockchain. So just like a regular linked list where you have a series of blocks and each block has data as well as a pointer to the previous block in the list, here the previous block pointer will be replaced with a hash pointer. So it says where it is and what the value of this entire previous block was. And we're going to remember the head of the list like this, just as a regular hash pointer. Okay. And a use case for this, for a blockchain like this, is a tamper-evident log. That is, if we want to build a log data structure that stores a bunch of data so that we can add data onto the end of the log, but if somebody goes later and messes with data that is earlier in the log, we're going to detect it. That's what the tamper evidence means. So to understand why a blockchain gives us this tamper-evident property, let's ask what happens if an adversary wants to go back and tamper with data later that's in the middle of the chain. Okay, so let's assume that an adversary wants to tamper with this block down here. He wants to change the data here, and he wants to do it in such a way that we, the holders of the hash pointer at the head here, won't be able to detect it. All right, so the adversary changed the contents of this block, and therefore the hash here, which is a hash of this entire block, is not going to match up. Because the hash function is collision-free, it must be the case that the hash of this block is now different. And so we could detect the inconsistency between this data and the hash pointer that we remembered before. Or we could do that unless the adversary also tampers with the hash pointer. If he tampers with this hash pointer, then he makes these two match up. But now he's changed the content of this block. And what that means is that when we come back later and hash the contents of this block, it's not going to match the hash that we remembered before because the contents of the block has changed. And so we're going to detect the inconsistency between the contents of this block and this hash, unless the adversary also tampers with the block over here on the right. But now when he does that, the hash of this block is not going to match the hash that we remembered up here and the hash that we're holding on to. And this the adversary can't tamper with because this is the value that we remembered as being the head of the list. And so the upshot of this is that if the adversary wants to tamper with data anywhere in this entire chain, in order to keep the story consistent, he's going to have to tamper with hash pointers all the way back to the beginning, and he's ultimately going to run into a roadblock because he won't be able to tamper with the head of the list. And so what this means is that just by remembering this hash pointer, we've essentially remembered a kind of hash, a tamper-evident hash of the entire list all the way back to the beginning. And so we can build a blockchain like this containing as many blocks as we want, going back to some special block at the beginning of the list, which we might call the genesis block. And that's a tamper-evident log built out of a blockchain. Now another useful data structure that we can build using hash pointers is a binary tree. We can build a binary tree with hash pointers, and this is called, in the jargon, a Merkle tree, after Ralph Merkle, who invented it. And the idea is this. Suppose we have a bunch of data blocks, which we'll draw across the bottom down here. We're going to take consecutive pairs of these data blocks, and for these two data blocks, we're going to build a data structure here that has two hash pointers, one to each of these blocks. And similarly all the way across. We'll then go another level up, and this block here will contain a hash pointer of these two children down here, and so on all the way back up to the root of the tree. And then just like before, we're going to remember just the hash pointer up here at the head of the tree. And we can then, if we want, traverse down through the hash pointers to any point in the list, and we can make sure that the data hasn't been tampered with. Because just like I showed you with the blockchain, if an adversary tampers with some block down here at the bottom with the data, that will cause the hash pointer that's one level up to not match, so he'll have to tamper with that, and therefore he'll have to tamper with the hash pointer one level up from there, and therefore he'll have to tamper with the hash pointer one level up from there, and eventually he'll get up to the top where he won't be able to tamper with the hash pointer that we've remembered. So again, any attempt to tamper with any piece of data across the bottom will be insured against by just remembering the hash pointer at the top. Now another nice feature about Merkle trees is that unlike the blockchain that we built before, that if someone wants to prove to us that a particular data block is a member of this Merkle tree, all they need to show us is this amount of data. So if we remember just the root, and someone wants to convince us that this block is in the Merkle tree, they need to show us this block, and we can verify that the hash matches up. And then they need to show us this block, and we can verify that the hash of this matches that. They can show us this block, we verify that the hash of this block matches this hash pointer, and then they show us the data. And just by verifying the hashes up to the root, we can verify that this data block was in the Merkle tree. So that takes about log n items that we need to be shown, and it takes about log n time for us to verify it. And so with a very large number of data blocks in the Merkle tree, we can still prove membership in a relatively short time. Okay, so Merkle trees have various advantages. One advantage, of course, is the tree holds many items, but we just need to remember the one root hash, which is only 256 bits. We can verify membership in a Merkle tree in logarithmic time and logarithmic space. That's nice. And there's a variant, which is a sorted Merkle tree. That's just a Merkle tree where we take the blocks at the bottom and we sort them into some order, say alphabetical, lexicographic order, or numerical order, or some order that we agree on. Now, having done that, once we've sorted the Merkle tree, now it's possible to verify non-membership in a Merkle tree. That is, we can prove that a particular block is not in the Merkle tree. And the way we do that is simply by showing a path to the item that's just before where that item would be and just after where it would be. And then we can say, look, both of these items are in the Merkle tree, they're consecutive, and therefore there's no space in between them. There's nothing in between them, and so the thing that we're trying to prove non-membership of can't be there. All right, so a Merkle tree is a binary search tree built with hash pointers. We can do logarithmic time membership proofs, non-membership proofs if we sort the tree, and it's very efficient. More generally, it turns out that we can use hash pointers in any pointer-based data structure, as long as the data structure doesn't have cycles. If there are cycles in the data structure, then we won't be able to make all the hashes match up. If you think about it, in an acyclic data structure, we can sort of start near the leaves or near the things that don't have any pointers coming out of them, compute the hashes of those, and then work our way back sort of toward the beginning. But in a structure with cycles, there's no end that we can start with and compute back from. So, for example, a directed acyclic graph out of hash pointers, and we'll be able to verify membership in that DAG very efficiently, and it will be easy to compute. So this is a general trick that you'll see over and over throughout the distributed data structures and throughout the algorithms that we talk about later in this lecture and in subsequent lectures. In segment 1.3, we're going to talk about digital signatures. This is the second cryptographic primitive along with hash functions that we need as building blocks for the cryptocurrency discussion later on. So a digital signature is supposed to be just like a signature on paper, only in digital form. And what that means is this. What we want from signatures is two things. First, that just like an idealized paper signature, only you can make your signature, but anyone who sees your signature can verify that it's valid. And then the second thing you want is that the signature is tied to a particular document so that somebody can't take your signature and snip it off one document and glue it onto the bottom of another one. Because the signature is not just a signature, it signifies your agreement or endorsement of a particular document. Okay, so the question is, how can we build this in a digital form using cryptography? So let's get into the nuts and bolts. Here's an API for digital signatures. There are three operations that we need to be able to do. The first one is we need, in the beginning, to be able to generate keys. And so we have a generate keys operation, and we tell it a key size. How big in bits should the keys be? And this produces two keys, SK and PK. SK will be a secret signing key. This is information you keep secret that you use for making your signature. And PK is a public verification key that you're going to give to everybody and that anybody can use to verify your signature when they see it. Okay. The second operation is the sign operation. So the sign operation, you take your secret signing key and you take some message that you want to put your signature on, and it returns SIG, which is a signature. It's just some string of bits that represents your signature. And then the third operation is a verify that takes something that claims to be a valid signature and verifies that it's correct. It takes the public key of the signer, it takes the message that the signature is supposedly on, and it takes the supposed signature. And it just says yes or no, is this a valid signature? Okay, so these three operations, these three algorithms constitute a signature scheme. And I'll note that the first two can be randomized algorithms. The verification won't be, it will always be deterministic. And in fact, if you think about it, generate keys had better be randomized because it ought to be generating different keys for different people. Okay, so the requirements for the signatures at a slightly more technical level are the following two requirements. First of all, that if a signature is, that valid signatures will verify. If a signature is valid, that is, if I sign a message with SK, with my secret key, that if someone then later tries to validate that using my public key and the same message, that will validate correctly. So this says that that signatures are useful at all. But then the second thing you want is that it's impossible to forge signatures. That is, an adversary who knows your public key, who knows your verification key, and gets to see signatures on some other messages, can't forge your signature on some message that he wants to forge it on. And in order to explain this property in a little bit more detail, it's normally formulated in terms of a sort of game that we play with an adversary. So the game, I'll depict it here with this diagram. So over here on the left, you have the challenger, who's a TV judge, and the challenger is going to test a claim by an attacker. The attacker claims that he can forge signatures, and we're going to test that claim, and the judge will pass judgment on it. The attacker here, this guy is actually Whit Diffie, who is one of the inventors of digital signatures, of the concept of digital signatures, and a distinguished cryptographer, so I thought I'd let him play the attacker role here. Okay, so the game works like this. The first thing we do is we use generate keys to generate a secret key, a secret signing key, and a public verification key that match up. Now we give the secret key to the challenger, to the judge, and we give the public key to both parties, both to the challenger and to the attacker. So the attacker only knows information that's public. He only knows the public key. And his mission is going to be to try to forge a message. The challenger knows the secret key, so he can make signatures. Right? Now, if you think about a real-life application, and a real-life attacker would be able to see valid signatures from their would-be victim on a number of different documents. And maybe the attacker could even manipulate the victim into signing innocuous-looking documents, if that's useful to the attacker. So in our game, we're going to allow the attacker to get signatures on some documents of his choice. And we see that in the diagram like this. The attacker is going to send over a message M0 to the challenger, and the challenger is going to sign that message and send the signature back. The attacker can look at that, scratch his head a little bit, and send over another message, M1. The challenger will sign that. And we do that for as long as the attacker wants. The attacker can send over any sequence of messages he wants and get signatures on them. Once the attacker is satisfied that he's seen enough signatures, and we're going to let him see only a plausible number, then he's going to pick some message M that he wants to forge a signature on, and he's going to try to forge a signature. And of course, there's a rule that says that this M, this message that he's trying to forge a signature on, isn't one of the messages that he's already seen. Because it would be really easy for him to send over a valid signature on M0. I mean, we sent him a valid signature on M0 earlier. So he's going to pick some other message that he hasn't seen a signature for already, and he's going to send over what he claims is a signature on that message. And then the question is, can he succeed? So the challenger is going to run the verify algorithm, use the public verification key, and on that message, and the signature that the attacker provided, and is going to check whether it verifies. And if it does verify, if this returns true, then the attacker wins. The attacker has forged a message. And so this game is what we use to define what it means for a digital signature scheme to have the unforgeability property. And if we want to get really precise, what we say is that the attacker's probability of winning this game is negligible, and that that's true no matter what algorithm the attacker is using. In other words, we're going to say that the signature scheme is unforgeable if, no matter what algorithm the attacker is using, the attacker has only a negligible chance of successfully forging a message. And if we have that property together with the much easier property that valid messages verify, then we have a digital signature scheme that is suitable. Okay. Now, there's a bunch of practical things that we need to do to turn that algorithmic idea into a more practically implementable signature mechanism. For example, the algorithms we talk about are randomized, at least some of them will be, and so we need a good source of randomness. And the importance of this really can't be underestimated. Band randomness will sink you, your algorithm will be insecure. And I'll just point out here that attacks on the source of randomness are a favorite trick of intelligence agencies, and those are the people who know what kinds of attacks are likely to be successful. In practice, there's a limit on the message size that you're able to sign because real schemes are going to operate on bit strings of limited length. The fix to that is simply to use the hash of the message rather than the message itself. That way the message can be really big, but the hash will be only 256 bits. And because hash functions are collision-free, it's safe to use the hash of the message as the input to the digital signature scheme rather than the message. And by the way, a fun trick, which we'll see used later, is that you can sign a hash pointer. And if you sign a hash pointer, then the signature covers or protects the whole structure, not just the hash pointer itself, but everything it points to and everything it points to. For example, if you were to sign the hash pointer that was at the end of a blockchain, the result is that you would effectively be digitally signing the entire contents of that blockchain. That's a useful trick that we'll see used later. Okay, now let's get into the nuts and bolts. Bitcoin uses a particular digital signature scheme that's called ECDSA. That's the elliptic curve digital signature algorithm, and it's a US government standard. And we won't go into all the details of how ECDSA works. It relies on some extremely hairy math. And trust me, you don't want to see all the details of how that works. You can look it up if you're interested. So we'll skip that. One thing I'll note, though, is with ECDSA, good randomness. I said this before, but I'll say it again because it's really essential. Good randomness is especially essential with ECDSA. If you use bad randomness in generating keys or even in signing, you probably leaked your private key. It stands to reason that if you use bad randomness in generating a key, that the key that you generate is maybe not secure. But it's a quirk of ECDSA that even if you use bad randomness just in making a signature using your perfectly good key, that also will leak your private key, and then it's game over. So we need to be especially careful about this in practice. This is a common mistake. So that completes the discussion of digital signatures as a cryptographic primitive. And then in the next segment, we'll move on and talk about some applications of digital signatures that will turn out to be useful in building cryptocurrencies. In segment 1.4, we'll move on, having covered digital signatures, and talk about a nice trick that we can use that goes along with digital signatures. And the useful trick is this. The idea is to take a public key, one of those public verification keys from a digital signature scheme, and equate that to an identity. That is an identity of a person or an actor in a system. So if you see a signature that verifies correctly, that is, if you see a signature such that you can verify with someone's public key that that is a signature on a particular message, then you can think of that as that public key saying the message. You can literally think of a public key as kind of like an actor or a party in a system, and that they can make statements by signing those statements. And so if you think in that mindset, then this public key is like an identity. It's an actor who can do stuff in the system. And if you think about it then, for someone to speak for PK, that is for someone to be able to make statements that will be seen as coming out of PK's mouth, you have to know the matching secret key, SK. And so if you know the secret key that corresponds to the public key, PK, then you can sign messages with that secret key, and what you're doing essentially is making statements on behalf of that public key. And that means that there is an identity in the system which only you can speak for. And of course, that's what you want an identity to be, something that one person can speak for or on behalf of that everybody can see. All right, so if we're going to treat public keys as identities, one of the consequences of that is that you can make a new identity whenever you want. If you want to make a new identity, you just do this. You create a new random key pair, SK and PK, by doing the generate keys operation in our digital signature scheme. And we get out SK and PK. PK is then the public name that you can use. That's the name of that identity, what it's called. Although in practice, you'd probably use the hash of PK because public keys are big. But again, we'll leave that aside as a detail. So PK, or the hash of it, is the public name that you use to talk about the identity. And SK, the secret key, is the information that lets you, the person who generated this identity, speak for the identity. You control the identity because only you know the secret key. And if you generated this in such a way that the public key PK looks random, then nobody needs to know who you are. You can generate a fresh identity that looks random, that looks like a face in the crowd, that only you can control. This brings us to the idea of decentralized identity management. That rather than having a central place that you have to go in order to register as a user in a system, you don't need to get a username, you don't need to inform someone that you're going to be using a particular name. If you want a new identity, just make one. Anybody can make a new identity at any time, and you can make as many as you want. If you prefer to be known by 5 different names, no problem, just make 5 identities. If you want to be somewhat anonymous for a while, you can make a new identity, use it just for a little while, then throw it away. All of these things are possible with decentralized identity management, and there's no central point of control, so that you don't have to have anyone who's in charge of it. The system operates in an entirely decentralized way. And this is the way Bitcoin, in fact, does identity. These identities are called addresses in Bitcoin jargon. And so you'll hear the term address used in talking about Bitcoin and cryptocurrencies. But what that really is just a public key or a hash of a public key. It's an identity that someone made up out of thin air as part of this decentralized identity management scheme. Now, the obvious question that arises when you're talking about decentralized identity management and people making up these identities is, how private is this? And the answer is, it's complicated. On the one hand, the addresses that are made up this way are not connected to your real-world identity. You can execute a randomized algorithm. It will make some kind of PK that looks kind of random, and nothing exists initially to connect that to who you are. You can do that in the privacy of your own home. So that's good news if you want to be able to act privately. But the bad news if you want to act privately is that if that address, if that identity is making a series of statements over time, if it's engaging in a series of acts over time, that people can see that whoever this is has done a certain series of actions, and they can start to connect the dots. Gee, this person is acting a lot like Joe. Maybe this person is Joe. And so an observer can link together these things over time and make inferences. And so this balance between, on the one hand, there being no initial tie to real-world identity, and on the other hand, that a pattern of behavior of an address emerging over time, and the question of what can be inferred and which dots can be connected, that gets pretty complicated. And that's really the question of privacy in a cryptocurrency like Bitcoin. And there's a whole lecture about that later on. And so I'm not going to steal the thunder of that lecture. I just want to give you an idea of how decentralized identity makes privacy a complicated question. In segment 1.5, we're going to move from talking about cryptography, and we're going to move on to cryptocurrencies. Now, I know that many of you showed up here for the cryptocurrency stuff, and trust me, there will be a lot more cryptocurrency material in future lectures. Unfortunately, we needed to eat some of our cryptographic vegetables in order to have the background to talk about cryptocurrencies. And now you'll see, when I start talking about cryptocurrencies, how these pieces fit together and why the cryptographic operations like hash functions and digital signatures are actually useful. All right, so in this section, I want to talk about some simplified cryptocurrencies that give us ideas about how systems like Bitcoin work. Of course, it's going to require about 10 more lectures in order to really spill out all of the implications of how Bitcoin works and what that means. But let me talk about some very simple cryptocurrencies to get the discussion started. And first, let's talk about Goofy Coin. Goofy Coin is about the simplest cryptocurrency we can imagine. And it works kind of like this. There are just a couple rules of Goofy Coin. The first rule is that Goofy can create new coins. Goofy can make a new coin whenever he wants, and when he makes a new coin, it belongs to him. So when Goofy makes a coin, it's represented by a data structure like this. Here you have the create coin operation, and there's a unique coin ID that Goofy generated. And then there's a digital signature that was put on it by Goofy, which anyone can verify. So anyone being given this can verify that the signature is valid and that it's a signature of this statement. And new coins belong to Goofy by definition because those are the rules that Goofy made. So that's the first rule. Goofy can create new coins. The second rule of Goofy Coin is that whoever owns a coin can pass it on to someone else. They can spend it. So for example, here we have the coin that I showed you before that Goofy created. And now we're going to take a hash pointer to that coin. And then we're going to create a statement. Goofy's going to make a statement that says, pay this to Alice. Alice is being named by a public key here. Pay to public key Alice the coin that's represented by this hash pointer. And this is also signed by Goofy. Now, Goofy is the one who owned that coin, and so Goofy has to sign any transaction that spends the coin. And once this has happened, now Alice owns the coin. Alice owns the coin, and Alice can prove that she owns the coin because she can present this data structure here, which is validly signed by Goofy and points to a coin that was validly owned by Goofy. And so the correctness of this coin is self-evident in the system. Now Alice can move on, and she can spend the coin as well. So here we have the coin we had before. This is down here at the bottom. We have the creation of the coin signed by Goofy. Now Goofy paid the coin to Alice via this hash pointer, and he signed that. Now Alice is the owner of the coin. Now she can create a statement like this that says, pay this coin to Bob's public key, and here's a hash pointer to the coin. And now Alice signs that. So because Alice was the valid owner of the coin, which we could verify by walking this chain, now we know that this is valid and the coin belongs to Bob. So Bob is now the owner of this coin. So those are all the rules of Goofy Coin. Goofy can create new coins by simply signing a statement that he's making a new coin with a unique coin ID. And then whoever owns a coin can pass it on to someone else by signing a statement saying, pass on this coin to person X. And you can verify the validity of a coin by simply following the chain and verifying all of the signatures along the way. That's Goofy Coin. All right. Now, there's a problem, though. There's a big security problem with Goofy Coin, and we can see it in this structure here. So look at this coin here. This is the coin that Goofy made and then paid to Alice. Alice was the owner of that coin, and there's a problem. Alice paid this coin on to Bob, but now Alice makes another data structure like this, which pays to Chuck the very same coin. And this is signed by Alice. Now, if Chuck doesn't know about this thing up in the upper left, this data structure, let's say Alice just gave that to Bob and didn't tell Chuck. Now, Chuck will look at this and he'll think that this is perfectly valid, and now he's the owner of the coin. Chuck has a valid-looking claim to be the owner of this coin, and Bob has an equally valid-looking claim to be an owner of this coin, and that's a problem because coins are not supposed to work that way. This is called a double spending attack. It's called double spending because Alice is spending the same coin twice. And double spending attacks are one of the key problems that a cryptocurrency has to solve. Goofy Coin does not solve the double spending attack, and therefore Goofy Coin is not secure. So although Goofy Coin is simple and we understand its rules, it won't cut it as a cryptocurrency because it allows double spending. So in order to build a cryptocurrency that is going to be workable, we need to have some solution to the double spending problem. And indeed, the double spending problem is the main design challenge that we face in designing a cryptocurrency. So we need to somehow improve on Goofy Coin, and we'll do that by designing another coin, which I'll call Scrooge Coin. Scrooge Coin is going to be rather like Goofy Coin, except it will solve the double spending problem in a particular way. And this coin was created by Scrooge. Okay. So this is a little bit more complicated in terms of data structures, but here's one of the key ideas, that Scrooge is going to publish a history of all the transactions that have happened. This will be a blockchain, that data structure we talked about before, and it will be digitally signed by Scrooge. So anyone can, and it looks like this, of course. It's a series of blocks, data blocks. Each block will have one transaction in it. This block has the transaction with transaction ID number 73. And it has the contents of this transaction, and then there's a hash pointer to the previous block in the history. Okay, and then Scrooge will take the hash pointer, which represents this entire structure, and he'll digitally sign it and publish it. Now anybody can verify that Scrooge really did sign this hash pointer, and then they can follow this chain all the way back and see what is the entire history of all the transactions in the history of Scrooge Coin as endorsed by Scrooge. Okay. Now I said here that we put one transaction in each block. We do that for simplicity of explanation, but in practice, as an optimization, we'd really put multiple transactions into the same block, as Bitcoin does. So you can bear in mind as I talk about Scrooge coin that that's the way we'd really do it in practice. So Scrooge publishes this history. What does the history do? Well, the thing the history does for us is it allows us to detect double spending. Because assume Alice owns a coin, and she's going to pay that coin on to Bob. And she's then later going to try to pay that coin on to Charlie. Charlie's going to notice that something is wrong because Charlie will be able to look into the history and see that Alice already paid that coin to Bob. In fact, everyone will be able to see that Alice already paid that coin to Bob. So if she tries to pay that coin to Chuck, then everyone can see that that's a double spend and they'll be able to reject it. Scrooge will reject it, and everyone else will reject it and know that they really shouldn't trust Alice. All right. So in Scrooge coin, there are two kinds of transactions. The first kind is a create coins transaction, and what it does is create new coins. That's like the operation Goofy could do in Goofy coin that makes a new coin. But here, we're going to allow multiple coins to be created in one transaction. So here's what a create coins transaction looks like. It has transaction ID number 73, let's say in this case. Its transaction type is create coins, and then down here there's a list of which coins are created. Each coin is going to have a serial number within this transaction, 0, 1, 2, etc. Each coin has a value. It's worth a certain number of Scrooge coins. And each coin has a recipient, which is going to be a public key who gets that coin as it's created. So this transaction type creates a bunch of new coins and assigns them to people as initial owners. Now we're going to have a concept in Scrooge coin of a coin ID. That refers to a particular coin. So this particular coin here is coin ID 73 because it was created in transaction 73 and it was number 0 within that transaction. Similarly, we have 73 73 and so on. So every coin in Scrooge coin has a coin ID that we can use to refer to it. A create coins transaction is always valid. Why is it valid? Well, because Scrooge said so, and they call it Scrooge coin for a reason. If Scrooge puts this into the history which he signs, then it's valid by definition. We don't need to worry about whether Scrooge is entitled to create coins, just like we didn't need to worry in Goofy coin about whether Goofy is entitled to create coins. The rules of the system, which were created by Scrooge, simply say that if Scrooge wants to make coins, then that's valid. So anything he puts into the history is valid. The second kind of transaction we're going to talk about is a pay coins transaction. And this is a transaction that consumes some coins and destroys them and creates new coins of the same total value, but which might belong to different people. So over here on the left, we have an example of what a pay coins transaction looks like. This is transaction ID number 73, let's say. Its type is pay coins. We have here a list of the coins that this one consumes. All of these coins are being consumed and destroyed by this pay coins transaction. So we're going to add up the value of all of those coins, and then we're going to create a bunch of new coins, down here 0, 1, and 2, etc., just like before in the create coins transaction. Each one has a value. Each one will belong to a certain recipient. And those new coins had better add up to the same total value as the coins that we consumed. And then at the bottom, we have a set of digital signatures. This transaction has to be signed by everyone who's paying in a coin. So if you're the owner of one of the coins that's going to be consumed in this transaction, then you need to digitally sign the transaction to say that you're really okay with spending this coin. The rules of Scrooge coins say that a pay coins transaction is valid if 4 things are true. First, if the consumed coins are valid, that is, they really were created in previous transactions. Second, that the consumed coins were not already consumed in some previous transaction. That is, that this is not a double spend. Third, that the total value of the coins that come out of this transaction is equal to the total value of the coins that went in. And finally, that the transaction is validly signed by the owners of all of the consumed coins. If all of those things are true, then this pay coins transaction is valid. Scrooge will accept it. He'll write it into the history, into the blockchain, and everyone will see that this transaction has happened. One thing to note about this scheme is that coins are immutable. Coins are never changed, they're never subdivided, they're never combined. All they are is created once in one transaction and then later consumed in some other transaction. But you can get the same effect as being able to subdivide or pay on or combine coins by using transactions. For example, if you want to subdivide a coin, you can just create a new transaction that consumes that one coin and then produces two new coins of the same total value. And if you want, you can give those two new coins back to yourself. That's a way that you can subdivide a coin that you own. Similarly, you can combine coins or you can pay on a coin, in effect, by just creating a chain of transactions, each of which pass that value on in the form of a new coin to someone else. So although coins are immutable in this system, it has all of the flexibility of a system that didn't have immutable coins. Okay, now we come to the core problem with Scrooge coin. Scrooge coin will work. People can see which coins are valid. It prevents double spending because everyone can look into the blockchain and see that all of the transactions are valid and that every coin is consumed only once. But the problem is Scrooge. Scrooge thinks this is fine, right? Scrooge says, don't worry, I'm honest. But the fact is, if Scrooge starts misbehaving, then we're going to have a problem. Or if Scrooge just gets bored of the whole Scrooge coin scheme and stops doing the things that he's supposed to do, then the system won't operate anymore. And so the problem we have here is centralization. That although Scrooge is happy with this system, we as users of it might not be. So the central technical challenge that we need to solve in order to improve on Scrooge coin is, can we de-Scroogify the system? That is, can we get rid of that centralized Scrooge figure? Can we have a cryptocurrency that operates like Scrooge coin in many ways, but doesn't have any central trusted authority? In order to do that, we're going to need to figure out how to provide the services that Scrooge provides, but do it in a decentralized way, in a way in which no particular party is particularly trusted. That means we're going to need to figure out how everyone can agree upon a single published blockchain that is the agreed upon history of which transactions have happened. We need to figure out how people can agree which transactions are valid and which transactions have actually occurred. And we need to figure out how we can assign IDs to things in a decentralized way. If we can solve all of those problems, then we can build a currency that is very much like Bitcoin, which is like Scrooge coin, but without a centralized party. But in order to do that, it's going to take a few more lectures, and we hope you'll stick around and watch them. Thanks.
Hello, and welcome to the second lecture, which is going to be all about decentralization in Bitcoin. Now, in the first lecture, you saw a lot of the crypto basics that underlie Bitcoin, and we ended with a simple currency that we called Scrooge coin that seems to achieve a lot of what we want in a ledger-based cryptocurrency, except for one big glaring problem, which is that it relies upon the centralized authority called Scrooge. And we ended with the question of, how do we de-Scroogify this currency? How do we go to a decentralized version of this? That's what we're going to see today. What I find cool about this is that the way in which Bitcoin achieves decentralization is not purely technical, but it's a combination of technical and clever incentive engineering. And at the end of this lecture, you should have a really good appreciation for how this happens, and a lot of the magic or the mystery of Bitcoin should become clear to you, and how it works, and why it's secure, and what makes it tick. So it turns out that decentralization is an important concept not just for Bitcoin, but in fact, this notion of competing paradigms of centralization versus decentralization plays out in a variety of different digital technologies. To understand Bitcoin's decentralization, I want to start with the caveat that decentralization almost always is not all or nothing. Almost no system is purely decentralized or purely centralized. And a good example of this is email, which is a decentralized system fundamentally, I would say. It's based on a standards-based protocol, SMTP, but what has happened, especially in the last decade or so, is that we see a dominance of a few different webmail providers, which are sort of centralized service providers, and this might be a good model for understanding what might be happening to Bitcoin. So with that, let's delve into some of the technical aspects of Bitcoin's decentralization, and I would break this down into at least 5 different questions. Questions like, who maintains this ledger of transactions? who has authority over which transactions are valid, who creates new Bitcoins, and in fact other questions like who determines how the rules of the system change and how do Bitcoins acquire exchange value. So these are all components of decentralization of the Bitcoin protocol, more or less. And the first three of these are going to be the questions that we will consider in this lecture. And when I say how is Bitcoin decentralized, what I mean encompasses the first three of these meanings. And I want to emphasize that there are aspects to decentralization beyond the protocol. That includes things like Bitcoin exchanges, where you can convert Bitcoin into other currencies. It includes things like wallet software and a variety of other service providers. And so even though the underlying protocol is decentralized, these services that develop on top of it may be centralized or decentralized to varying degrees. And just to drive home this point, let me show you three different aspects of Bitcoin and where they fall on the centralization-decentralization spectrum. First, there's the peer-to-peer network. And this aspect of Bitcoin, I would say, is the closest thing to purely decentralized. Why is that? Because anybody can run a Bitcoin node, and there's a fairly low barrier to entry. You can go online, you can download a Bitcoin client yourself. It requires a lot of disk consumption on your computer, but basically you can run that on your laptop or your PC yourself. And currently there are several thousand Bitcoin nodes, and so this really resembles a peer-to-peer decentralized system. But that's not the only component of Bitcoin. There's also Bitcoin mining, which we'll study later in this lecture. And Bitcoin mining is technically also open to anyone, but it turns out that it requires a very high capital cost. It's a consequence of how the system happens to have evolved. And because of this, there has been a high centralization or a concentration of power in the Bitcoin mining ecosystem. And the community frequently sees this as quite undesirable. So this aspect of Bitcoin is not quite as decentralized as one might want it to be. And here's a third aspect, updates to the software. And this really gets to how and when the rules of the system change. And once again here, one can conceptually imagine that everybody running a Bitcoin node will look at the Bitcoin specification and maybe even create their own software. And again, you have a purely decentralized system. But of course, that's not how it works in practice. The core developers are really trusted by the community, and they have a lot of power when it comes to determining what Bitcoin software each of these nodes will run on their computer. So we've talked in a generic manner about centralization and decentralization. Let's now talk at a bit more technical level about Bitcoin and decentralization. And a key word that's going to come up again and again here is consensus, specifically distributed consensus. So what am I talking about here? At a technical level, the key challenge that you have to solve to build a distributed eCash system is called distributed consensus. And this is a class of protocols that's been studied for decades in the computer science literature. But intuitively, you can think of it as our goal being to decentralize Scrooge coin, which is the hypothetical currency that we saw in the first lecture. So as I said, there's decades of research in computer science on these consensus protocols, and the traditional motivating application for this is reliability in distributed systems. What do I mean by that? Imagine you're in charge of the backend for a company like Google or Facebook. These companies typically have thousands or even millions of servers, which form a massive distributed database that records all of the actions that happen on the system, like users' comments and likes and posts and so on. So when a new comment, let's say, comes in, the way it'll be recorded is that there might be 10 or 15 different nodes in that massive backend that might contain copies of this action. Now, what the server needs to make sure is that that comment either gets recorded in all copies of that database or none of them. If for some reason, because some of these nodes might be faulty, the action gets recorded in none of the databases, it's okay. You can go back to the user and say, there was a problem saving your post, would you please try again? On the other hand, if some of the copies of the database saved it and others didn't, then you'd be in a lot of trouble because you'd have an inconsistent database. So this is the key problem that motivated the traditional research on distributed consensus. And you can sort of see the similarities to Bitcoin here, but we're going to talk in a bit more detail about the similarities and differences. So that was the traditional motivating application, but we can also imagine that if we achieved a distributed consensus protocol, and we were able to use that to build a massive global scale distributed key value store that maps arbitrary keys or names to arbitrary values, then that will enable a lot of applications. For example, a distributed domain name system, which is simply a mapping between human understandable domain names to IP addresses. or a public key directory, which is a mapping between user email addresses, let's say, to their public keys, or even things like stock trades. Because this distributed database, instead of keeping track of who's paid whom how much money, would keep track of who's transferred what units of which stock to whom. And the cool thing about this is that now that Bitcoin has solved the distributed consensus problem in a certain sense that we'll try to understand in this lecture, we can also go ahead and try to think about solutions to all of these other related problems. And in fact, there are many altcoins. And altcoins, we'll have several more lectures about altcoins, but very briefly, altcoins are systems built on Bitcoin-like principles to achieve perhaps slightly different goals. Sometimes currency systems, sometimes not currency systems, such as one of these applications. And so, given that we can solve distributed consensus now, and given that we can build a global distributed key value store, it enables a lot of these other cool applications. Okay, let's go to a technical definition now. The technical definition of distributed consensus is really quite simple. Imagine that there is a fixed number n of nodes or processes, and each of these nodes has some input value. And then a consensus protocol happens, and the two requirements on this consensus protocol are that the protocol should terminate, and all correct nodes should decide on some value, the consensus value. Right? And I say correct nodes because some of the nodes might be faulty or even outright malicious. And the second requirement is that this value that they agree upon cannot be an arbitrary value, but it should be a value that was proposed as input by at least one of these correct nodes. So it's really that simple, but let's try to see what this might mean in the context of Bitcoin. So to understand how distributed consensus could work in Bitcoin, let's start with a reminder that Bitcoin is a peer-to-peer system, right? So what I mean when I say that Bitcoin is a peer-to-peer system is that when Alice wants to pay Bob, what she does is she's going to broadcast a transaction to all of the Bitcoin nodes that comprise the peer-to-peer network. And you can see here the structure of the transaction. This is similar to Goofy Coin that we saw in the first lecture. And what a transaction is going to have is it's going to have Alice's signature, which the other nodes need in order to know that it really in fact came from Alice. It's going to have Bob's public key, which also acts as his address at which he wants to receive Bitcoins. And further, it contains a hash. What is this hash? Recall this notion of hash pointers that we saw in the first lecture. So this hash is a way for Alice to link together this transaction or this coin to her receipt of this coin from someone else previously. Right? So those are the things that are contained in this data structure that we call a transaction, and she's going to broadcast that to all of the Bitcoin peer-to-peer nodes. And notice something funny here. Bob's computer is nowhere in this picture. Now Bob, if he wants to be notified that this transaction did in fact happen and that he got paid, he might want to run a Bitcoin node that's one of these peer-to-peer nodes in order to listen in on the network and be sure that he's received that transaction, but his listening is not in fact necessary for him to receive the funds. The Bitcoins will be his whether or not he's running a node on the network. So given this peer-to-peer system, what is it exactly that the nodes might want to reach consensus on? Well, given that a variety of users are broadcasting these transactions to the network, what everybody wants to reach consensus on is exactly which transactions were broadcasted and the order in which these transactions happened. Right? So what does that mean specifically? How consensus could work in Bitcoin is that at any given time, all the nodes in the peer-to-peer network would have a sequence of blocks of transactions that they've reached consensus on. So recall that in Scrooge Coin, for optimization purposes, for efficiency, we put transactions into blocks and we link these blocks together on a blockchain. So we're utilizing a similar principle here. We could do consensus on transactions one by one. That would be okay. It would just be inefficient. So instead, we do consensus on a block by block basis. So at any given point, all these nodes in the peer-to-peer network would have the sequence of blocks that they've agreed upon already. And each node would then have a set of outstanding transactions that it has heard about. So recall that for these transactions, consensus has not yet happened. And so almost by definition, each node might have a slightly different version of the outstanding transactions that it's heard about. The peer-to-peer network is not perfect, so some node may have heard about a transaction, but not other nodes. So given that we have the setup, what could happen is that you have the sequence of blocks that everybody has agreed upon. A block is just a series of transactions. And now there are these, let's say, these 3 nodes in the system, each of whom proposes, each of whom has an input, the set of outstanding transactions that it's heard about. And they execute together some consensus protocol. And for the consensus protocol to succeed, you can select any valid block, even if it's a block that was proposed by only one node. And for a block to be valid, all of these transactions have to have the right crypto signatures and so on. So you could select any of these valid blocks and the consensus protocol would still be okay. If some transaction somehow didn't make it into this particular block that gets chosen as the result of a consensus protocol, it could just wait and get into the next block. Right? So maybe this green block gets selected, it gets added to the consensus blockchain, and then the protocol proceeds in rounds. So if you took the traditional theory of distributed consensus and applied that to Bitcoin, this is the sort of system that you might end up with. Now this has some similarities to how Bitcoin works, but it's not exactly how Bitcoin works. And why is that? And the reason for this is simple. Doing things this way is a really hard technical problem for a variety of reasons. There are some obvious ones. Nodes might crash and nodes might outright be malicious. But also because the network is highly imperfect. It's a peer-to-peer system. Not all pairs of nodes are connected to each other. There could be faults in the network because of poor internet connectivity and so on. And finally, there's going to be a lot of latency in the system because all of these things happen over the internet. They're not even within a single data center or something like that. And one particular consequence of this high latency is that there is no notion of global time. What does this mean and why is this important? It means that not all nodes can agree to a common ordering of events simply based on observing timestamps. It just doesn't work like that. So you can't possibly design your protocol by saying things like, take the node that sent the first message in step 1 and have that node do something in step 2. You just can't work like that because not all nodes will agree on which message was sent first in the first step of the protocol. So this really puts serious constraints on what sorts of algorithms you can really put into your consensus protocols. And in fact, because of these constraints, a lot of the literature on distributed consensus is somewhat pessimistic, and many impossibility results have been proved. I'm just going to name a couple of these in case you want to look them up, but I won't go into too much detail. One impossibility result that's very well known and pretty simple to understand is called the Byzantine generals problem. And a much more subtle one, known for the names of the authors who first proved it, is called the Fisher-Lynch-Patterson impossibility result. Under some conditions, which include the nodes acting in a deterministic manner, what they proved is that consensus is impossible even with a single faulty process. So despite these impossibility results, there are a few well-known protocols, and Paxos is probably one of the better known. And what Paxos does is it makes certain compromises. What it gives you is that it never produces an inconsistent result, which would be really bad, but it accepts the trade-off that under certain conditions, albeit rare ones, the protocol can get stuck and fail to make any progress. But here's the interesting thing. These impossibility results were, they were proved in a different model. They were intended to study distributed databases. And this model doesn't carry over that well to the setting that Bitcoin operates under. So what these results really tell us more about the model than about the problem, in fact. And what Bitcoin does is that it violates a lot of the assumptions that go into these models. And because of that, consensus in Bitcoin ironically works better in practice than in theory. And what this really means is that the theory that was developed for a different set of problems needs to catch up in order to be able to say really interesting things about Bitcoin. But nevertheless, that theory is quite important because, for example, it can help us predict unforeseen attacks and really be able to come to strong guarantees on the nature of consensus and security in Bitcoin. So what are these different assumptions? What are some things that Bitcoin does differently? Well, first of all, it introduces the idea of incentives. And this is very different from any previous system for distributed consensus. And this is only possible in Bitcoin because it is a currency and you can use that currency to give incentives to the participants for acting honestly. And so Bitcoin doesn't quite solve the distributed consensus problem in a general sense, but it solves it in the context of a currency system. The other thing that it does differently is that it really embraces the notion of randomness. And what I mean by that is one of the things it does is it does away with the notion of a specific starting point and ending point for consensus. Instead, consensus happens over a long period of time, about an hour in the practical system, but even at the end of that time, you're not 100% sure that a transaction or a block that you're interested in has made it into the consensus blockchain. Instead, as time goes on, your probability goes up higher and higher, and the probability that you're wrong in making an assumption about a transaction goes down exponentially. So that's the kind of inherently probabilistic guarantee that Bitcoin gives you, and that's why it's able to completely get around these traditional impossibility results on distributed consensus protocols. So let's now dig into the technical details of Bitcoin's consensus algorithm. And while we're looking at that, we should keep in mind that Bitcoin does all of this without nodes having any persistent long-term identities. And this is yet again a difference from how traditional distributed consensus algorithms operated. And if nodes did have identities, it would make things a lot easier for a couple of reasons. One is a pragmatic reason. It would allow you to put into your protocol things like, now the node with the lowest numerical ID should take some step or something like that. So that's a simple pragmatic reason, which already, if nodes are completely anonymous, becomes harder to do. But a much more serious reason for nodes to have identities is for security, because if nodes were identified and it weren't trivial to create new node identities, then we could make assumptions like, let's say that less than 50% of the nodes are malicious, and we could derive security properties out of that. So for both of these reasons, the consensus protocol in Bitcoin is a bit harder. But why is it exactly that Bitcoin nodes don't have identities? Well, it's for a couple of reasons. One is that if you're in a decentralized model, in a peer-to-peer system, there is no central authority to give identities to nodes and verify that they're not creating new nodes at will. And in fact, the technical term for this is a Sybil attack. Sybils are just copies of nodes that a malicious adversary can create to look like there are a lot of different participants, when in fact all those pseudo-participants are really controlled by the same adversary. The other reason is that pseudonymity is inherently a goal of Bitcoin. Even if it were possible or easy to establish identities for all nodes or all participants, we wouldn't necessarily want to do that. So Bitcoin doesn't give you strong anonymity guarantees out of the box, in that the different transactions that you make can probably be linked together, but at the same time, nobody is forcing you to put your real-life identity, like your name or IP address or anything like that, in order to participate in the peer-to-peer network and in the blockchain, and that's an important property. So what we can do instead is we can make a weaker assumption. And I kind of want you to take a leap of faith with me here, that this weaker assumption is something that is going to be feasible. And I'm going to make this assumption here and later show you how this is actually accomplished. And what this weaker assumption is that we're going to assume that there is some ability somehow to pick a random node in the system. And a good motivating analogy for this is a lottery or a raffle or any number of real-life systems where tracking and verifying people and giving them identities and verifying those identities is pretty hard. And so what we do in those contexts is we might give them tokens or tickets or something of that sort, and that then enables us to later pick a random token ID and call upon that person. So we're going to do something similar with respect to these Bitcoin nodes and further assume for the moment that this token generation and distribution algorithm has enough smarts so that if the adversary is going to try to create a lot of Sybil nodes, together all of those Sybils just get one token, so the adversary is not able to multiply his power that way. So let's make this assumption for now, and let's see what becomes possible if we make this assumption. Here's the key idea. What becomes possible under this assumption of random node selection is something called implicit consensus. So what is implicit consensus? In each round, and there are going to be multiple rounds, each round corresponding to a different block in the blockchain. In each round, a random node is somehow selected, magically for the moment, and this node gets to propose the next block in the chain. There is no consensus algorithm, there is no voting. This node simply unilaterally proposes what the next block in the blockchain is going to be. But what if that node is malicious? Well, there is a process for this, but it is an implicit one. Other nodes will implicitly accept or reject that block. And how will they do that? If they accept that block, they will signal that acceptance by extending the blockchain starting from that block, or if they reject that block, they will extend the chain by ignoring that block and starting from whatever was the previous latest block in the blockchain. And technically, how is that implemented? Recall that each block contains a hash of the block that it extends, and this is the technical mechanism that allows nodes to signal which block it is that they're extending. So given this is what the overall consensus algorithm in Bitcoin is going to look like. Now, this is a little bit simplified, and the reason it's simplified is, again, that I'm assuming sort of this magic random node selection process. But except for that simplification, this is pretty close to how Bitcoin actually works. So whenever Alice wants to pay Bob, she will create a transaction, and she will broadcast it to all of the nodes. And any one of these nodes is constantly listening to the network and collecting a list of outstanding transactions that have not yet made it into the blockchain. At some point, one of these nodes is going to be randomly called upon to propose the next block. It's going to round up all of the outstanding transactions that it's heard about and propose that block. Now, presumably that node was honest, but it could also be a malicious node or a faulty node and propose a block that contains some invalid transactions. Invalid transactions are those that don't have the right crypto signature or where the transaction is already spent. In other words, an attempt to double spend. So if that happens, other nodes are going to signal their acceptance or rejection of the block, as we saw on the last slide, by either including the hash of this latest block in their next block, or ignoring this block and including the hash of whatever was the previous block that they considered to be valid. Right. So now let's try to understand why this consensus algorithm works. And the way I like to understand this is, instead of asking why this works, let's try to ask, how can a malicious adversary try to subvert this process? So let's look at that for a second. So here we have a couple of blocks in the blockchain. Assume that this extends to the left a long way back, all the way to what is called the genesis block. But here I'm only showing you a couple of blocks in the blockchain. And that pointer that you see over there is a block referring to what is the previous block that it extends by including a hash of that previous block within its own contents. So a malicious attacker, let's call her Alice. What might she try to do? Can she simply steal Bitcoins belonging to another user at a different address that she doesn't control? Now, even if it is now Alice's turn to propose the next block in this chain, she cannot steal other users' Bitcoins. Why? Because she cannot forge their signatures. So as long as the underlying crypto is solid, she's not able to simply steal Bitcoins. Another thing she might try to do is, if she really, really hates some other user, Bob, then she can look at Bob's address and she can decide that any transactions originating from Bob's address, she will simply not include them in any block that she proposes to get onto the blockchain. In other words, she's denying service to Bob. So this is a valid attack that she can try to mount. But luckily, it's nothing more than a little annoyance, because if Bob's block doesn't make it into the next block that Alice proposes, he will just wait another block until an honest node gets the chance to propose a block, and then his transaction will get into that block. So that's not really a good attack either. So the only one that we're really left with for what a malicious node can try to do here is called a double spending attack. So how might a double spending attack work? To understand that, let's assume that Alice is a customer of some online merchant or a website run by Bob, who provides some online service in exchange for payment in Bitcoins. Let's say he allows the download of some software. So here's how a double spending attack might work. Alice goes to Bob's website and decides to buy this item, pays for it with Bitcoins, and what that means in technical terms is that she's going to create a Bitcoin transaction from her address to Bob's address. She broadcasts it to the network, and let's say that some honest node creates the next block, listens to this transaction, and includes it in that block. So what is going on here? So there is this block that was created by an honest node that contains a transaction that represents a payment from Alice to the merchant Bob. By C subscript A, I mean a coin belonging to Alice, and that is now being sent to Bob's address. Let's zoom into this in a little bit more technical detail. A transaction, as we saw earlier, is a data structure that contains Alice's signature here and an instruction to pay to Bob's public key, and also a hash. What is this hash? This hash represents a pointer to the transaction where Alice in fact received that coin from somebody else, and that must be a pointer to a transaction that was included in some previous block in the consensus chain. So visually, it's going to look something like this. Let's pause for a second here because there's something subtle going on. There are at least two different types of pointers in this diagram that I've showed you. There's in fact a third one corresponding to Merkle trees, but we're not going to look at that at the present moment. But these two types of pointers that I refer to are blocks that include a hash of the previous block that they're extending, and transactions that include a pointer to whatever the previous transaction where the coin came from. Right, so this is the situation, and this block was now generated by an honest node. And now let's assume that the next time a random node is called, that node is a malicious node controlled by Alice. Right? So this is the blockchain as it stands right now. Bob has already looked at this blockchain, decided that Alice has paid him, and has allowed Alice to download the software or whatever it is that she was buying on his website. Right. So as far as Bob is concerned, he's satisfied, the transaction is completed. Alice has now received her goods in exchange for the payment. Now what might happen is if Alice now gets to propose the next block, she could propose a block that looks like this. Ignores altogether this valid block over here, and instead contains a pointer to the previous block. And furthermore, it's going to contain a transaction that contains a transfer of coins, of Alice's coins, to another address, A prime, that's also controlled by Alice. So this is a classic double spend pattern. What is going on here is Alice now creates a new transaction that transfers that coin, instead of to Bob's address, to another address owned by her. And visually, it's going to look like this. This is a completely different transaction, also with a hash pointer, going back to the same transaction referred to earlier. Right? So this is what an attempt at a double spend looked like. And how do we know if this double spend attempt is going to succeed or not? Well, that depends on whether this green transaction here or this red transaction is going to ultimately end up in the long-term consensus chain. So what determines that? That is determined by the fact that honest nodes are always following the policy of extending the longest valid branch. So now, which of these is the longest valid branch? You might look at this and say, aha, the first one is the longest valid branch, not the second one, because it's a double spend attempt. But here's a very subtle point that I want you to appreciate. From sort of a moral point of view, this transaction in green and the transaction in red might look very different because based on the explanation that I've given you, the first one is an attempt by Alice to pay Bob, whereas the second one is an attempt by Alice to defraud Bob and pay coins back to herself. But from a technological point of view, these two transactions are completely identical. The nodes that are looking at this really have no way to tell which one is the legitimate transaction. I'm putting legitimate in air quotes because it's a moral judgment that we apply to it. It's not a technical distinction. Versus which one is the attempted double spend. It could easily be the other way around. Now, nodes often follow a heuristic of extending the block that they first heard about on the peer-to-peer network, but it's not a solid rule, and in any case, because of network latency, that could easily be the other way around. So now there is at least some chance that the next node that gets to propose a block will extend this block instead of this one. Or it could be that even if it's an honest node, Alice could try to bribe that node or try to subvert the process in a variety of ways. So for whatever reason, without going too much into the details, let's say that the next node extends the block with the red transaction instead of the green one. What this means is that at this point, the next honest node is much more likely to extend this block instead of this one because now this has become the longest valid chain. So let's say that after one more block, the situation looks like this. Now it's starting to look pretty likely that this double spend has succeeded. In fact, what might happen is that this ends up the long-term consensus chain, and this block gets completely ignored by the network, and this is now called an orphan block, and this is an example of a successful double spend. So now let's look at this whole situation from Bob the merchant's point of view. And understanding how Bob can protect himself from this double spending attack is really going to be a key part of understanding Bitcoin security. So let's look at what happened here again. We have a couple of blocks in the blockchain. And at this point, Alice broadcasts a transaction that represents her payment to Bob. And so Bob is going to hear about it on the peer-to-peer network right here, even before the next block gets created. And so Bob can do something even more foolhardy than what he did in the previous slide, which is that as soon as he hears about the transaction on the peer-to-peer network, he can complete the transaction on the website and allow Alice to download whatever she's downloading. That's called a zero confirmation transaction. Or he could wait until the transaction gets one confirmation in the blockchain, which means that at least some node has created a block and has proposed this transaction, and that has gone into the blockchain. But as we saw earlier, even after one confirmation, there could be an attempt at a double spend. So let's say that this actually happens. If, as in the previous slide, the double spend attempt succeeds, what Bob should do is to realize that the block that he thought represented Alice paying him has now been orphaned, and so he should abandon the transaction. Instead, if it so happens that despite this double spend attempt, the next block that's generated turns out to extend the block that he's interested in. Now he sees that his transaction has two confirmations in the blockchain. Now he gets a little bit more confidence that his transaction is going to end up on the long-term consensus chain. So let's say there's one more, and now there are three confirmations. In general, the more confirmations your transaction gets, the higher the probability that it is going to end up on the long-term consensus chain, because if you recall the honest node's behavior, that they will always extend the longest valid branch that they see, the chance that this one is going to catch up to this longer branch is now very minuscule, especially if only a minority of the nodes are malicious. Right? Because typically, the only reason that this double spend attempt block would be extended at this point is if the next node to be picked randomly was a malicious node, and then you'd need another malicious node and then another for the shorter branch to then become the longer branch. In general, the double spend probability decreases exponentially with the number of confirmations. So if the transaction you're interested in has received k confirmations, then the probability that this other transaction is going to end up on the long-term consensus chain goes down exponentially as a function of k. And the most common heuristic that's used in the Bitcoin ecosystem is that you wait for 6 confirmations. There is nothing really special about the number 6. It's just a good trade-off between the amount of time you have to wait and your guarantee that the transaction you're interested in ends up on the consensus blockchain. So let's recap what we saw here. Protection against invalid transactions, that is, protection against a malicious node simply making up a transaction to steal someone's bitcoins, is entirely cryptographic, but it is enforced by consensus, which means that if a node does attempt that, then the only reason that that transaction won't end up in the long-term consensus chain is because a majority of the nodes are honest and will treat that transaction as invalid. On the other hand, protection against double spending is purely by consensus. Cryptography has nothing to say about this, and true transactions that represent a double spending attempt kind of look identical from the perspective of signatures and so on, but it's the consensus that determines which one will end up on the long-term consensus chain. And finally, you're never 100% sure that a transaction you're interested in is on the consensus branch, but this exponential probability guarantee is pretty good. After about 6 transactions, there's virtually no chance that, that you're going to go wrong. So in the previous section, we got a basic look at Bitcoin's consensus algorithm and a good intuition for why we believe that it's secure. But recall that at the beginning of the lecture, I told you that Bitcoin's decentralization is partly a technical mechanism and partly clever incentive engineering. So far, we've mostly looked at the technical mechanism. Now let's talk about the incentive engineering that happens in Bitcoin. I asked you to take a leap of faith with me earlier in assuming that we're able to pick a random node, and perhaps more problematically, that at least 50% of the time this process will pick an honest node. But of course, this assumption of honesty is quite problematic, especially if there are financial incentives for participants to subvert this. Then why would we expect any node to be honest, really? So what we want to ask is, can we give nodes an incentive for behaving honestly? Let's look at this with respect to the picture we've been looking at. This is the long-term consensus chain, and this block contains an attempt to double spend. We can ask, can we penalize somehow the node that created this block? But this is problematic for a number of reasons, including the fact that nodes don't have identities, and so there's no way to go after them to penalize them. So instead, let's flip the question around and ask, can we reward the nodes that created all these blocks that did end up on the long-term consensus chain? Well, again, sort of the same problem. We don't have node identities, so we can't mail them cash to their home addresses. If only there were some sort of digital currency that we can use to incentivize them, a decentralized one perhaps. You probably see where I'm getting at. In other words, we're going to use bitcoins in order to incentivize the nodes that created these blocks. So how are we going to do that? Well, so far, everything that I've said is just an abstract algorithm for achieving distributed consensus. Now we're going to break out of that model. What I'm going to say now is specific to the fact that what we're achieving through this distributed consensus process is in fact a currency. And we're going to incentivize these nodes by paying them in units of this currency. So how do we do that? There are in fact two separate incentive mechanisms in Bitcoin, and the first one is called the block reward. So what is the block reward? It's just this. According to the rules of Bitcoin, the node that creates each block gets to include a special transaction in that block, and that special transaction is a coin creation transaction. And this node can also choose the recipient address of this transaction. So of course that node will typically choose an address belonging to itself as the recipient of this coin creation transaction, thereby paying itself. It's sort of, you can think of it as a payment in exchange for the service of creating that block to go onto the consensus chain. In fact, the value of this coin creation transaction has an interesting property. It's currently fixed at 25 bitcoins, but it actually halves every 4 years. We're now in the second period. For the first 4 years of Bitcoin's existence, it was 50 bitcoins. Now it's 25, and it's going to keep halving. This has some interesting consequences. We'll come back to that in the next slide. But let me ask you this. It appears, based on what I've said here, that this node gets the block reward regardless of whether it proposes a block with only valid transactions or it behaves maliciously. So how are we actually providing any incentives for honest behavior via this block reward? But think about this. Well, how will this node sort of get to collect its reward? That will only happen if this block ends up on the long-term consensus branch, because that's the only case in which this coin creation transaction will be considered valid, because the coin creation transaction is not special. It's just like every other transaction. It's only valid if it ends up on the consensus chain. So that's the incentive mechanism here. It's very subtle, but it's a very neat trick. And so it incentivizes nodes to behave honestly, or at the very minimum, it incentivizes nodes to behave in a way that they think other nodes are going to agree with in creating the next blocks of the blockchain. So that's the first incentive mechanism. Let's come back to this point now, this weird sort of halving phenomenon that we see here. And this can be best illustrated graphically. Here I'm going to show you a graph of time on the x-axis versus the total number of bitcoins in circulation. And this over here was the first period where each block resulted in 50 new bitcoins being created. And roughly at the end of last year, that block reward halved from 50 to 25. And you can see that every 4 years, extending well into the future, the slope of this curve is going to keep halving. And this is a geometric series, and you might know that it means that there is a finite sum. And in fact, there is a total finite supply of bitcoins. And if you add up all these numbers, it works out to 21 million based on the rate of new block creation, which I'm going to get to in a second. Also worth noting is that this is the only way in which new bitcoins are created. There is no other coin generation mechanism, and that's why this is a final and total number, as the rules stand now at least, for how many bitcoins there can ever be. And this new block creation reward is actually going to run out. So that sounds a bit weird. Does that mean that the system will stop working and become insecure because nodes no longer have the incentive to behave honestly? Well, not quite, because this is only the first of two incentive mechanisms. There is quite another incentive mechanism called the transaction fee. And what is a transaction fee? So the creator of any transaction, not the creator of a block, but the creator of a transaction, when Alice is paying Bob, what she can do is she can choose to make the output value of that coin less than the input value. And the way that all the nodes interpret this difference, according to the rules of Bitcoin, is that it's a transaction fee And whoever creates the block that first puts that transaction into the blockchain gets to collect that transaction fee. So if you're a node that's creating a block that contains, say, 200 transactions, then the sum of all those 200 transaction fees accrues to you and to the address that you put into that block. Of course, this transaction fee is purely voluntary, like a tip, but we expect, based on our understanding of the system, that as the block reward starts to run out, it'll become more and more important, almost mandatory, for nodes to put a transaction fee into their transactions in order to get a reasonable quality of service. And to a certain degree, this is already starting to happen now. But precisely how the system will evolve, it really depends on a lot of game theory, which hasn't been fully worked out yet. So that's an interesting area of open research in Bitcoin. So now we've acquired an understanding of how the nodes that create these blocks are incentivized to act honestly or follow the protocol. And so if we address a few more of these remaining problems, we'll be all set to have a really good understanding of how Bitcoin achieves decentralization. What are these remaining problems? Well, one of them, the first major one, is the leap of faith that I asked you to take, which is that somehow we can pick a random node. And the second is that we've created a new problem by giving nodes these block rewards and incentives, which is that you could easily get into a free-for-all where everybody wants to run a Bitcoin node in the hope of capturing some of these rewards. And a third one is an even trickier version of this problem, which is that an adversary might create a whole different number of Sybil nodes in order to really try to subvert this consensus process. So number 3 is sort of a trickier version of number 2. It turns out that all of these problems are related, and all of them have the same solution. And that solution is called proof of work. So what is proof of work? Here's the key idea. Instead of picking a random node, we do something a little bit different, which is we approximate selecting a random node by instead selecting nodes in proportion to a resource that we hope that nobody can monopolize. What does that mean? Well, if that resource that we're talking about is computing power, then it's a proof of work system where we somehow select nodes in proportion to their computing power. Alternately, it could be in proportion to ownership of the currency, and this is a legitimate alternate model. It's not used in Bitcoin, but it's been proposed and it's used in a lot of alternatives to Bitcoin, and that's called proof of stake, which we'll see in a later lecture. But let's come back to proof of work. Let's try to get a better idea of what this means. Selecting nodes in proportion to their computing power, another way to understand this is that we're allowing nodes to compete with each other by using their computing power. And that will result in nodes automatically being picked in that proportion. So those are two equivalent ways to view proof of work. You can also think of a third way, which is that we're making it moderately hard through proof of work to create new identities. So it's sort of a tax on identity creation and on the Sybil attack. This may all appear a bit vague, so let me actually go ahead and show you what is the exact proof of work system that's used in Bitcoin, and that's going to make things a lot clearer. So here it is. It's called hash puzzles, and what this means is that in order to create a block, the node that proposes that block is required to find a number, a nonce, such that when you put together in the block the nonce, the previous hash, and the list of transactions that comprise that block, and take the hash of this whole long string, then that hash output should be a number that is very small, that falls into this small target space here in relation to this very large space that is the output space of that hash function. Let's look at it one more time. As we looked at it earlier, normally a block contains a series of transactions that you're proposing. In addition, a block also contains a pointer to the previous block, as we saw, and a pointer is just a string in this context. But in addition here, we're requiring that a block also contain a nonce. And why is this? And the idea is that we want to make it moderately difficult to, in fact, find a nonce that satisfies this required property, which is that hashing the whole block together, including that nonce, is going to result in a particular type of output. And so we believe that if the hash function is secure, then the only way to succeed in solving this hash puzzle is to just try enough nonces one by one until you get lucky. So specifically, if this target space were just 1% of the overall output space, you would have to try about 100 nonces before you got lucky. And if this hash function were to behave essentially randomly, only 1 in 100 nonces will result in an output that falls within this target space. In fact, the size of this target space is not nearly as high as 1% of the output space. It's much, much smaller than that, which we'll get to in a second. But fundamentally, this is the computational problem that a node is required to solve in order to produce the block. Now, this notion of hash puzzles and proof of work completely does away with the requirement for somebody somehow to pick a random node. Instead, nodes are simply all the time independently competing to solve these hash puzzles. And once in a while, one of them will get lucky and will find a random nonce that satisfies this property. And that node then gets to propose the next block. That's how it's completely decentralized. There is nobody deciding which node it is that gets to propose the next block. So let's look at it in a little bit more detail now. There are 3 properties that I want to show you, essential properties of this proof of work function, of this hash puzzle. And the first is that it needs to be quite difficult to compute. I said moderately difficult, but what I mean by moderately difficult, as of today, and you'll see why it varies with time, it's about 10 to the 20 hashes per block that you need to compute. So the size of the target space is only 1 over 10 to the 20 of the size of the output space of this hash function. Right, so if you look at it in terms of the amount of computing that your laptop needs to do, for example, this is simply a humongous and infeasible number. And because of this, only some nodes even bother to compete in this block creation process. And this is what is known as Bitcoin mining, basically the process of repeatedly trying and solving these hash puzzles. And we call these nodes miners. And because of how capital intensive this process is, this goes back to what I said at the beginning, that even though technically anybody can be a miner, there's been a lot of concentration of power or concentration of participation in the mining ecosystem. So that's the first property of these proof of work puzzles. The second property is that we want this cost to be parameterizable. It's not a cost that is fixed over all time. And the way that that's accomplished is that all the nodes in the Bitcoin peer-to-peer network will automatically recalculate the target, that is the size of the target space as a fraction of the output space, every 2 weeks. And they do it in such a way that they maintain this invariant, which is that the average time between any 2 successive blocks produced globally in the overall Bitcoin network is about 10 minutes. So let's think about what this means. What this means is that if you're a miner and you've invested a certain fixed amount of hardware into Bitcoin mining, but the overall mining ecosystem is growing, more miners are coming in or they're deploying faster and faster hardware, that means that over a 2-week period, slightly more blocks are going to be found than expected. And so nodes will automatically readjust the target. And so the amount of work that you have to do to be able to find a block is going to increase. So if you put in a fixed amount of hardware investment, the rate at which you find blocks is actually dependent upon what other miners are doing. So there's a very nice formula to capture this, which is that the probability that any given miner Alice is going to win the next block is equivalent to the fraction of global hash power that she controls. Which means that if she has mining hardware that's about 0.1% of total hash power, she will compute roughly 1 in every 1,000 blocks. So why does this readjustment happen? Why do we want to maintain this 10-minute invariant? Well, the reason is simple. If blocks were to come very close together, then there would be a lot of inefficiency and we would lose the optimization benefits of being able to put a lot of transactions, as it currently stands, several hundred transactions in a single block. If you went down from 10 minutes to 5 minutes, it would probably be okay. And there are a lot of discussions about if we're doing an altcoin now, what is the block latency that we should have? But everybody agrees that the block latency should be a fixed amount. It cannot be allowed to go down without limit. And that's why you have this automatic target recalculation property. Now, because of the way that this cost function and proof of work is set up, it allows us to reformulate our security assumption. Here's where we finally depart from the leap of faith that I asked you to take several slides ago. Instead of saying that somehow the majority of nodes are honest, in a context where nodes don't even have identities and not being clear about what that means, we can now state crisply that a lot of attacks on Bitcoin are infeasible if the majority of miners weighted by hash power are following the protocol or are honest. And the reason for that is if a majority of miners weighted by hash power are honest, because of this competition for proposing the next block, this will automatically ensure that there is at least a 50% chance that the next block to be proposed at any point is coming from an honest node instead of a malicious one. Let's now look at the consequences of the fact that solving hash puzzles is probabilistic. Why is it probabilistic? Because nobody can predict which nonce is going to result in solving the hash puzzle. The only way to do it is to try nonces one by one and hope that one succeeds, right? And so this process is called mathematically Bernoulli trials. I won't go into detail on that, but you can look it up. But typically nodes try so many nonces that a discrete probability process called Bernoulli trials can be well approximated by a continuous probability process called a Poisson process. And the end result of all of that is that the distribution, the probability density function of the time to find the next block by any node in the network globally looks something like this. It's called an exponential distribution, but really the upshot is that there is some small probability that if a block has been found now, the next block is going to be found very soon or within a few seconds or within a minute. And there's also some small probability that it will take a long time, maybe an hour, to find the next block. But overall, the network automatically adjusts the difficulty so that the interblock time is maintained at an average long term of 10 minutes. Right. So this is a graph that shows how frequently blocks are going to be created by the entire network, not caring about which miner this is coming from. If you're a miner specifically interested in how quickly you're finding blocks, what does this probability density function look like? Well, it's going to have the same shape, but it's just going to have a different scale on the x-axis. Again, it can be represented by a nice equation. For a specific miner, the mean time to find a block, given that you've just found a block, is going to be 10 minutes divided by the fraction of hash power that you control. So again, if you have 0.1% of the total network hash power, you're going to find blocks once every 10,000 minutes, which is several days. And so not only is your mean time between blocks going to be very high, the variance of the time between blocks found by you is also going to be very high. And this has some important consequences that we're going to be looking at in later lectures. So now let's turn to the third important probability of this proof of work function, which is that it's actually trivial to verify that a node has computed proof of work correctly. What does that mean? Even if it takes a node on average 10 to the 20 tries to find a nonce that succeeds in finding the right property of the hash function, that nonce must be published as part of the block, so it's trivial for any other node to look at the block contents, hash them all together, and verify that the output is less than the target. So this is an important property because, once again, it allows you to get rid of centralization. You don't need any centralized authority verifying that miners are doing their job correctly. Any node or any miner can instantly verify that a block found by another miner satisfies this proof of work property, and thereby they can be sure that this miner put in a lot of computing power into finding that block. Let's now look at mining economics, because we've said that it's quite expensive for miners to be in operation because finding a single block takes computing about 10 to the 20 hashes. At the same time, we've also seen that the block reward is about 25 bitcoins, which is quite a lot of money. So it really boils down to an economics question of whether or not it's profitable for a miner to mine. But we can write down a simple equation that represents what the inputs into this decision are. Fundamentally, the mining reward that the miner gets is in terms of the block reward and transaction fees. The miner asks himself whether that's bigger than or less than their total expenditure, which is the hardware and electricity cost. In fact, Bitcoin mining is so expensive in terms of electricity that that becomes a significant portion of the cost and not just the upfront cost of the hardware. And if the rewards are greater than the costs, then the miner profits. If not, the miner incurs a loss. But there are some complications to this simple equation. The first is that, as you may have noticed, the hardware cost is a fixed cost. It's an upfront cost. whereas the electricity cost is a variable cost that is incurred over time. Another complication is that remember that a reward that the miner gets depends upon the rate at which they find blocks, which depends on not just the power of their hardware, but in fact, more accurately, as the ratio of the power of their hardware as a fraction of the total global hash rate. So that makes it more complicated as well. Another complication is note that the costs that the miner incurs are in terms of dollars or whatever currency that they're using, whereas they're rewarded in terms of bitcoins that are created or bitcoins that are transaction fees. So this equation is really going to depend on what the exchange rate of Bitcoin is doing at any given time. And finally, so far we've assumed that the miner is interested in honestly following the protocol, but it could be the case that the miner could deploy some other mining strategy instead of always finding the next block that extends the longest valid branch. And so this equation doesn't capture all the nuances of the different strategies that the miner can employ. So even though we can write down the simple equation, actually analyzing what it makes sense for miners to do is a complicated game theory problem, and we don't have simple answers to that. Okay, so now we've obtained a pretty good understanding of how Bitcoin achieves decentralization. Let's put it all together now and do a little bit of a recap and understand some high-level points in order to get an even better understanding. So what I'm going to do is I'm going to do a very quick recap of several of the major aspects of Bitcoin that we've learned so far. Let's start from identities. As we've learned, there are no real-world identities required to participate in the Bitcoin protocol. Any user can create a pseudonymous key pair at any moment, any number of them. And when Alice and Bob want to make a transaction, when Alice, for example, wants to know what address Bob wants to get paid at, that's not part of the Bitcoin protocol. That needs to be through some other process, for example, on Bob the merchant's website. So given these pseudonymous key pairs as identities, transactions are basically messages that are broadcast to the Bitcoin peer-to-peer network that are instructions to transfer a coin from one address to another. And a coin really is just a chain of transactions to the extent that we can call anything in Bitcoin an actual coin, and this is something we'll see in much more detail in future lectures. And so this peer-to-peer network that we've looked at, its goal is to propagate all new transactions to all the Bitcoin peer nodes, as well as new blocks to the Bitcoin peer nodes, but it's just going to do sort of the best effort that it can. The real security of the system doesn't come from the perfection of the peer-to-peer network. In fact, the underlying assumption that the network is in fact quite unreliable. But instead, where the security comes from is from the blockchain and the consensus protocol that we spent a lot of time looking at. So what it means for your transaction to be in the blockchain is that it achieves a lot of confirmations. It's not a fixed number. 6 is a commonly used heuristic, but the more confirmations your transaction has received, the more blocks are found that extend the block that contained your transaction, the more certain you can be that your transaction was part of the consensus chain. And now, often there are going to be a variety of orphan blocks. These are blocks that don't make it into the consensus chain. This could represent an invalid transaction or a double spend attempt. It could simply represent the fact that there is latency in the network, and two miners competing to solve this proof of work puzzle simply ended up finding new blocks within just a few seconds of each other, and so both of these blocks were broadcast nearly simultaneously onto the network. So another subtle point here is that if Alice and Bob are two different miners, and Alice has 100 times as much computing power as Bob, what that means is not that Alice will always win the race against Bob to find the next block, but instead, Alice and Bob have a ratio, a probability ratio of finding the next block in the proportion 100 to 1. So in the long term, Bob will find, on average, 1% of the blocks that Alice does. So those are some of the basics of blockchain and consensus and where the security of the system really comes from. And finally, we looked at hash puzzles and mining. Miners are a special type of nodes that bother to compete in this game of creating new blocks, and they're rewarded for their efforts in terms of bitcoins. And we expect that miners are going to be typically somewhere near the economic equilibrium of the expenditure that they incur in terms of hardware and electricity being somewhere equal to the rewards that they obtain in terms of the new block creation reward and the transaction fee-based rewards. So that's a broad recap of the system. Let me show you in a pointed way how deeply this notion of distributed consensus permeates Bitcoin. Now, in a traditional currency, consensus does come into play in a certain limited extent, which is we have a consensus process around what is the exchange rate of the currency. You can make a rough analogy to consensus in distributed systems. And that is certainly true in Bitcoin as well. We need consensus around the value, the exchange rate of Bitcoin, but consensus goes much deeper in Bitcoin than in other, say, fiat currencies. In fact, you need consensus around state, which is what the blockchain accomplishes, that is a record of which transactions are valid or which transactions have even happened. So even the idea of how many Bitcoins you own is subject to consensus. What it means when I say I own a certain amount or number of Bitcoins is that I mean that the Bitcoin peer-to-peer network, as recorded in the blockchain, considers me, the sum total of all my addresses, to own a certain number of Bitcoins. That is sort of the ultimate nature of truth in Bitcoin. So ownership of Bitcoins is nothing more than other nodes thinking that I own a certain number of Bitcoins. And finally, we need consensus about the rules of the system, because occasionally the rules of the system have to change. There are things called soft forks and hard forks, and we're going to see a little bit more detail of this in later lectures. Now, I want to show you another subtle idea, which is very tricky, and it's this very neat idea of bootstrapping that I really found intriguing the first time I encountered it, and so I want to share this with you. So what do I mean by bootstrapping? I mean the tricky interplay between three things in Bitcoin. And what are these three things? Let's start from the notion of security of the blockchain. So obviously we want the blockchain to be secure for Bitcoin to have to be a viable currency. But what is necessary for the blockchain to be secure? What this means is that an adversary shouldn't be able to overwhelm the consensus process. Shouldn't be able to create a lot of nodes and take over 50% or more of the new block creation. But when will that be true? What is a prerequisite for that? A prerequisite for that is having a healthy mining ecosystem made up of largely honest protocol-following nodes. So that's a prerequisite for security of the blockchain. But what's a prerequisite for that? When can we be sure that a lot of miners will put a lot of computing power into participating in this hash puzzle solving competition? Well, they're only going to do that if the exchange rate of Bitcoin is pretty high. Why is that? Because they receive rewards denominated in Bitcoins, whereas their expenditure is in dollars. So the more the value of the currency goes up, the more incentivized these miners are going to be. But what ensures a high and stable value of the currency? That can only happen if users in general, people who want to buy Bitcoins, have trust in the security of the blockchain. Because if they believe that the network could be overwhelmed at any moment by an attacker, then Bitcoin is not going to have a lot of value as a currency. So you have this interlocking interdependence between these three things. Right? So the existence of each of these is predicated on the existence of another. So one might flip that around and imagine at the beginning, during Bitcoin's creation, when none of these three things existed, when there were no miners other than what we believe to be Nakamoto himself or whoever the creator was running the mining software. And when Bitcoin didn't have a lot of value as a currency. And when the blockchain was in fact insecure because there was not a lot of mining going on, and so anybody could easily overwhelm this process. How do you go from there, not having any of these three properties, to having all three of them? And that is what I mean by bootstrapping. And it's this very tricky process of how all of these three characteristics were acquired by the Bitcoin system in an interdependent manner with each other. And this was, of course, fueled by a lot of media attention as well, because the more people hear about Bitcoin, the more they're going to get interested in mining. And the more they get interested in mining, the more confidence people will have in the security of the blockchain, because there's now more mining activity going on, and so on and so forth. And so Bitcoin went from having none of these properties to now having, in some large measure, all three of these properties. And that's the interesting bootstrapping feature of Bitcoin. And every new altcoin that wants to succeed also has to somehow solve this problem of pulling itself up by its bootstraps. Okay. Let me leave you now with one final thing, which is that in order to understand consensus and what it's responsible for and what it's not responsible for, a good way to do that is to ask ourselves what would happen if consensus failed and there were in fact a 51% attacker somehow who controls 51% or more of the mining power in the Bitcoin network. So let's see what happens in that case, and let's list a whole variety of things, possible bad things that we think might happen, and let's ask ourselves which of these are possible for a 51% attacker. First of all, can this attacker steal coins from an existing address? Well, you might guess that the answer is no, because stealing from an existing address is not possible unless you subvert the cryptography. It's not enough to subvert the consensus process. This is a bit tricky. Let's follow through this line of argument. Let's say that this 51% attacker creates an invalid block that contains an invalid transaction that represents stealing bitcoins from an existing address that the attacker doesn't control and transferring them to his own address. Now this attacker can pretend that that's a valid transaction and pretend that that's a valid block and keep building upon this block and even succeed in making that the longest branch, but the other honest nodes are simply not going to accept this invalid block and are going to keep mining based on the last valid block that they found in the network. So what will happen is that there will be what we call a fork in the chain. Now imagine this from the point of view of the attacker trying to spend these invalid coins and send them to some merchant Bob and buy something in exchange. Now Bob will presumably be running a Bitcoin node himself, and that will be an honest node, and that node is going to say, oh, this might be the longest branch, but it's not a valid branch because it contains an invalid transaction because the signatures didn't check out. And so it's going to simply ignore this longest branch because it's an invalid branch. And because of that, subverting consensus is not enough. You have to subvert cryptography to steal coins from an existing address. So we conclude that this attack is not possible for a 51% attacker. By the way, in saying all of this, I should note that this is all somewhat hypothetical, somewhat a thought experiment, because if there were, in fact, actual signs of a 51% attack, what will probably happen is that the developers will notice this and will try to react to it, and we'll update the Bitcoin software, and we might expect that the rules of the system of the P2P network might change in some form to make this attack more difficult to launch, but we can't quite predict that, so we're working in a simplified model where a 51% attack happens, but other than that, there are no changes or tweaks to the rules of the system. Okay, let's move on. Can the attacker suppress some transactions? Let's say there is some user, say Carol, whom the attacker really doesn't like, and the attacker knows some of Carol's addresses and wants to make sure that no coins belonging to any of those addresses can possibly be spent. Is that possible? Well, let's think about this. The attacker, since he controls the consensus process of the blockchain, can simply refuse to create any new blocks that contain transactions from one of Carol's addresses, and can in fact also refuse to build upon blocks that contain such transactions. And the attacker will be successful at that. However, the attacker cannot prevent these transactions from even being broadcast to the peer-to-peer network, because the peer-to-peer network doesn't depend on the blockchain, doesn't depend on consensus, and we're assuming that the attacker doesn't fully control the network. So the transactions are still going to find a way to reach the majority of nodes. So even if the attacker tries this attack, it will be very clear that that attack is happening because the peer-to-peer network will still receive these transactions. Okay, what about this one? Can the attacker change the block reward? Can the attacker start pretending that the block reward is, instead of 25 bitcoins, 100 bitcoins or something like that? Well, this sort of corresponds to changing the rules of the system, and because of a reasoning similar to what we applied for stealing bitcoins from an existing address, this is also not possible because the attacker doesn't control the copies of the Bitcoin software that all of the honest nodes are running. So that's also not possible. Finally, let's ask ourselves if the attacker can somehow destroy confidence in Bitcoin. Well, let's imagine what would happen if there were a variety of double spend attempts and a behavior of not extending the longest valid branch and other such attempted attacks. Then people are going to look at this and decide that Bitcoin is no longer acting as a decentralized ledger that they can trust. And so people will simply lose confidence in the currency, and we might expect that the exchange rate of Bitcoin is going to plummet. In fact, if there is a 51% attacker, and this is known, even if the attacker is not necessarily trying to launch any attacks, it's possible that this might happen. So this we can classify as not only possible, but in fact likely that a 51% attack of any sort will simply destroy confidence in the currency. And this last one is in fact the main practical threat if a 51% attack were ever to materialize. None of these others really, considering the amount of expenditure that the adversary would have to put into attacking Bitcoin and achieving a 51% majority, really makes sense from a financial point of view to try any of these other attacks. Great. So now, hopefully, you've obtained a really good understanding of how decentralization is achieved in Bitcoin, and understood identities, understood transactions, understood the peer-to-peer network, understood the blockchain and consensus, understood hash puzzles and mining. So you should be at a really good point now, and a good launching point for understanding a lot more of the subtle details and nuances of Bitcoin, which we're going to start seeing in the next few lectures. So the next lecture is going to be by Joe Bonneau, where he will address a lot of questions that take off from the point where we've left off in this lecture. The first is, how do we get from consensus to currency? So this is an assumption that I've already made in this lecture. Not only are we solving a distributed consensus problem, but also we're treating the result of distributed consensus as a currency in order to incentivize participants. But a lot of details are missing. What exactly does it mean to be paid in Bitcoin? How does that happen? How are those transactions represented, and so on? We're going to look at that. We're going to look at what else can we do with consensus. I hinted at this a little bit, but it turns out that Bitcoin offers a lot in addition to just doing consensus. It has a whole scripting language, so there are a lot of interesting things to see there. And so Joe is going to take it from there in the next lecture. Thank you.
Welcome to the third lecture in our series on Bitcoin. This lecture is going to be all about the mechanics of Bitcoin at a fairly low level. So whereas in the first two lectures we've talked at a relatively high level, in this lecture we're going to be trying to give it to you as real as possible. So look at real data structures, real scripts, try to learn the details and language of Bitcoin in a precise way to set up everything that we want to talk about for the remainder of the course. So in some ways this will be the most challenging lecture because a lot of details are going to be flying at you. It's also one of the most real where you're really learning the specifics and the quirks that make Bitcoin what it is. So to recap where we left off last time, the Bitcoin consensus mechanism gives us an append-only ledger. So a data structure that we can only write to, and once data is written, it's there forever. And there's a decentralized protocol for establishing consensus about the value of that ledger. And the miners who perform that protocol are validating transactions, so making sure that transactions are well formed, that there aren't double spends, and that this thing can function as a currency. Although it's kind of funny because we assumed that a currency existed to motivate these miners. So in this lecture we'll be looking at the details of how we actually build that currency to make the miners make this whole process happen. All right, so we'll start by looking at transactions in Bitcoin. Transactions are really the fundamental building block which the whole currency is going to be based on. So remember, we have this ledger. The ledger is append only, so as time goes on we just add more and more units to it. We're going to take a simplified model here where instead of having blocks we just have individual transactions being added to the ledger one at a time. So how can we build a currency this way? So the first model you might think of, which is actually a lot of people's mental model for how Bitcoin works that we'll look at first, is that you'd have an account-based system. So you can add some transactions that create new coins and credit them to somebody. And then later you can transfer them and you just have a transaction that would say, we're moving 17 coins from Alice to Bob. That will be signed by Alice to authorize the transaction. And that's all the information that would be contained. Now backing this up, there would be some state that says that after Alice received 25 coins in the first transaction and then transferred 17 coins to Bob in the second transaction, Alice would have an account that is left with 8 Bitcoins. So now after that transfer from Alice to Bob, we can add some more transactions to the ledger. We'll say that Bob pays some Bitcoins to Charlie, Charlie pays some coins to Alice. And at this point, each participant, Alice, Bob, and Charlie, has an account with a different value in it, and those values are going to mutate each time we add a new transaction. Now the downside of this system, if we add a new transaction at the bottom here, is that we have to remember what the account balance is for each participant to figure out if this transaction is valid or not. Does Alice have the 15 coins that she's trying to transfer to David here? So sure enough, looking at this just with your naked eye, it's fairly hard to tell to do the mental arithmetic to figure out if Alice has enough money to transfer to David here. And in fact, to figure this out, you'd have to look backwards in time forever to see every transaction affecting Alice and whether or not her net balance at the time that she tries to transfer 15 coins to David is greater than 15 coins. Okay, so to tell if this transaction is valid or not, we have to figure out whether or not Alice has the 15 coins that she's trying to transfer to David. And to figure that out, we might have to look backwards forever to the beginning of time at every transaction that's ever involved Alice. Every time Alice has sent or received coins, we need to find all of those transactions and add them up to see if she really has the 15 coins that she's trying to transfer to David. And of course, we can make this a little bit more efficient with some data structures that track Alice's balance after each transaction, but that's going to require a lot of extra housekeeping besides the blockchain itself. And that's why Bitcoin isn't based on an account-based model like this. Instead, Bitcoin uses a ledger that just keeps track of transactions. So how does that work? So this is a transaction-based ledger, which is very close to Bitcoin. So now transactions explicitly specify a number of inputs and a number of outputs. And transactions also each have a unique identifier. So we'll start with transaction 1, which has no inputs, because this is new currency being created, and an output of 25 coins going to Alice. And again, since this is a transaction where new coins are being created, there's no signature required here. Now, let's say that Alice wants to send some of those coins over to Bob. Well, now she has to explicitly refer to the previous transaction where these coins are coming from. So the input to this transaction will be output index 0 from transaction 1, which we can see from the very previous transaction in the log was a transaction that assigned 25 bitcoins to Alice. And now there are two outputs of this transaction. One of them is 17 coins to Bob, and one of them is 8 coins to Alice. And of course, this whole thing is signed by Alice so that we know that Alice actually wants to do this transaction. And now you might ask, why does Alice have to send money to herself here? She's taken the 25 coins that were assigned to her in transaction 1. She only wanted to pay 17 to Bob, and she has to have a new output where 8 coins are sent back to herself, possibly to a different key, but to herself. So this is what's called a change address. And the design here is that you always completely consume the output of a previous transaction. So there's no way to say I only need 17 coins from that previous output. You have to say I'm using all 25 coins from the previous output, but since you want to keep some, you just have a second output that sends some of the coins back to yourself, which is called a change address. Now, let's say that we keep going with this system, and now we add a new transaction, and we ask ourselves again, is this new transaction valid? Now it's much easier to look at the blockchain and figure out whether or not this transaction is valid, because we know exactly which input to look at. So we just need to go to transaction 2, output 1, and verify that there's enough money there and that it hasn't been sent already. And of course, we can look back and say, yes, that second output of transaction 2 went to Alice with 8 coins, therefore it's enough to cover the outputs of this transaction. It's a finite backward scan to check for the validity. And we implement this with hash pointers. So again, each transaction has a unique ID. In reality, they're not serial numbers like this, it's the hash of the block. And each transaction actually gets its specific ID as well, which is the hash of the transaction. And now it's basically just following one pointer to figure out whether or not there's enough money to cover the desired outputs in the new transaction. Now conceptually you could say maybe this isn't that much different than just maintaining a separate data structure which tracked account values for each person, but the nice thing is that now this data structure is embedded within the data in the blockchain itself. So some other things that we can do quite easily here, we can merge value. So let's say there's two different transactions that send some money to Bob, 17 coins in transaction 1 and 2 coins in transaction 2. Bob might say, I'd like to have one transaction I can spend later where I have all 19 coins. So this is pretty easy. You just create a new transaction that has 2 inputs now and only 1 output, so all of those coins go to Bob. And you've combined the 2 previous transactions into one that Bob can then spend later. Similarly, we can do joint payments pretty easily. So let's say that Carol and Bob both want to pay David. We can have a transaction with 2 inputs that are actually owned by 2 different people and combine the value and pay all 8 coins to David. And the only extra thing here is that since the 2 outputs that are being claimed here are owned by 2 different people, we're going to need 2 separate signatures, one by Carol and one by Bob. So conceptually, that's really all there is to it, to a Bitcoin transaction. And let's look at what it looks like at the low level. So again, one of the goals of this lecture is going to be to show you the real data structure, the real deal of what Bitcoin looks like. And here it is. Now, this isn't exactly what a Bitcoin transaction looks like. This is a representation of it that is pretty printed. It looks kind of like JSON. In reality, there's a compact binary format that this gets compiled down to that's not human readable, but this is very, very close to the actual low-level transaction. So there's 3 parts. There's some metadata, there's a series of inputs, and a series of outputs. So we'll start with the metadata. So there's some housekeeping information, which is the size of the transaction, the number of inputs, and the number of outputs. Pretty straightforward stuff. There's the hash of the entire transaction, which, as I said, will serve as a unique ID for the transaction to let us do hash pointers. And then there's this funny lock time parameter, which I'll come back to later. The transaction inputs is just an array of inputs that all have the same form. The inputs specify a previous transaction specifically, so they have the hash of the previous transaction or a hash pointer to it, and the index of which output from that transaction you're actually claiming. And then there's a signature. So remember that we have to sign to show that we actually have the ability to claim those previous transaction outputs. And now the outputs have just 2 things. They have a value, so each output can have a different value. The sum of all the outputs has to be less than the sum of all the inputs. And then there's this funny thing that looks like what we want to be the recipient address. So each output is supposed to go to a specific person or to a specific public key. And there is some stuff in there that looks like it's the hash of a public key. But there's also some other stuff that looks like a script. And in fact, it is a script, and we'll talk more about that very soon. Okay, so like we said, each transaction output doesn't just specify a simple public key, it actually specifies a script. So what do I mean by that? What is a script and why do we use scripts? In this section, we're going to talk about what the Bitcoin scripting language is and why script is used instead of simply assigning a public key. Okay, so to understand scripts, I think the easiest way is by an example. And we'll take as an example the most common script in Bitcoin, which is to redeem a previous transaction by signing with the correct public key. So this is what the output address would look like in that case. The output address is really a script. And in this case, the script is going to have 4 instructions. So what happens to this script? Who runs it? How does this script indicate who has the ability to spend these coins? The secret is that the input address is also a script. So that's a bit of script that you combine with the output address. You simply concatenate them. And that gets you one script that has to run successfully in order to claim a Bitcoin. So traditionally, these 2 scripts are called script sig and script pub key. and that's because in the simplest case, the output script just specifies a public key, and the input script specifies a signature with that public key. When a transaction is being validated, the two scripts get pasted together, they get run, and if the concatenated script can run without any errors, this is considered a valid transaction. So where did this scripting language come from? It doesn't really have a proper name. It's just called Script, or the Bitcoin scripting language, and it was built specifically for Bitcoin. It was probably most inspired by a language called Forth, which is an old stack-based simple programming language. But you don't need to understand Forth to understand Bitcoin scripting. The key design properties here were to have something that was quite simple, quite compact, but yet had support for pretty sophisticated cryptography. So there are special purpose instructions to compute hash functions and to compute signatures and verify signatures. And this is a stack-based language. And you may have never seen a stack-based language before in your life, but I'll explain on the next slide what that means and why that was chosen. So there are a lot of limits here that are important to keep in mind. In particular, there are no loops in the Bitcoin scripting language. Every instruction is executed exactly once in a linear manner. So if you look at a script, just based on the number of instructions in the script, you know exactly how long it might take to run and how much memory it could use. So this is not a Turing-complete language. It doesn't have the ability to compute arbitrarily powerful functions, and this is by design because the miners have to run these scripts, which are submitted by arbitrary participants in the network, so you don't want to give them the power to submit a script that might have an infinite loop or might run forever. And since it's not a Turing-complete language, we don't have the halting problem. You can look at any Bitcoin script and be sure that it's going to terminate within a finite number of steps, which is just the number of instructions that are in that script. Okay, now the fun part. We're going to look at a specific Bitcoin script and exactly how it's executed. This is the same example as before. This is the most common script in Bitcoin. A script where the sender of coins simply specifies the public key of the recipient, and the recipient of the coins, to redeem them, has to specify a signature using that specified public key. So the first two instructions in this script are simply data instructions, like I said, and these are the signature and the public key used to generate that signature. And these were specified by the recipient in that script sig component or the input script. So executing data instructions is easy in a stack-based language. If you see data, you just push it onto the stack. And that's the only interaction with memory that you have in a stack-based programming language. There's no variables, there's only a stack. So the only thing you can do to write data to memory is to push it onto the stack. So after we've pushed those two values onto the stack, we're going to start executing the second half of the script, which was specified by the sender of the coins. So this is the script pub key component of the script. And now we're going to start to actually manipulate some of those values on the stack. So this duplicate instruction, opdup, says simply take the value that's on the top of the stack, pop it off, and then write 2 copies back to the stack. So we're just going to duplicate that public key. The next instruction, hash 160, says take the top value on the stack and compute a cryptographic hash of it. So this top value is going to be converted from the public key into a hash of the public key. Now we're going to do one more push of data onto the stack. And this data, remember, was specified by the sender of the coins. So this is the public key that the sender specified had to be used to generate the signature to redeem these coins. So now at the top of the stack we have 2 values. We have the hash of the public key as specified by the sender, and the hash of the public key that was actually used by the recipient when trying to claim the coins. And we'll just run this equal verify command, which just says, are the 2 values at the top of the stack equal? If they aren't, an error is going to be thrown and the script will stop executing. But we'll assume that they are. We'll assume that the recipient of the coins actually did use the correct public key. That instruction will consume those two data items that are at the top of the stack. So now we're left with two data items on the stack, a signature and a public key. And we've already checked that the public key was the right public key that was specified by the sender of these coins. And now we want to check that the signature is actually valid. So this is where the power of the Bitcoin scripting language really comes into play. There's one instruction here that lets you verify a signature. So it's easy to write scripts that do signature verification without calling any special library to check the signatures. That's all built into the Bitcoin scripting language. Now, one thing I haven't told you is what is this actually a signature of? What was the input to the signature function? And it turns out there's only one thing you can sign in Bitcoin, which is an entire transaction. So this check sig instruction is going to verify that the entire transaction was successfully signed. So in just one go, hopefully the check sig instruction will pop those remaining two items off of the stack, check that the signature is valid, and now we've executed every instruction in the script. There's nothing left on the stack, and if we haven't had any errors, the output of this script will be a simple yes. So every Bitcoin script can only produce two outcomes. It can either execute successfully with no errors, in which case the transaction is valid. If there's any error while the script is executing, the whole transaction will be invalid and shouldn't be accepted into the blockchain. So a little bit more about the Bitcoin scripting language. It's very small. There's only room for 256 instructions because each one is given 1 byte. And of those, 15 of them are currently disabled, so you can't use them at all. And 75 of them are reserved, so haven't been assigned any specific meaning yet, but might be instructions that are added later in time. So there's a lot of the basic instructions that you'd expect in any programming language are going to be there. There's basic arithmetic, basic logic like if and then, throwing errors, not throwing errors, returning early. And finally, there are crypto instructions, like I said. So there are hash functions, instructions for signature verification, and there's a special, very important instruction for multi-signature verification. That's called check multisig. So this, even more powerful than checking just a single signature with one instruction, Bitcoin actually lets you check multiple signatures with one instruction. So with multisig, you specify n public keys, and you specify a parameter t, or a threshold. And for this instruction to execute validly, there have to be at least t signatures, t out of n of those public keys that are valid. So we'll show some examples of what you'd use multisig for in a second, but this is quite a powerful primitive that in a compact way in the Bitcoin scripting language, you can express the concept that t out of n of these public keys must sign in order for this transaction to be valid. So there's an important bug here. There's a gotcha, which has been there since the beginning of time, which is that in the original implementation of this, the check multisig instruction actually pops an extra data value off the stack and ignores it. So this is just a quirk of the Bitcoin language. It's something that in programming you have to deal with by putting an extra dummy variable onto the stack. And at this point, it's considered a feature in Bitcoin in that it's not going away. The costs of removing it are much higher than the damage it causes. So this is just a fun bug that everybody in the Bitcoin community gets to live with. So, like I've said, we have this whole scripting language that lets us specify, in some sense, arbitrary conditions that must be met in order to spend coins. But as of today, this isn't used very heavily. So if you look at the history of Bitcoin and look at what scripts have actually been used, the vast majority, 99.9%, are exactly the same script, which is in fact the script I showed you in our example of a script execution, a script that just specifies one public key and requires a signature for that public key in order to spend the coins. There's a few other things that have some use. So multisig gets used a little bit, and there's a special type of script called pay-to-script hash that I'll talk about in just a minute. But other than that, there hasn't been too much creativity in terms of what scripts people actually use. And one reason for that is that Bitcoin nodes by default have a whitelist of scripts, and they refuse to accept scripts that they consider not standard. This doesn't mean that those scripts can't be used at all, it just makes them harder to use. And I'll talk about exactly what that means a little bit later when we talk about the Bitcoin peer-to-peer network. Okay, so I mentioned that some of the scripts are what we call proof of burn. So proof of burn is actually a script that can never be redeemed. So if you have a proof of burn script, it's provable that those coins have been destroyed. There's no possible way for them to be spent. This is quite simple to implement. You just use this code op-return, which throws an error if it's ever reached. And no matter what values you put before then, that instruction will get executed eventually, in which case this program will crash. The data that comes after op-return is never going to be looked at, so this is an opportunity for people to specify arbitrary data in a script. So what is the point of proof of burn? Well, there's two main things that this gets used for. The first is to write arbitrary data into the blockchain. If for some reason you want to write your name, or if you want to timestamp and prove that you knew some data at a specific time, you can create a very low value Bitcoin transaction that's proof of burn. So you can destroy a very small amount of currency, and in exchange you can write whatever you want into the blockchain, which should be kept around forever. The other example of proof of burn we'll talk about in a later lecture on alternate currencies, but it can be a way to bootstrap an alternative to Bitcoin by forcing people to destroy Bitcoin in order to gain coins in the new system. So one thing that's funny about this is that the sender of coins has to specify the script exactly. So this might be funny if you're a consumer, you're shopping online, you're about to order something and you say, all right, I'm ready to check out, I'm ready to pay, tell me the address where I should send my coins. And the retailer came back and said, oh, well, we're doing something fancy now. We're using multi-sig. We're going to ask you to send the coins to some complicated script. You might say, I don't know how to do that. That's too complicated. As a consumer, I just want to send to a very simple address. So in response to that problem, there's a really clever hack in Bitcoin, which is that instead of having the sender specify the entire script, the sender can specify just a hash of the script that is going to be needed to redeem those coins. So this looks like the sender specifying a very simple script which just hashes the top value on the stack and checks to see if it's equal to the required redemption script. So the receiver of those coins, all they have to do, it looks like, is just specify the right script, and then this transaction will verify. So the basic script is very easy to satisfy here. The receiver just has to specify as a data value the value of the script that whose hash the sender specified. But after this happens, a special second step of validation is going to occur, where that top data value from the stack is going to be reinterpreted as instructions, and then it's going to be executed a second time as a script. So we see there were two stages that happened here. First, there was this traditional script which checked that the redemption script had the right hash, and then the redemption script will be deserialized and run as a script itself, and here's where the actual signature check is going to happen. So this is called pay-to-script hash in Bitcoin as an alternative to the normal mode of operation, which is pay to a public key. And the reason this was so complicated is that this was added to Bitcoin after the fact. This wasn't part of the initial design specification. This is probably the most notable feature that's been added to Bitcoin that wasn't there in the original specification. And it solves a couple of important problems. It removes complexity from the sender, so the recipient can just specify a hash that the sender sends money to. And it actually has a nice efficiency gain, as we'll talk about later, since miners have to track the set of output scripts that haven't been redeemed yet. The output scripts are now as small as possible with pay-to-script hash, because they just specify a hash, and all of the complexity is pushed to the input scripts. So we've just invested the effort to understand Bitcoin scripts a little bit, but I haven't really shown you what's so cool about Bitcoin scripts yet. It turns out you can do quite a lot of neat things that will justify the complexity of having a scripting language instead of just specifying public keys. So one of them is to do an escrow transaction. So this is a classic situation online. Alice and Bob want to do business with each other. Maybe Alice has just won some online auction and is ready to buy some things from Bob. Now Alice wants to pay Bob in Bitcoin for Bob to send some physical goods back to Alice. But we get into this problem where Alice doesn't want to pay until after she's received the goods, but Bob doesn't want to send the goods until after Bob has been paid. So what can we do about that? There's quite a nice solution in Bitcoin that's actually used quite heavily in practice, which is to introduce a third party and do escrow transactions. So how does this work? Well, Alice is going to send the money not directly to Bob, but create a multi-sig transaction that requires 2 of 3 people to sign in order to redeem the coins. And those 3 people are going to be Alice, Bob, and Judy, who's a judge who's going to come into play in case there's any dispute. So Alice will create this transaction for the desired amount with that 2 out of 3 multi-sig between Alice, Bob, and Judy. Alice signs the transaction, redeeming some coins that she owns, and this will get published in the blockchain. So at this point, these coins are held in escrow between Alice, Bob, and Judy, and any 2 of them can specify where the coin should go. So Bob will be satisfied after that happens that he's safe sending the goods over to Alice. So he'll mail them or deliver them physically. Now what we hope happens in the normal case is that Alice and Bob are both honest, in which case the goods arrive on time. They're what Alice was expecting, and she wants to actually release the money from escrow so that Bob can spend it. So if this happens, Alice and Bob can both sign a transaction redeeming the funds from escrow and sending them to Bob. And the great thing here is that Judy never had to get involved at all. There was no dispute, and so Alice and Bob were able to sign, and that represents 2 out of the 3 people required by the multi-sig transaction. So in the normal case, this isn't that much less efficient than Alice just sending Bob the money. It requires just 1 extra transaction on the blockchain. Now, what would have happened if Bob didn't actually send the goods? Or if he tried to send them and they were lost in the mail? Maybe he sent the wrong size. Alice now doesn't want to pay Bob because she thinks that she got cheated and she wants to get her money back. So Alice and Bob are definitely not both going to sign a transaction that releases the money to Bob, but Bob's also not going to sign a transaction that releases the money back to Alice because he may be denying Alice's claim of fraud here. So now we're going to have to get Judy involved. Judy's going to have to decide which of these 2 people was honest, which one doesn't deserve the money. And if Judy decides that Bob cheated, Judy will be willing to sign a transaction along with Alice, sending the money from escrow back to Alice. So Alice and Judy can get together. That's 2 of the 3 required signatures, and Alice can get her money back. And of course, Judy would have the opportunity to rule in the other direction. If Judy thinks that Alice is at fault here and Alice is simply refusing to pay when she should, Judy can sign a transaction with Bob, sending the money to Bob. So Judy essentially has full control here, but the nice thing is that she won't have to be involved unless there's a dispute. Another cool application is what are called green addresses. So the problem here is that Alice wants to pay Bob, and Bob's offline. So Bob can't go and look at the blockchain to see if a transaction that Alice is sending is actually there. Maybe Bob simply doesn't have the time to go and look at the blockchain and wait for the transaction to be confirmed. Remember that normally we want a transaction to be in the blockchain and be confirmed by 6 blocks, which takes up to an hour before we trust that it's really in the blockchain. Or maybe Bob is just in a Faraday cage and doesn't have any connection to the internet at all, so Bob is never going to be able to check the blockchain. This would be the case, say, if Bob is a person selling food on the street. So to solve this problem of being able to send money using Bitcoin without the recipient being able to access the blockchain, we have to introduce another third party, which is the bank. So Alice is going to talk to her bank and say, hey, it's me, Alice. I'm your loyal customer. Here's my card or my identification. And I'd really like to pay Bob here. Could you help me out? And the bank will say, sure, I'm going to deduct some money out of your account and draw up a transaction from one of my green addresses over to Bob. So notice that this money is coming directly from the bank to Bob. Some of the money, of course, in a change address is going back to the bank, maybe. But essentially, the bank is paying Bob here from a bank-controlled address. That bank-controlled address comes with a guarantee that that money will never be double spent. So as soon as Bob sees that this transaction is signed by the bank, if he trusts the bank, if he trusts the bank's guarantee not to double spend the money, he can accept that that money will eventually be his when it's confirmed in the blockchain. Now notice that this is not a Bitcoin enforced guarantee. This is a real-world guarantee. So Bob has to trust that the bank in the real world is doing a business and cares about their reputation and won't double spend for that reason. And the bank will be able to say, you can look at my history, I've been using this green address for a long time and I've never double spent, therefore I'm very unlikely to do so in the future. Of course, if the bank ever does double spend, trust in this whole system is going to collapse pretty quickly. And in fact, the two most prominent online services that implemented green addresses, which were InstaWallet and Mt. Gox, both ended up collapsing. So for that reason, green addresses aren't used as much in Bitcoin as when they were first proposed. People were really excited and thought this was a great idea and a way to do payments more quickly and without accessing the blockchain. Now people are actually quite nervous about this idea. And they're worried that this puts too much trust in the bank. As a result, this isn't used that much in practice, even though it's a cool protocol. A third example I'd like to show you is a way to do efficient micropayments. So the setup here is that Alice is a customer who wants to pay Bob a low amount of money for some service that she's going to use. So maybe in this case, Bob is really Alice's wireless service provider, and Alice wants to pay a small amount of money for every minute that she talks on her phone. Now you can see why a solution that won't work here is to simply create a Bitcoin transaction every minute that Alice speaks on the phone. That's going to create too many transactions, there will be too many transaction fees, and nobody's happy about that. The simple solution here is to create a new low-value transaction every minute that Alice talks on the phone. So if she talks for 2 hours, you might need over 100 transactions. Now, the problem that you're going to get into in that system is that those transactions might be all very low value, and the transaction fees might really kill you. So if the value of each one of these transactions is on the order of what the transaction fees are, you're going to be paying quite a high cost to do this. So what we would like is if you can combine all these small payments into one big payment at the end. And there's actually a neat way to do this with serial micropayments. So how is this going to work? So we start with a multi-sig transaction that pays the maximum amount Alice would ever need to spend to a multi-sig transaction requiring both Alice and Bob to sign to release the coins. Now, after the first minute that Alice has used the service, or the first time Alice needs to make a micropayment, she signs a transaction spending those coins that were sent to the multi-sig address, sending one coin to Bob and returning the rest to Alice. After the next minute of using the service, Alice signs another transaction, and this time she's paying 2 coins to Bob and sending the rest to herself. And notice that these are just signed by Alice. They haven't been signed by Bob yet. Alice is going to keep sending these transactions to Bob every minute that she uses the service. Notice that these aren't getting published in the blockchain, they're just getting sent from Alice to Bob. Eventually, Alice is going to finish using the service, in which case she'll tell Bob, I'm done, you can cut off the service, I'm not going to pay you anymore. And Bob's going to say, great, I'll disconnect your service, and I'm going to take that last transaction that you sent me, and I'm also going to sign that and publish that to the blockchain. So since each transaction was paying Bob a little bit more and Alice a little bit less, whatever the final one is what Bob is going to choose to actually redeem, paying him for the service that he was provided and giving the rest of the money back to Alice. And the great thing is that all those transactions that Alice signed along the way won't make it to the blockchain. Bob doesn't have to sign them. They'll just get discarded. So technically, all of these transactions are double spends. So unlike the case with green addresses, where we were specifically trying to avoid double spends with a strong guarantee, with this micropayment protocol, we're actually generating a huge amount of potential double spends. Although in practice, if both parties are operating normally, Bob will never sign any transaction but the last one, in which case the blockchain won't actually see any attempt at a double spend. Now there's one more detail here, if you stop and think for a second, which is somewhat tricky to deal with. What if Bob never signs the last transaction? He may just say, I'm happy to let the coins sit there in escrow forever, in which case maybe the coins won't move, but Alice will be out the full value that she paid at the beginning. So there's a very clever way to avoid this problem using a feature that I described earlier but haven't explained yet, which I'll need to introduce now. And that feature is called lock time. So to avoid this problem, before the micropayment protocol can even start, Alice and Bob will both sign a transaction which refunds all of Alice's money back to her, but is locked until some time in the future. So before Alice signs the first transaction paying for the first minute of service, she's going to want to get this refund transaction from Bob and be able to hold that in her hand, and know that if she makes it to time t and Bob hasn't signed any of the small transactions that Alice has sent, Alice can publish this transaction which refunds all of the money directly to her. So what does it mean when I said it's locked until time t? How do we do that? Well, you'll remember when we looked at the metadata in Bitcoin transactions that there was this lock time parameter, which I had left unexplained. It's quite simple, actually. If you specify any value other than 0 for the lock time, that tells miners, don't publish this transaction until this point in time. The transaction is invalid and can't be published until either a specific block number or a specific point in time based on the timestamps that are being put into blocks. So this is a way of preparing a transaction that can only be spent in the future if something else doesn't happen. And it works quite nicely in that micropayments protocol as a safety valve for Alice to know that if Bob never signs, eventually she'll be able to get her money back. So hopefully those examples have shown you that you can do some pretty neat stuff with Bitcoin scripts. Those are just 3 examples that are the most practical and simple to explain, but there are a lot of other things that people have looked into doing. One of them is multiplayer lotteries, which is a very complicated multi-step protocol with a lot of transactions with different lock times. There are escrows in case people cheat, but you can actually run a fair multi-party lottery over Bitcoin using just the scripting language, which is really neat. There are other things, like you can pay someone if they know the pre-image of a hash, so you can try to pay somebody to do some brute force work for you. And there are a couple of neat protocols for different people to get their coins together and mix them so that it's harder to trace who owns which coin. And we'll talk about that a lot more in our lecture on anonymity. So the general term for contracts like this is smart contracts, which means that the contracts actually have some technical enforcement of something that used to be enforced through things like laws or courts of arbitration. So it's a really cool feature of Bitcoin that we can use scripts and we can use the miners and we can use transaction validation to enforce things like escrow or the micropayment protocol. And you don't have to rely on any centralized authority to actually enforce these contracts. Now the whole field of smart contracts goes quite deep. There's a lot more smart contracts people would like to apply, a lot of which you unfortunately can't build with the Bitcoin script today. So the Bitcoin script is fairly limited in the types of things that you can address. There's a lot of smart contracts people wish they could build that either are impossible or nobody has come up with a way to do it yet. But you can do quite a few interesting smart contracts with the Bitcoin script. So now let's talk about how Bitcoin blocks get put together. So we've been talking about the blockchain and the fact that transactions are actually grouped by blocks, but everything in this lecture so far we've been talking about just individual transactions getting published. So why do we group transactions together into blocks? Well, a couple reasons. One is that that creates a nice single unit of work for miners that's bigger than the individual transaction size. So if the miners had to do work and do hashing and add metadata for every transaction in the system, that would provide too much overhead. It also makes the hash chain of blocks shorter because we only need one block for a large number of transactions. And that's going to make it easier for us to verify the blockchain data structure. So what does the blockchain data structure look like? It's a pretty clever combination of two different hash-based data structures. So on the top here, we have a hash chain of blocks. Each one has a block header and then a pointer to some transaction data, as well as a pointer to the previous block in the sequence. And remember, these are hash pointers. And then we have a tree of all of the transactions that are included in each block. So this is a hash tree, or what's called a Merkle tree, which commits to all of the transactions in the block in quite an efficient way. So it's easy to provide just the path through the tree, which will be logarithmic in size, to prove that that transaction is included in a specific block. So that's the high-level idea behind a block. What does it look like in practice at the low level? So we'll do another deep dive into the actual data here. So this is what a Bitcoin block looks like. There's what's called the block header, which has all of the metadata for that block. And then there's that Merkle tree of transactions. So basically a long list of transactions. All of the hashes are arranged in this tree structure, which gives you the ability to efficiently prove which transactions are included in a block. The most important part, of course, is the header, which mostly has information related to the mining puzzle, which was talked about in the lecture on consensus, and we'll revisit in the lecture on mining. But recall that the most important thing here is that the hash of the block header has to start with a large number of zeros for the block to be valid. And then there's some other data to make that happen. There's a nonce that miners can change. There's a timestamp. There's a indication of how difficult this block was to find. That's all stored in the header. And the important thing is that the header is the only thing that's hashed during mining. So to verify that chain of blocks, all you need to do is look at the headers. And the only transaction data that's included in the header is that one root of the transaction tree. So that's this Merkle root parameter. The other thing that's interesting about blocks is that they have one special transaction in the Merkle tree, which is unlike all the other transactions we looked at before. And this is the coin-based transaction. So this is where the creation of new coins in Bitcoin happens. It mostly looks like a normal transaction with a few exceptions. So the value of this transaction is going to be equal to currently a little over 25 Bitcoins. As we discussed, this is a flat mining reward, which is set by the system and which is halving every 4 years. In practice, it will be a little bit more than 25 Bitcoin because it also gets to include the transaction fees collected from every transaction included in the block. So the pointer to the output transaction that this coin-based transaction is receiving is a null pointer. It's a hash of all zeros. And this is an indication that since this is the creation of new coins, there is no antecedent. There's no previous transaction that's being consumed to create these coins. And there's also this special Coinbase parameter. And the Coinbase parameter is completely arbitrary. The miners can put whatever they want in there. So famously, in the very first block ever mined in Bitcoin, the Coinbase parameter had a quote from the newspaper. It had a quote from the Times of London describing a story involving the Chancellor bailing out banks, which was both a political commentary on the motivation for starting Bitcoin and served as a commitment that Bitcoin, the first block, was obviously mined after this newspaper came out. But since then, miners are free to put whatever they want in the Coinbase parameter. It's been used as a place to put some arbitrary data for different reasons, to signal support by miners for different new features, but there's no actual limits on what miners can put in there. So with both the block format and the transaction format that we described earlier, the best way to learn it is to just see for yourself. So there's a lot of websites that make this data accessible. This is a screenshot from blockchain.info, which I found very helpful myself in understanding and exploring what's going on at a low level in Bitcoin. There are a lot of other websites that do a great job of making this information accessible. So you can look at the graph of transactions, see which transactions redeem which other transactions, look for transactions with complicated scripts, You can look at the block structure and see how blocks refer to other blocks. It's all available online because, again, the Bitcoin is a public data structure, so a lot of different people have put very pretty wrappers around this to explore it graphically. So we've been talking about the ability for participants to publish a transaction and get it into the blockchain as if this happens by magic. Of course, it doesn't happen by magic in the real world. It happens through the Bitcoin network. So what is a Bitcoin network? It's a peer-to-peer network, so it inherits a lot of ideas from peer-to-peer networks that have been proposed for all sorts of other purposes. It's a peer-to-peer network where all nodes are equal. There's no hierarchy, there's no centralized special nodes, no master nodes. Every node on Bitcoin is an equal peer. It runs over TCP, it has a random topology, so there's random nodes are paired with random other nodes. And new nodes can come at any time. So you can download the Bitcoin client today, you can spin your computer up as a node, and you'll be a participating Bitcoin node with equal rights and capabilities as every other node on the Bitcoin network. Now the network is very dynamic, it changes over time, nodes are coming and going all the time, although there's actually no explicit way to leave the network. Instead, if you don't hear from a node for a while, 3 hours is the amount that's hard-coded into the common clients. People eventually start to forget you, so it gracefully handles nodes going offline. So what does that mean that you can simply join the Bitcoin peer-to-peer network at any time? Well, if this is a picture of the network at one moment in time, obviously scaled down quite a bit with just 7 nodes, but this is a picture of what it might look like, 7 nodes with all random connections to each other. And notice that the numbers are scattered around here because there's no geographic topology here. Networks connect to other nodes in a random fashion by design. Now, if you launch a new node and say you want to join the network, you start with a simple message to one node that you know about. So all you need to know is how to get to one node that's already on the network. This is usually called your seed node, and there's a few different ways you can look up lists of seed nodes to try connecting to. But you find your seed node, and you send a special message saying, tell me all the peers that you have. Tell me the addresses of all the other nodes in the network that you know about. And that node will respond and say, well, I'm paired with nodes 1 and 7, you can try them. And then you might go talk to 1 and 7 and say, hey, tell me everybody on the network that you know about. And they'll send you the nodes that they know about, and you can iterate as many times as you want until you have a list of peers to make connections with. And then you can choose which ones to peer with, and you'll be a fully functioning member of the Bitcoin network. And again, there's a few steps of randomness here, so depending on which seed node you used or which of the peers of the seed node you decided to go and talk to, you'll end up with a random set of nodes that you're connected to, but that's perfectly fine. So now that you're a member of the network, what is the network good for? Well, the network maintains the blockchain, so if you want to publish a transaction, you want to get the entire network to hear about it. And there's a simple flooding algorithm to make this happen. So let's say that node 4 here hears about a new transaction. So Alice wants to pay Bob some money. Alice creates a Bitcoin transaction and submits it to node 4. Or maybe her wallet software or her exchange does that on her behalf. But somehow this transaction gets to node 4. Now node 4 says, great, I've got a new transaction. Alice wants to pay Bob. Let's tell everybody about it. Sometimes this is called a gossip protocol, because it's very simple. If you have news, you try to tell as many people as you can, and they try to tell as many people as they can, much like people gossiping in the real world. Great, so node 4 is going to talk to its neighbors, node 3 and node 2, and say, hey, check out this new transaction. Alice wants to pay Bob. And those nodes will add it to their own pool of pending transactions. So each node maintains a list of all the transactions they've heard about that haven't been put into the blockchain yet. And then they can decide to forward that onto other nodes. So 3 is going to talk to its neighbors and say, new transaction for you, Alice wants to pay Bob. That'll end up in their transaction pools and so on. And we want to make sure that this process doesn't go on forever. So let's say that node 2 comes along later and tries to tell node 7, hey, new transaction, Alice wants to pay Bob. Node 7 is going to say, that's all right, node 2, I've already heard about that. I already got it in my memory pool. I don't need to forward it further. So eventually this thing has to stop because every node will have heard about the new transaction and they won't forward it anymore. And remember, every transaction is identified uniquely by its hash. So each node can tell they've seen that hash before and that they don't need to keep forwarding that transaction, so it won't loop around the network forever. So how do nodes decide when they hear about a new transaction whether or not they should propagate it? The most important thing they do is they check to see, given their view of the blockchain, whether or not this transaction is valid. So they do all the transaction validation we talked about earlier. They run the script, they see that the script checks out, they see that the coins that are being redeemed here haven't already been spent. And if all of that checks out, then this looks like a valid transaction that they should try to relay. With a couple of other caveats, by default, nodes won't relay the transaction if it's a non-standard script. If the script has any weird features, if it doesn't match a fairly simple whitelist of scripts that nodes know about, even though it's a valid transaction, the nodes won't relay it. They'll also make sure that they haven't seen the transaction before. That's that condition to avoid infinite loops. And there's another property, which is that they won't relay the transaction if it looks like a double spend. So if they've seen a transaction where Alice tries to send some specific coins to Bob, and then later they see a second transaction where Alice tries to send those same coins to Charlie, the node shouldn't relay the second transaction. Even though either transaction could be valid because those coins still haven't been spent, they'll only relay the first one they hear. And that's an extra guard against double spending. But it's important to keep in mind that all of these checks are just sanity checks. So well-behaving nodes all implement these to try to keep the network healthy and running properly. But there's no rule that says that nodes have to follow these specific steps. So since it's a peer-to-peer network and anybody can join, there's always the possibility of a node not following this exact protocol, forwarding double spends, forwarding transactions that aren't standard, forwarding transactions that aren't valid. And that's why it's important that every node do the checking for itself. So it's possible that nodes will end up with a different view of the pending transaction pool based on what they've seen. So let's go back to this example where node 4 originally relayed a transaction where Alice was trying to pay Bob. And let's say that this transaction hasn't yet flooded to the entire network, and before it gets to everybody, node 1 is going to announce a new transaction and say, hey, I just heard Alice is trying to pay Charlie. Now from node 1's perspective, this is a valid transaction, and they haven't seen the other transaction where Alice is trying to pay Bob. So node 1 is going to implement the protocol normally and is going to tell all of her neighbors about it. Now the neighbors that haven't heard the conflicting transaction yet will add it to their transaction pool. Whereas other neighbors, like node 6 in this example, they've already received a transaction where Alice is trying to pay Bob. So node 6 is going to say, I don't want to hold two conflicting transactions in my pool. I'll just keep the one I already have. The network may end up in a divided state here, where different nodes have a different view of what the pending transaction pool is. But that's fine. These transactions haven't been published in the blockchain yet, so this is just a temporary state where nodes disagree on which transaction should be put into the next block. In practice, this is a race condition. If nodes have a different perspective on which transactions are pending or which blocks have been accepted, that's okay in a temporary state, and eventually they'll sort it out. So in the case of transactions, if different nodes have a different view of the pending transaction pool, depending on who mines the next block, they'll essentially break the tie or the race condition and decide which of those two pending transactions should end up being put permanently into a block. And once one of those two transactions has been put into a block, other nodes will see that the transaction that they're holding onto in their pool is now never going to make it into a block because it would be a double spend, and they'll just drop it. So if the transaction where Alice tried to pay Bob successfully makes it into a block first, the nodes who heard the transaction where Alice tried to pay Charlie will just say, that's not a valid transaction anymore, so I can forget it. So the default behavior is for nodes to just hang on to whatever they hear first, which means that network position matters. If two conflicting transactions or two conflicting blocks get announced at two different positions in the network, they'll both flood in opposite directions, and the nodes which end up with one transaction or the other will depend on which side of the network they started out closer to. Of course, this assumes that every miner implements this logic where they keep whatever they hear first, but there's no central authority enforcing this. So every node is free to do whatever logic they want. So if for some reason, if any node wants to, they can choose to implement any other logic they want for choosing which blocks or which transactions to forward. We'll talk about that more in our lecture on mining, why miners might want to implement some different logic other than the default. Now, I've been talking mostly about transactions here. The logic for announcing new blocks whenever miners find a new block is almost exactly the same as propagating a new transaction. So the same algorithm is used to announce new blocks around the network. It's the same flooding algorithm, the same gossip process. And in this case, instead of verifying that the transaction is valid by running a script, the nodes are going to verify that the new block is valid by computing the hash and making sure that it starts with a sufficient number of zeros to meet the difficulty target. Now, validating a block is also much more in-depth, because in addition to validating the header and seeing that the hash value is correct, nodes are asked to validate every transaction included in the block to make sure that the block contains only valid new transactions. And the other check, which is this really important critical part that makes Bitcoin consensus what it is that nodes shouldn't forward a block unless it builds on their perspective of the current longest chain. So they have a view of the blockchain, and they should only forward new blocks if they come at the very end of the chain, not at some earlier point. And this avoids forks building up. So just like with transactions, nodes can implement different logic if they want. They're free to relay blocks that aren't valid, or to relay blocks that build off of an earlier point in the blockchain. So some nodes may be trying to relay a block that doesn't extend the current longest chain, that actually builds a fork. And that's okay, the protocol is designed to withstand that. So how long does this flooding algorithm actually take? How much latency is imposed here? This is a graph showing the average time for new blocks to propagate to every node in the network. And the three lines show the 25th, the 50th, and the 75th percentile of how long it takes for a new block to reach every node in the network. And if you look at the 75th percentile there for some of the larger blocks, and this is heavily dependent on size because of bandwidth constraints that some nodes have, you'll see that the average propagation time is over 30 seconds. So this shows that this isn't a particularly efficient protocol. On the internet, 30 seconds is a pretty long time for people to hear about something. The reason it takes so long is because the protocol is not very efficient. It wasn't designed to be efficient, it was designed to be simple and to have no structure so that every node is equal and they can come and go at every time. And as a result, the topology may not be optimized for fast communication. A block may need to go through many nodes before it reaches some of the most distant nodes in the network. Whereas if you design the network top-down for efficiency, you would design it to make sure that the path between any two nodes was very short. For Bitcoin, it's more important to have a decentralized structure where all nodes are equal, even if that means that the propagation time can be over 30 seconds in some cases. So how big is a Bitcoin network? Well, there's no official statistics anywhere because, again, there's no central authority overseeing it. It's simply whatever the nodes participating, they are the Bitcoin network. So it's impossible to measure exactly, and it's changing all the time. But a number of researchers have looked into this and tried to come up with estimates. On the high end, some researchers have said that over 1 million IP addresses in a given month will at some point be running the Bitcoin protocol and acting at least temporarily as a Bitcoin node. But if you look at full nodes that are actually permanently connected and are fully validating every transaction they hear and running the full protocol, it's only about 5 or 10,000, which may be a surprisingly low number. And in fact, that number may be dropping. There's no evidence that the number of fully validating nodes is going up, and there's some concern that the number of fully validating nodes is actually going down. So to be a fully validating node, You want to stay permanently connected so that you hear about all data. The longer you're offline, the more catch-up you're going to have to do to hear about all the transactions you missed. And you're going to have to store the entire blockchain. You'll also need a pretty active network connection so that you can hear every new transaction and forward it to your peers. So you can see the growth over time here. And currently it takes about 20 gigabytes to store the entire blockchain, which isn't too bad. If you have a few years old PC with an active network connection, you have what it takes to be a fully validating node. Although you basically need to dedicate that machine to doing that and not much else. Fully validating nodes maintain the entire set of unspent transaction outputs. So every coin that's available to be spent, and remember, those are just unspent output transactions, ideally you'd like to store this in RAM, so that when you hear a new proposed transaction on the network, you can quickly check the transaction that it's attempting to claim, run the script, and see if the signature is valid. So currently there are about 12 million unspent transactions, and that's out of 44 million transactions that have ever been proposed. So fortunately that's still small enough to fit in less than a gigabyte of RAM in an efficient data structure, so that if you're running a fully validating node, every time you hear about a new transaction, you can quickly check, run the redemption script, and see that this is a valid transaction that you should put in your pending transaction pool. So in contrast to being a fully validating node, there are lightweight nodes, also called thin clients or simple payment verification clients. This is actually the vast majority of nodes on the Bitcoin network. And the difference here is that these nodes aren't attempting to store the entire blockchain. They only store the pieces that they need to verify some specific transactions that they care about. So for example, if you run a wallet, your wallet might want to be a simple payment verification node. And if somebody sends money to you, you'll act as a node. You'll download the bits of the blockchain that you need to verify that the person sending you the money actually owned it and that the transaction sending it to you actually gets included in the blockchain, but you won't care about the thousands of other transactions going on that don't affect you. Now, an SPV client like this won't have the full security level of being a fully validating node. And the reason is that when they hear a new block, the only thing they can check is the block header. They can check to see that the block was difficult to mine, but they can't check to see that every transaction included in that block is actually valid because they don't have the entire previous blockchain. They don't know the entire unspent transaction output set. They can only validate the transactions that actually affect them. So they're essentially trusting the fully validating nodes to have validated all the other transactions that are out there. So this isn't a bad security trade-off. You're assuming there are fully validating nodes out there that are doing the hard work, and that if miners went through the trouble to mine this block, which is a really expensive process, they probably also did some validation to make sure that this block wouldn't be rejected. And the cost savings of being an SPV node are huge. It's about 1,000 times smaller to just store block headers than to store all of the previous transactions. So instead of storing about 20 gigabytes of data, you're down to about 20 megabytes, which is something that almost anybody on a PC or even on a phone can store and act as a limited node in the Bitcoin network. So finally, we'll talk about some built-in limitations to the Bitcoin protocol and why it's challenging to actually improve them. There are a lot of hard-coded constants that are implemented into the Bitcoin protocol, which were chosen when Bitcoin was proposed in 2009, before we really had any idea that it might grow into this globally important currency. So the most important limits are probably the limits on the average time per block, the size of blocks, the number of signature operations in a block, and the divisibility of the currency. The limitations on the total number of Bitcoins in existence, as well as the structure of the mining rewards, are very likely to never be changed because the economic implications of changing them are too great. Miners have invested a lot of real-world resources into becoming miners, assuming that Bitcoin rewards would take a certain shape and that the limited supply of Bitcoins would remain the way it's been planned. So if you change that, that would have large financial implications for people. So for that reason, the community has basically agreed that those values, whether or not they were wisely chosen, we're basically stuck with. Some other changes you'd like to make seem like they would make everybody better off. Things about Bitcoin that just weren't quite properly designed at the beginning, but are also hard to change. The main aspect of Bitcoin that people are worried about and would probably like to change if they had time to design it over again are limits that affect the throughput of the system. How many transactions can the Bitcoin network process per second? So this limitation comes from the hard-coded limit on the size of blocks. Each block is limited to 1,000,000 bytes. And each transaction has to be at least 250 bytes. So if you divide through and the fact that blocks are found every 10 minutes, you're left with about 7 transactions per second, which is all that the Bitcoin network can handle. And it seems like tweaking those numbers would be very easy. It's just one constant in a file somewhere that you'd have to change. It would actually be very hard to change this in practice for reasons that will become clear in a few seconds. So how does 7 transactions per second compare? Well, if you went down to the offices of Visa and told them, I'm proposing a new payment system that can handle 7 transactions per second, they would probably tell you, that's terrible, and then they would laugh and throw you out the door. They've been working for a long time to build a payment network that goes way bigger than this. So it's said that Visa handles on average about 2,000 transactions per second around the world. And on the busiest times, so think the Saturday before Christmas when everybody's out shopping and swiping a credit card, the Visa network can handle about 10,000 transactions per second. And other payment card networks are similarly big. You can also look at PayPal, which is not as big or as old as Visa, but even PayPal can handle 100 transactions per second at peak times, so an order of magnitude more than Bitcoin. Another limitation that people are worried about in the long term is that the cryptography in Bitcoin is fixed. There's only a couple of hash algorithms, and there's only one signature algorithm, which is elliptic curve DSA, over a specific elliptic curve called SEC P256. And there's some concern that over the lifetime of Bitcoin, which people would like to be for a long time, this algorithm might be broken. Cryptographers might come up with a clever new attack that we haven't foreseen, which makes this an insecure algorithm. And the same is true of the hash functions. Hash functions in the last decade have actually seen steady progress in cryptanalysis, with SHA-1, which is included in Bitcoin, already having some known cryptographic weaknesses. So to change this, we would have to extend the Bitcoin scripting language to support new cryptographic algorithms. So what would it look like to make a change like this, where we just said, we had a problem in Bitcoin, we're going to release a new version of the software, and everybody is going to have to switch? This is what we would call a hard forking change. So in practice, it's impossible to assume that every node would upgrade. Some nodes in the network would fail to get the new software or fail to get it in time. And what would be the implications of that? Well, let's take a look at a network here where most of the nodes have upgraded, but there are a few that haven't. And now let's say one of the new nodes says, hey, I found this nifty, great new block. Maybe it has some new signature algorithm in one of the transactions using the new features that we've added to Bitcoin. So block 4 has found this and says, okay, I'm going to update and say that's now the newest block. So I'm at block index 24. The rest of the network is at 23. But I'm going to propagate that to all of my peers using the normal block flooding algorithm. So node 4 is going to send block 24 out to its neighbors, nodes 3 and 2. Node 3 is going to get it and say, great, I got that one. I'll update my version of the blockchain to have that as the newest block. Whereas node 2 is going to say, that's crazy. You have some operation code that's disabled or reserved. I have to reject this block. I don't understand it. I can't accept it. And similarly, when it gets over to node 6 is also going to say, nope, I can't accept that block either. And now you're going to end up in a state where the new nodes have one picture of the blockchain, and the old nodes have all refused to accept this latest block. So the new nodes will go off and work on a version of the blockchain, including this new block with the new fancy feature. And the old nodes will all be stuck on an old version of the blockchain. And unfortunately, they're never going to catch up, because until they upgrade their software, they'll keep rejecting all of the blocks that are proposed by the nodes in the network that have upgraded to the new version of the protocol. So the reason it's called a hard fork is that the blockchain will split. Every node in the network will be on one side of it based on which version of the protocol it's running, and they'll never join together again. And this is considered unacceptable by the community, that old nodes would effectively be cut out of the Bitcoin network if they don't upgrade their software. So by contrast, there's an approach called soft forking, which tries to avoid creating a permanent fork like this. The observation is that we can add new features to the Bitcoin protocol if they only restrict the set of valid transactions or the set of valid blocks. Because we want to avoid this hard fork situation, we can try to add new features in a way that will cause only a soft fork. So the key to making this happen is that the new features can only make validation rules stricter. They can only limit the set of blocks or the set of transactions that are considered valid. So the new nodes in the network will be enforcing some new, tighter set of rules. So we're relying on enough nodes switching to the new version of the protocol that they'll be able to enforce the new rules, knowing that the old nodes won't be able to enforce the new rules because they haven't heard of them yet. There is a risk here, which is that old nodes might be mining an invalid block because they include some transaction which used to be valid, but according to the new, more strict rules, is not valid anymore. So that could be bad. Those nodes could waste a lot of time mining a block that the new nodes will reject. But when they try to announce that new block, the new nodes will reject it. The old nodes will at least figure out that for some reason, even though I don't understand the reason, the rest of the network has rejected my new block. Therefore, I should move on to the version of the blockchain that all of my peers have, and it won't be a hard fork. They'll have a temporary fork by virtue of the new block they tried to mine that was rejected by the network, but they'll recover and get back onto the main chain. So the classic example of a change that was made via a soft fork was pay-to-script hash, which we introduced earlier in the section discussing the scripting language. So the view of pay-to-script hash from old nodes, and again, pay-to-script hash was not present in the first version of the Bitcoin protocol, they see this script as really simple. All it's doing is hashing this one data value and checking to see if it's equal to the value specified in the output script. The old nodes never do that second step of verification in pay-to-script hash, where they then check to see that that value before being hashed runs as a valid script. So what could we possibly add with a soft fork? Pay-to-script hash was successful. It's also possible that new cryptographic schemes could be added by a soft fork, or that we could add some extra metadata in blocks that had some meaning. And the place you'd add this is in the Coinbase parameter. So today, any value is accepted in the Coinbase parameter, but we could in the future say that the Coinbase has to have some specific example. One idea that's been proposed is that in each new block, Coinbase contains a Merkle root of the entire set of unspent transactions. It would only result in a soft fork because old nodes might mine a block that didn't have the required new Coinbase parameter that got rejected by the network, but they would catch up and join the main chain that the network is mining. Other changes might require a hard fork. That would be if we wanted to add new opcodes to Bitcoin, change the limits on block or transaction size, or do a lot of bug fixes. So for example, the bug I showed earlier, where the multisig instruction pops an extra value off the stack, that would actually require a hard fork. And that's the reason why, even though it's an annoying bug that people wish wasn't there anymore, it's much easier to just leave the bug in the protocol and have people work around it, rather than have a hard fork change to Bitcoin. So all of these hard forking changes, even though they would be nice, are very unlikely to happen, at least within the current climate of Bitcoin. But a lot of these ideas have been tested out and proved to be successful in alternative currencies, which start over from scratch, and we'll be talking about those in a lot more detail in our lecture on altcoins. So I spent a lot of time talking about details today. I know this has been a long lecture with a lot of technical detail, very hard to absorb it all at once. So like I said, I would certainly recommend you can go online and see some of this stuff in practice, see what blocks and transactions look like. It took me a couple of times looking at them before I really had a good sense of what was going on, but I think the practical examples do really help. In the next lecture, given all these mechanics we've introduced, we're going to look at the human side of things. Because after all, human beings aren't Bitcoin nodes, and you're never going to run a Bitcoin node in your head. So how do you as a human actually interact with this network to get it to be usable as a currency? How do you find a node to tell about your transaction? How do you get Bitcoins in exchange for cash? How do you store your Bitcoins? So all of these questions are crucial for making a currency that will actually work for people as opposed to just software.
Welcome to Lecture 4, where we'll talk about how we store and use Bitcoins in practice. In section 4.1, we'll talk about the simplest way of storing Bitcoins, and that is simply putting them on a local device. Now, just to review, in order to spend a Bitcoin, you need to know two kinds of things. First of all, you need to know some information that's stored on the public blockchain. You need to know what the identity of the coin is and how much it's worth, for example. And along with that, you also need to know the secret key of the owner of the Bitcoin. Presumably that's you. Now, if you think about it, the first piece of information, being on the public blockchain, you don't need to worry too much about how to store it because you can always get it back when you need it. But the secret signing key is the thing that you'd better keep track of. So in practice, when we talk about how you store your Bitcoins, what we're really talking about is how you store and manage your keys. And that's going to be the main topic when we talk about how to store Bitcoins. So really, this lecture, which we titled How to Store and Use Bitcoins, might as well be called How to Store and Use Secret Keys, because that's really what it's about. Okay, now, when figuring out how we're going to store and manage our keys, there are three goals that we have in mind. The first goal is availability. You want to be sure that you can actually spend your coins when you want to. The second goal is security, and that is that nobody else can spend your coins. If someone gets the power to spend your coins, they could just send your coins to themselves, and then you don't have the coins anymore. And the third goal is convenience, just that whatever you do, it's relatively easy to use. Okay, so the simplest approach to managing your keys, what to do with them, is just to take the key and store it in a file and put that file on your own local device, on your computer, on your phone, or on some other kind of gadget that you carry or own or control. And evaluating that method against our three goals, well, for convenience, it's great. Nothing could be better than to have, say, an app on your phone where you can push a button or swipe something and spend your Bitcoins. So for convenience, it wins. But when it comes to availability and security, storing things on a local device in a simple way is not such a great idea. And the reason is, first, when you get to availability, that your key, your coins, are no more available than your device. That means if you lose the device, if the device crashes and you have to wipe the disk, if your file gets corrupted or something like that, you're out of luck. The key is lost, therefore your coins are lost. Similarly, for security, your keys, therefore your coins, are just as secure as your device. If somebody managed to break into your device to compromise it, if they can put malware on your device, a virus or something like that, then they can get the key, leak the key to themselves, and they can then send all of your coins to themselves. So although storing things locally is very convenient and very simple, it really isn't up to the task for availability and security. And the way to think about this is a lot like carrying around money in your wallet or your purse or in your pocket. It's useful to have some spending money, but you don't want to carry around your life savings because you worry that you might lose it or that somebody might steal it. And so what you typically do is store a little bit of information, a little bit of money in your wallet, and keep most of your money somewhere else. Now, in order to do all of this, we typically, if we're going to follow the local storage approach, we typically use wallet software. And that's just software that manages all the details of keys and makes things convenient. It keeps track of your coins. It gives you a nice user interface. If you want to send $4.25 worth of Bitcoins to your local Starbucks, the wallet software will give you some easy way to do that. And by the way, if you're using wallet software, once you're using software to manage keys and such, it's a nice trick, it's a useful trick to use a whole bunch of different addresses, a whole bunch of different keys. So rather than taking all of your coins and paying them to one address and controlling them with one key, you can have a separate address, a separate Bitcoin address, and a separate key for each coin. That keeps things separated so that you get a maximum degree of anonymity or privacy. And you don't need, as an individual, to worry about the management of all these different keys and addresses. Your wallet software takes care of it for you and just gives you a very simple interface that says how much is in the wallet and lets you spend it. The wallet software figures out all the details of which keys need to be used and how to generate new addresses and all of that stuff. So one thing you need to do if you're going to be able to receive Bitcoins in payment into your wallet or spend them to somebody else is you need to have a way of exchanging an address with somebody. So you can give them an address or receive an address so that payments can happen. And there are two main ways that addresses are encoded or conveyed in this way. The first one is as a text string, and the second is as a QR code. So as a text string, what we do is we take the bits of the key and we encode it as a number in base 58 notation, and then we use these 58 characters to encode the digits in our base 58 notation. So what this is basically is it's all of the digits and capital letters and small letters, except that they've taken out a few that might be confusing or might look like each other. For example, capital O and 0 are both taken out because they look too much alike. But other than that, most of the characters are here, and you can encode first in base 58 notation and then using this alphabet. The second method for encoding a Bitcoin address is as a QR code, something like this. This is a simple 2D barcode. And you can do something like point your phone at this, take a picture, and your phone can scan it and recover the bits of the address. And so this is the sort of thing you might use, for example, in a store, or if you want to have a phone-to-phone communication. My phone might display a barcode like this, which is my address on it, and your phone might take a picture of it in order to get the address. So this down here actually is an active address, and if you'd like to give me some Bitcoins, feel free to do so. In segment 4.2, we'll talk about hot storage and cold storage. Recall that in 4.1, we talked about how to store Bitcoins on your local computer, the equivalent of carrying money around in your wallet or your pocket. Now, the idea of hot and cold storage is that you're going to have some storage which is hot or online, as on your phone or in your local computer. And as we covered before, storing Bitcoins in that way is convenient, but it's also somewhat risky. You'll keep some money in hot storage, and you'll keep some money in cold storage. Cold storage is offline. It's locked away somewhere. It's not connected to the internet. And it's archival. It's more secure. It's safer, but of course, it's not as convenient. So this is similar to how you carry some money around on your person, but you don't keep your life savings on your person. You put that somewhere safer. And so when we're using this strategy of hot and cold storage, we're going to have separate keys and separate addresses for the coins that are stored either on the hot side or the cold side. And so the main topic of discussion here, the main thing we need to go over, is how you move coins back and forth between the hot and cold sides and what the relationship is between the sides. Okay, so obviously you're going to have separate secret keys to control the coins on the hot side and the cold side. The whole point of cold storage is that the coins that are in cold storage are not vulnerable to attack or loss if the hot storage is compromised. And so you need to have separate private keys for hot versus cold storage. And of course, each side needs to know the addresses that the other side is using, because you want to be able to transfer money back and forth between the different sides, between the hot side and the cold side. And so each side knows its own secret keys, and it also knows the addresses at which the other side will accept transfers. And that lets you do transfers back and forth. Now, in practice, of course, the cold storage is not online. And so the hot storage and the cold storage won't be able to connect to each other across any network. So you can think of the cold storage as being locked up somewhere while the hot storage is operating. Now, the good news here is that even if the cold storage is offline and not connected to anything, the hot storage still knows the addresses at which the cold storage is willing to accept coins. And that means that the hot storage can send coins across to the cold storage even while the cold storage is offline. And that's very nice. At any time, if the amount of money in your wallet in your hot wallet becomes uncomfortably large, you can just transfer a chunk of it over into cold storage, and you don't need to put your cold storage at risk by connecting it in order to receive that money on the cold side. Next time the cold storage connects, it will be able to receive from the blockchain information about those transfers to it, and then the cold storage will be able to do what it wants with those coins. Okay, but now we have a little bit of a problem if you think about it, which is how we manage these addresses. On the one hand, as I said in segment 4.1, we want, for privacy reasons and for other reasons, to be able to receive each coin at a separate address and to be able to manage the different secret keys that are used at that address. And so whenever we transfer a coin from the hot side to the cold side, we'd like to use a fresh cold address for that purpose. But because the cold side is not online, we have to have some way for the hot side to find out about those addresses. And that's the problem that we need to solve. Now, there's a kind of awkward solution to this, which would work, but we'd prefer not to use. And that is this, that we have the cold side generate a big batch of addresses all at once. We transfer those addresses over to the hot side, and then we use them up one by one. And the drawback of that is that we're periodically going to have to reconnect the cold side in order to transfer more addresses. And we might worry that while we're out and about, spending our bitcoins on a night on the town, that the hot wallet will run out of these addresses, and that could be a problem. So that's an awkward solution, generating them in batches. What's a better solution, a more effective solution, is to use a hierarchical wallet, but that requires a little bit of cryptographic trickery. So let me explain the trick behind hierarchical wallets. So just to review, previously when we talked about key generation, when we talked about digital signatures back in lecture 1, we talked about an API operation called generate keys, which generates a public key and a secret key. The public key in a Bitcoin context corresponds to the Bitcoin address that can receive coins, and the private key we still call a private key, and that's the key that allows us to spend or control the coins that are sent to the corresponding address. So this is how things normally would work if we generated keys in the standard way. But with hierarchical key generation, we do things a little bit differently. Rather than just doing generate keys, we do a hierarchical key generation operation. And this generates two things. It generates, rather than an address, it generates what we'll call address generation info. And rather than generating a private key, it generates what we'll call private key generation info. And now we can take this information and generate multiple keys. For example, given the address generation info, we can apply a gen address operation and give it the address generation info and some integer I. And that will generate the ith address in a whole series of addresses. And we can do this for any integer I. Any integer I, we can generate the ith address in the sequence given only that integer and the address generation info. Similarly, on the private key side, we can take this private key generating info and use it to generate a key, again using any integer I. And what we get is the ith key in the sequence. Right. Now, what makes this useful is that it has two important properties. First, that the ith address and the ith key match up and correspond to each other, just as if they were generated the old-fashioned way. And what I mean by that is that a coin that's transferred to the ith address will be spendable and controllable by somebody who knows the ith key. So these behave just like a regular address and a regular key. The other thing that's important is that we have a security property, and the security property is this, that the address generation info doesn't leak keys. That is, it doesn't leak any information about what the keys might be. And that means that it's safe to give the address generation info to anybody, and so that anybody can be enabled to generate the ith key. Now, not all digital signature schemes that exist can be modified in a way like this to support hierarchical key generation. Some can and some can't. But the good news is that the digital signature scheme used by Bitcoin, which is called ECDSA, does support hierarchical key generation, and so we can do this trick. And the reason this is useful for hot and cold storage is that we can take this operation and split it up between the hot side and cold side of our storage, like this. Everything that has a blue background here is done on the cold side, and everything that has a red background is done on the hot side. And so what we do is at the very beginning, on the cold side, we do the generate keys hierarchical operation. We then take the private key generation info that makes and keep it on the cold side. and we take the address generation info that that makes and pass it across to the hot side. Then, once we've done that, the hot side can generate the entire sequence of addresses on its own without needing any further communication with the cold side. We can generate an arbitrarily long string of addresses, or at least long enough that we'd never have to worry about running out. And on the private side, we can generate the corresponding keys, again, without needing to communicate. We can generate that later. So if we do things this way, there's only one passage of information from the cold side to the hot side about keys and addresses. That happens once at the very beginning of the situation. And once that's done, then no further connection is required. And so this lets us use separate keys and separate addresses for every coin that's passed across to the cold side, but without requiring a lot of back and forth communication, and critically for security, without requiring the cold side to connect to the net or pass information out in any way, except once at the beginning. Okay, so with that in place, we can talk about the different ways in which cold information can be stored. I said earlier that information on the cold side, whether it's a key or key generation info or something else, is stored offline. But let's get more specific about exactly how it is stored. The first way we can store it is to store the information in some kind of a device and just put that device in a safe. It might be a laptop computer, it might be a mobile phone or tablet, or it might just be a thumb drive. But whatever it is, we store the information on that device, we turn the device off, we lock the device up. And now, obviously, if somebody wants to steal this, they have to get into our locked storage and get that device away from us. The second method we can use is called a brain wallet. And in a brain wallet, what we're doing is we are taking the information that we want to protect and we're encrypting it under some kind of passphrase or password that a user remembers. Then, in order to get the information back later, we're going to ask the user to give us the passphrase, and then we'll be able to decrypt. If we do this, and if the crypto is done correctly, and if the user picked a good passphrase, then the security of this will be as good as the security of the passphrase. And as long as the user isn't tricked or coerced into giving up the passphrase, and as long as the adversary can't guess the passphrase, then our data is going to be secure. But this, of course, is subject to the same kind of attacks that passwords typically are. The third thing we can do to protect information offline is what's called a paper wallet. We can take the information and we can print it out onto paper, and then we can put that paper in some safe or secure place. We can lock it in a safe deposit box or something like that. Now, the benefit of doing that, obviously, is that, again, just like with a device, the security of this is just as good as the physical security of the paper that we're using. This is a Bitcoin paper wallet. They come in different shapes and sizes, but this is one example. What you see over here is the public address, the address of this wallet. And this is shown in two ways. First, as a 2D barcode, as a QR code. And then second, down here, you see it as a character string in the base 58 notation. Now, originally, this side over here was sealed because it has the private key within it, and you don't want to give away the private key too easily. We can open this up. Originally, we would have broken a seal, and we have this stuff here that's designed to frustrate scanners and people looking through and so on. And eventually, we open it up, and we see over here this, which is a 2D barcode which contains the private key that controls access to this wallet. Now, this particular wallet doesn't have any coins in it. I wouldn't be showing you the private key if it had any coins of mine in it. But this is the experience that you would have. And this is a thing that you can hand out to someone. And in fact, this was handed out at a conference as an example. So this shows how you can take a Bitcoin wallet and encode it as a paper artifact. You could take this thing, I could seal it up, put it in an envelope, and put it in a safe deposit box, and it would be relatively safe there. The fourth way that we can store offline information is to put it in some kind of tamper-proof device, some sort of device that resists tampering. The idea is that we either put the key into the device or the device generates the key, and then the device is designed so that there's no way it will output or divulge the key. The device might sign a statement with the key when we, say, press a button or give it some kind of password, but the device is designed so that it doesn't give out the key. And the advantage of that is that, again, the security of the key is, we hope, as good as the security of the device. And in particular, if we lose the device or if it's stolen, we'll know it. Unlike the theft of information about a key, where we might not know that someone has learned our key, if the key is built into a device and the device can never divulge the key, then if someone has stolen the key, they will necessarily have stolen the device, and we'll know that the device is missing. So this has some advantages as well. Now, in general, people may use a combination of all four of these methods in order to secure their keys. For hot storage, and especially for hot storage holding large amounts of bitcoins, people are willing to work pretty hard and come up with novel security schemes in order to protect them. And we'll talk a little bit about one of those more advanced schemes in the next segment. In segment 4.3, we'll talk about how to share and split keys. Up to now, we've talked about different ways of storing and managing the secret keys that control bitcoins, but we've always put a key in a single place. Whether that's locked in a safe or in software or on paper, it's in one place. And storing the key in one place leaves us with a single point of failure, so that if something goes wrong with that single storage place, then we're in trouble. So here what we'd like to do now is be able to take a key and split it up into pieces and share those pieces around so that we avoid the single point of failure problem. And so we're going to introduce a cryptographic trick called secret sharing. The idea is we're going to take some secret, in our case a secret key, and we're going to divide it up into some number n of pieces. And we're going to do that in such a way that if we're given any k of those pieces, then we'll be able to reconstruct the original secret. But if we're given fewer than k pieces, then we won't be able to learn anything about the original secret. So for example, we might have n equals 2 and k equals 2. That means we're dividing the secret into two pieces, and you need both pieces to put them together. And a specific way of getting n equals 2, k equals 2 secret sharing like this is as illustrated here. That first we're going to generate a number p, which is a large prime number. It doesn't need to be secret or anything, just really big. S is going to be the secret, and the secret has to be between 0 and p minus 1 inclusive. And then we're going to generate a random value r secretly, which is also within the range of between 0 and p minus 1. And now we're going to split our secret into two pieces, x1 and x2. Piece x1 is going to be s plus r modulo p. And remember that modulo is the operation that's sometimes written with the percent sign in programming languages. It just means take this value s plus r and divide it by p and keep the remainder when we do that division. That's s plus r modulo p. So that'll be x1, our first share. And the other share, x2, is going to be s plus 2r modulo p. Okay. And now if we have both of these shares, x1 and x2, we can combine them to reconstruct the secret s. What we do is we compute 2 times x1 minus x2 modulo p. So 2 times x1 is 2s plus 2r, and x2, which we're subtracting off, is s plus 2r. And so we have 2s minus s. That leaves us with an s. We have 2r minus 2r, and so the 2r's cancel out, and we're left just with s mod p, which is equal to s, because s is less than p. And so we can reconstruct the secret in this way. So given two shares, we can reconstruct. But given only one of the shares, it turns out we don't learn anything. And to see why that is, consider x1. We took s, which is the secret, but we added to it a random number, which could take on any value between 0 and p minus 1 with equal likelihood. And if you think about it, you can convince yourself that the result then of s plus r modulo p is equally likely to take on any value between 0 and p minus 1, and that's true regardless of what s was. And so this share by itself just looks like a purely random number and doesn't convey anything about what the value of s might have been. Similarly, this share by itself is also equally likely to take on any value between 0 and p minus 1, and therefore doesn't convey any information about s. So that's n equals 2, k equals 2. Given both shares, we can get back the secret. Given one share, we can't. Okay. Now in general, we can talk about how to get higher values of n and k. For example, let's talk about how to get higher values of n where k equals 2. That is, we're going to want to require two shares to be put together to reconstruct the secret, but we're going to make more than two shares that are eligible for use in this way. And so the way we'll do that is to draw our standard x and y axis here. And we're going to add a point here at 0, s, where s is the secret. And so obviously if somebody can learn what this point is, then they will have reconstructed the secret. Okay, now we're going to draw a line, and we're going to draw a line that has a random slope r. R is going to be generated randomly, and so we get a line like this. And now we can give out shares. The first share is this point here at x equals 1, and y is s plus r. The second share is here at x equals 2, and y turns out to be s plus 2r. The third share is here, x equals 3, and y is s plus 3r, and so on. We can go as far up this line as we want and generate as many shares as we want. Okay, now, if you think about it, you can convince yourself that given any 2 points, you can interpolate and find s, right? That's a property of a line. Given any 2 points on a line, you can interpolate the line. Imagine setting down a ruler that exactly touches, say, these 2 points, and then you can just draw a straight line along that ruler. So given any 2 points, you can reconstruct what this line is. You can see where the line crosses the y-axis. That will be 0, s, and that will give you back the secret. But given just 1 point, you don't really know anything. Because if you have, say, this point, well, the line might be sloped like this, but equally likely it might be sloped like this. It could be sloped any way at all. And so given just this point, you don't really know anything about where this line might cross the y-axis, so you don't know anything about s. And in fact, you can prove that if you do this arithmetic modulo a large prime p, like we did before in the previous slide, that in fact you can prove that any 2 points are sufficient to interpolate and find s, and fewer than 2 points don't tell you anything about s. And so this gives us n equals any value and k equals 2. All right, but now what if we wanted to require more than 2 points? Well, for 2 points we drew a line because any 2 points are sufficient to uniquely specify a line. If we want to require 3 points, what we're going to do is use a quadratic function because any 3 points are sufficient to reconstruct a quadratic function. And so we can use this table to understand what's going on. So if we use the equation s plus rx mod p with the random parameter r, that's the slope that we saw in the previous slide, then you need 2 points to recover s because you need 2 points to interpolate a line. If, on the other hand, if then you use a quadratic, that is s plus some random value r1 times x plus some other random value r2 times x squared, then there are 2 random parameters r1 and r2, and with any 3 points you can uniquely interpolate a quadratic and get back s. And we can just go up the ladder here. If we use a cubic function, there are 3 random parameters. We need 4 points. And in any case, you can generate as many points as you want on the line or the quadratic or the cubic. And therefore, you can get any value of n. And you see how you can get any value of k by just going to higher and higher order polynomials. And so this scheme will let you take any secret and split it into n shares such that k shares or more are needed to reconstruct. And that turns out to be a really useful thing because now you can take a secret key or other secret information and split it up in this way. Support k out of n splitting for any k and n. So let's talk about the good and bad that we get out of this process. The good part is that we can store the shares separately, and the adversary needs to be able to recover k shares in order to get back what the secret was. And that's a good news, right? That means that if we use, say, k equals 3, n equals 4, the adversary needs to break into 3 separate places. And if we're clever about storing those separate shares in places that are far apart and independently secured, then we can make the adversary's job much more difficult. And indeed, if we notice that the adversary has compromised one of those places, we can then race out and try to recover the other shares and address the problem. The other thing that's good about this is that we can afford to lose some of the shares. If we do 3 out of 4 secret splitting, then we can lose 1 share and we'll still have 3 left. And so we can put those 3 remaining ones together and still get back the key. So even though we're spreading out the information, there are more places where information might be lost. We can also tolerate the loss of some of those. In general, we can tolerate the loss of n minus k of them. Now that's the good news. The bad news is that if we take a key and we split it up in this way, and we then want to go back and use the key to sign something, we still need to bring the shares together and recalculate the initial secret in order to be able to sign with that key. And that point where we bring all the shares together and recombine them is still a single point of vulnerability where an adversary might be able to attack us. And that's the bad news. So although this is useful, it's not a panacea, and there's something else that we'd like, which is the ability to generate separate shares and use those shares separately in order to sign. And that's what's behind the concept of multisig that we saw earlier in Lecture 3. So if you recall multisig in Lecture 3, it lets you keep the shares or the different pieces that need to sign a particular transaction apart, and to allow them to approve the transaction separately without needing to reassemble the key at any point. So just as an example of application of that, suppose that Andrew, Arvind, Ed, and Joseph are co-workers. Let's say they're co-founders of a company, and the company has a lot of Bitcoins. Hey, we can dream. Now, what we might want to do is use multisig to protect our large store of Bitcoins. So what we're going to do is have each of the 4 of us generate a key pair, and we're going to, for our company's cold storage, store the coins so that we require multisig with 3 out of the 4 keys signing. Now, the result of that is that we know that we're relatively secure if the 4 of us keep our keys separately and secure them differently, that someone would have to compromise 3 out of the 4 keys, that if some employee or even 2 employees go rogue, those rogue employees can't steal all of the company's coins because you would need a conspiracy of 3 out of 4 to do that. And we also know that if something goes wrong, if one of us loses our key, or if one of us gets run over by a bus and our brain wallet is lost, the others can still get the coins back and transfer them over to a new place. And so multisig allows you or helps you to manage large bodies of cold stored coins in a way that's relatively secure and that requires action by multiple people before anything drastic happens. In segment 4.4, we'll move on to talk about online wallets and exchanges. Thus far, we've talked about ways in which you could store and manage your Bitcoins yourself. Now we'll talk about ways in which you can use other people's services to help you do that. So the first thing you could do is to use an online wallet. An online wallet is kind of like a local wallet that you might manage yourself, except that the information is stored in the cloud. And so you have some kind of, say, web-based interface like this. This is from one called Blockchain, but there are plenty of other online wallet services. You might have a website that you use on your computer. You might have an app that you use on your phone. So it's like a local wallet, but it's in the cloud. It might typically run in your browser, which means the site sends the code that does all of the operations. The site will store your keys. At least it will have the ability to access your keys. Ideally, the site will encrypt those keys under a password that only you know, but of course you have to trust them to do that. You have to trust their code to not leak that key or leak that password. And then of course you would log in order to access the wallet. Okay. So an online wallet has certain trade-offs compared to doing things yourself. One of the big advantages is that it's convenient. You don't have to install anything on your computer in order to be able to use an online wallet in your browser. On your phone, you maybe just have to install an app once. It'll work across multiple devices. You can have one wallet that you access on your desktop and on your phone, and it will just work because the real wallet lives in the cloud. But there are security worries. If the site or the people who operate the site turn out to be malicious or are compromised somehow, now you have to worry about the information of yours that they're storing. You have to worry about the fact that they're supplying code that has its grubby fingers on your Bitcoins. And there are things that can go wrong if there's a compromise or malice at the service provider. Ideally, you would hope that the site or the service is run by security professionals who are better trained or perhaps more diligent than you in protecting the security of things. And so you hope that they do a better job and that your coins are actually more secure. But at the end of the day, you have to trust them and you have to rely that they won't be compromised. Now, another approach, instead of an online wallet, is something that functions rather more like a bank in the real world. And to set context for this, let's talk about how banks or bank-like services operate in the traditional economy. So this is pretty simple, right? You give the bank some money, that's a deposit, and then the bank in exchange promises to give you back that money later. And of course, crucially, the bank doesn't actually just take your money and put it in a box in the back room. All the bank does is promise that if you show up and ask for the money, they'll give it back. The bank will typically take that money, put it somewhere else. They'll invest it or something else like that. The bank will probably keep some money around in reserve in order to make sure that they can pay out the demand for withdrawals that they'll face on a typical day or maybe even an unusual day. And many banks typically use something called fractional reserve, where they keep a certain fraction of all of the demand deposits on reserve just in case. Now, Bitcoin exchanges are businesses that, at least from a user interface standpoint, function in a way that's similar to banks. That is, they accept deposits of Bitcoins. You can transfer your Bitcoins to an exchange, and they will, just like a bank, promise you that they will give them back on demand later. You can also transfer fiat currency, that is, traditional currencies like dollars or euros or similar, into an exchange by doing a transfer from your bank account. And so you can make deposits of both of these sorts of things, and they promise to pay back either or both of them on demand. And what they then let you do is, again, various banking-like things. They let you make and receive Bitcoin payments. You can direct the exchange to pay out some Bitcoins to a particular party, or you can ask someone else to deposit funds into a particular exchange on your behalf, put them into your account. And they also let you exchange Bitcoins for fiat currency or vice versa. And typically the way they do that is they find some customer who wants to buy Bitcoins with dollars and some other customer who wants to sell Bitcoins for dollars, and they try to match them up. That is, they try to find customers who are willing to take opposite positions in a transaction so that there's a mutually acceptable price, and then they will consummate that transaction. Now, it's important to understand what happens if you buy or sell Bitcoins in an exchange. So suppose my account at some exchange starts holding $5,000 and 3 Bitcoins. And I use the exchange, I put in an order to buy 2 Bitcoins for $580 each. And eventually the exchange finds someone who's willing to take the other side of that transaction, and the transaction happens. So the result of that is that my account is different. Now I have 5 Bitcoins instead of 3, and I also have $3,840. That's my $5,000 initial dollars minus $580 each times 2 Bitcoins. That's $3,840. So now that's what's in my account. But the important thing to note here is that when this transaction happened involving me and another customer of the same exchange, that no transaction actually happened on the Bitcoin blockchain. Because the exchange didn't need to go to the blockchain in order to transfer from my account into that other person's account some dollars, or in the other direction some Bitcoins. So all that happens in this transaction is that the exchange is now making a different promise to me than they were making before. Before they said, we'll give you $5,000 and 3 Bitcoins. Now they're saying, we'll give you $3,840 and 5 Bitcoins. It's just a change in their promise, no actual movement of money through the dollar economy or through the Bitcoin blockchain. And of course, the other person has had the exchange's promise to them change in the corresponding opposite way. Now, there are pros and cons to using exchanges. One of the big pros is that exchanges help to connect the Bitcoin economy and the flows of Bitcoins with the fiat currency economy, the dollar and euro and other national currency economy, so that it's easy to transfer value back and forth. If I have an account in an exchange and I have a bunch of dollars and a bunch of Bitcoins, I can trade back and forth between dollars and Bitcoins pretty easily. And that's really helpful. The con is risk, that because an exchange functions in some ways like a bank, that is, that it is accepting demand deposits, that it's accepting payments of money to it in exchange for a promise to pay money back later, that you have the same kinds of risks that you face with banks. And those risks really fall into 3 categories. The first risk is the risk of a bank run. This, of course, is a famous scene from the movie It's a Wonderful Life. Jimmy Stewart is running a credit union, another bank-like business, and all of these people have shown up and they want their money back. This is a bank run. And Jimmy Stewart explains to them, I don't have your money in the back room. I lent out your money to Fred so he could open his hardware store and so on. So one of the risks is that even if the bank is solvent on paper, that you might show up and want your money back, and the bank might be unable to produce it. And there's a danger of a kind of panic behavior where once the rumor starts to get around that a bank or exchange might be in trouble, and they might be getting close to not honoring withdrawals, then people stampede in to try to withdraw their money ahead of the crowd, and you get a kind of avalanche. And that's what Jimmy Stewart was able to stave off with his eloquence in the movie. The second risk is that the owners of the banks might just be crooks. This is Charles Ponzi, inventor of the Ponzi scheme. A Ponzi scheme is a scheme where he would get people to give him money in exchange for wonderful, wonderful profits in the future, only he would actually take their money and use them to pay out the wonderful, wonderful profits to people who bought previously. And so his schemes were always insolvent and were doomed to eventually fail and lose a lot of people a lot of money, which is why he went to prison. And so there's the risk that the people who run the exchange are just crooks. The third risk is the risk of a cyber attack. The risk that someone will manage to penetrate the security of the exchange. Exchanges have large numbers of bitcoins. That means that they store key information that controls large numbers of bitcoins, and they need to be really careful about their procedures and how they manage their cold and hot storage and all of that. And if something goes wrong, if that key information is compromised, if a suitable quorum of employees is compromised, then your money could get stolen from the exchange. And all of these things have happened. We have seen exchanges that failed due to the equivalent of a bank run. We've seen exchanges that fail due to the operators of the exchange being crooks, and we've seen exchanges that fail due to break-ins. And in fact, the studies on this are not encouraging. The best study I think shows that at least as of the time of the study, something like 45% of Bitcoin exchanges had ended up closing due to some failure, some inability to pay out the money that the exchange had promised to pay out. The most famous example of this, of course, is Mt. Gox. Mt. Gox was at one time the largest Bitcoin exchange, and it eventually found itself insolvent. That is, unable to pay out the money that it owed. And Mt. Gox was a Japanese company, and it ended up declaring bankruptcy, leaving a lot of people wondering where their money had gone. Right now, Mt. Gox and the bankruptcy of Mt. Gox is tangled up in the Japanese and American courts, and it's going to be a while, I think, before we know exactly where the money went. The one thing we know is that there's a lot of it, and Mt. Gox doesn't have it anymore. So this is a cautionary tale about the use of exchanges. Now, connecting this back to banks, we don't see a 45% failure rate for banks in most developed countries. And the reason for that partly is because of regulation. For traditional banks, government regulates in various ways. The first thing that governments do is they often impose a minimum reserve requirement. In the US, this is typically 3 to 10% of demand deposits a bank is required to have in liquid form so that it can deal with the surge of withdrawals if that happens. Second, the regulators often regulate the types of investments and money management methods that banks can use to make sure that the bank's assets are invested in places that are relatively low risk, because those are really the assets of the depositors in some sense. Now, in exchange for these forms of regulation, governments typically do things to help banks or at least protect their depositors. First, governments will issue deposit insurance. That is, that they'll tell depositors that if you deposit your money in a bank that follows these rules, then we, the government, guarantee that if the bank goes under, we will make good on at least part of those deposits for you. And the other thing that governments sometimes do is act as a lender of last resort. And what that means is that if a bank gets itself into a tough spot, but it's basically solvent, that the government may step in and loan that bank money in order to tide it over until it can move money around as necessary to get itself out of the woods. So traditional banks are regulated in this way. Bitcoin exchanges are not. The question of whether or how Bitcoin exchanges or other Bitcoin businesses should be regulated is a topic that we'll come back to in Lecture 7. Now, there is one interesting thing that a Bitcoin exchange or somebody else who holds Bitcoins can do, which relies on some cryptographic tricks to give users or customers some amount of comfort about where the money went or where the money is that those people deposited into the Bitcoin business. And that's what's called a proof of reserve. So let me explain how that works. The goal here is that a Bitcoin exchange or some other business that's holding Bitcoins can prove that it has a fractional reserve. It can prove that we have at least, let's say, 25%, or maybe that we have 100% of the deposits that people have made with us available and under our control if need be. And so the way that proof of reserve works is you break the problem into two pieces. First, you prove how much reserve you're holding. That's the relatively easy part. So the company publishes a valid payment to self transaction of that amount. That is, if they claim to have 100,000 bitcoins, they create a transaction in which they pay 100,000 bitcoins to themselves and show that that transaction is valid. Then they sign some challenge string, that is some random string of bits that was generated by some impartial party, and they sign that challenge string with the very same private key that was used to validate that payment to self transaction. That proves that someone who knew that private key was participating in this proof of reserve. Now, strictly speaking, that's not a proof that the party who's claiming to own the reserve owns it. All this proves is that whoever does own that 100,000 bitcoins is willing to cooperate in this process. But nonetheless, this looks like a proof. This looks something like a proof that somebody controls or knows someone who controls the given amount of money. So the first piece is to prove how much reserve you have. And the second piece is to prove how many demand deposits the group holds. And if you can prove those two things, then somebody can simply divide those two numbers, and that's what your fractional reserve is. One more thing to note before we go on and talk about how you prove how many demand deposits you hold, that's the tricky part, is that in proving how much reserve you're holding, you could underclaim. That is, the organization might have 150,000 bitcoins, but choose to make a payment to self of only 100,000. And so this proof of reserve doesn't prove that this is all you have, but it proves that you have at least that much. Okay. Now, how do you prove how many demand deposits you hold? In order to do that, we're going to use a trick that relates to the Merkle trees that we talked about in lecture 1. And if you recall, a Merkle tree is a binary tree that's built with hash pointers, so that each one of these pointers not only says where we can get a piece of information, but also what the cryptographic hash of that information is. Now we're going to add to each one of these hash pointers another field or attribute. So we're going to add to each hash pointer a total value, that is a total monetary value in bitcoins of all of the things that are underneath that hash pointer in the tree. So for example, this hash pointer here would be tagged with the total value in this entire left subtree. Right? Now down here at the bottom, we're going to have one item for each user's or customer's account. And we're going to combine these up the tree so that each node, the hash pointer coming out of it, will be labeled with the sum of the values on the two hash pointers down below. So that will be a valid total for the subtree. So we can construct that structure, and then the exchange that wants to do the proof of reserve can cryptographically sign the root hash pointer here, which is making a claim that this is a valid tree and that everybody is down here. Okay. Now each customer can then go to the organization and they say, okay, prove it to me. If this is prove that my account is included in your tree. And so I can go to the exchange, I can make that demand, and they can show me this partial tree. I can see that up here that the hash pointer is the same hash pointer that they signed. I can see that the hash pointers are consistent all the way down, and that is that the hash stored in this hash pointer actually is the hash of the cryptographic hash of this node, and so on for each hash pointer all the way down. And so just like with the Merkle tree, that proves that my account here was in the tree that they initially committed to. I also am going to verify that the amounts in the hash pointers add up all the way down. So for example, the total value in this hash pointer adds up to the same total as this hash pointer plus this hash pointer, which is included in this node. And I make sure that on this path down to my account, that the totals add up all the way. Now, if you think about it, if everybody does this, if everybody makes a demand to see their own account, then every branch of this tree is going to get explored, and someone is going to verify that for every node in the tree, that the value of the hash pointer pointing to that node is equal to the sum of the value on these two children. And so if everyone does this, then they will collectively prove over the whole tree that the values are added correctly going up the tree. Okay, so this is the scheme that first the exchange builds a tree like this that includes all their customers' accounts at the bottom and sums the total values going up the top. Then all customers, or really realistically those customers who are willing to go to the trouble, demand to see the partial subtree that includes their account and verify that everything adds up. And if that works, then we can believe that the organization is correctly reporting all of the accounts that they have. Or actually, to be a little bit more precise, they can claim to have more accounts than they really have. All they're proving is that every actual account appears somewhere in the tree. Now let's review. So first, they've proven that they have at least X amount of reserve currency by doing a self-transaction of X amount. Then they've proven that their customers have at most an amount Y deposited. And of course, they can claim that in the other direction as well. So what that means is that the reserve fraction is, if they report it exactly accurately, it's X over Y. If in fact X is larger, then the reserve fraction is larger than they're claiming. Or if Y is smaller, then the reserve fraction also, because this is in the denominator, is also larger than they're claiming. And so when they prove an X and prove a Y this way, you can guarantee that the actual reserve fraction they're holding is at least as big as what they're claiming. And therefore they can prove a reserve to you. And what that means is that if a Bitcoin exchange wants to prove that they hold 25% reserves on all deposits, or 100%, they can do that in a way that's independently verifiable by anybody, and no central regulator is required. So that's an aspect of regulation that Bitcoin exchanges can prove voluntarily, but other aspects of regulation, as we'll see in a later lecture, are harder to guarantee. In segment 4.5, we'll talk about payment services. Thus far, we've talked about how you can store and manage your Bitcoins. Now we're going to talk about how a merchant can accept payment in Bitcoins in a practical way. So the scenario here is that we have a merchant. Maybe it's an online seller of some kind of goods or services. Maybe it's a local retail merchant, and they want to be able to receive payments in Bitcoins. Now, the reason they want to be able to receive payments in Bitcoins, let's say, is not that the merchant is so excited about Bitcoins, but simply because their customers want to be able to pay in Bitcoins. What the merchant wants is to receive dollars or local fiat currency, whatever that is, at the end of the day. They want to have some way of receiving payments in Bitcoins which is easy for them to deploy, so they don't have to worry a lot about technology, changing their website, or building some kind of point of sale technology. And they also want low risk. There are various risks associated with receiving payments in Bitcoins, and the merchant doesn't want to have to worry about those. So they don't want to have to worry about technology risk. That is, the risk that by changing their technology, something will go wrong, their website will go down, something will malfunction, and that will cost them money. They don't want to deal with the security risks of handling Bitcoins, the possibility that someone will break into their hot wallet, or some employee will make off with their Bitcoins. And they don't want to deal with the exchange rate risk, that the value of a Bitcoin in dollars may fluctuate from time to time, and the merchant who might want to sell a pizza for $12 wants to know that they're going to get $12 or something close to it, and that the value of the Bitcoins that they received in exchange for that pizza won't drop drastically before they can get it, before they can exchange those Bitcoins for dollars. So the merchant wants to be isolated from all of that. And so the reason that we have payment services is fundamentally to allow both of these parties to be happy and get what they want, while someone else takes care of bridging the gap between these different desires. So the process by which a merchant might arrange to accept Bitcoin payments on their site through a payment service would work something like this. The merchant would first go to the payment service's website, and they'd fill out a form that looks something like this. This particular form comes from a service called Coinbase. And so the merchant says, all right, I want to display a button on my web page. I want it to be a buy now button. I want the button to look like this. Here's the name of the item that is being bought. Here's the sale price amount, which can be in either Bitcoins or dollars or some other currency. And then here's where the funds should be sent when the customer buys. The merchant then, having filled that out, presses this button to generate button code, and out will come a bunch of HTML code that the merchant can just drop into their website. The merchant will put that into their website, and what will appear on the website to the customer will be a button that looks like whatever they chose. When the customer pushes that button, then a bunch of payment magic will happen, and the merchant will eventually get a confirmation saying that, yeah, a payment was made by this customer for alpaca socks in such and such amount. So the way that actually works, or one typical way that the mechanism might work for a payment, is illustrated here. Here we have down at the bottom a user who wants to buy something from the merchant who's up here, and we have over here the payment service. Okay, so the user goes to the merchant's website, they shop, they pick out an item they want to buy, and when it comes time to pay, the merchant will deliver a web page which will contain the Pay with Bitcoin button, and it will contain some other information. It will contain a transaction ID, that is some identifier that is meaningful to the merchant in their own accounting system, along with an amount that they want to be paid. And this will basically be the magic HTML code that was provided earlier by the payment service. The user, if they want to pay with Bitcoins, will click that button. That will cause information to be sent to the payment service as an HTTP or HTTPS, ideally, request, which says that that button was clicked. Here's the transaction ID from the merchant. Here's the amount. And of course, the identity of the merchant is implicit here. When that happens, now the payment service knows that this customer, whoever they are, wants to pay a certain amount of Bitcoins. And so the payment service will pop up some kind of a box or do some kind of an interaction with the user, in which the user will receive information about how to pay, and the user will then initiate a Bitcoin transfer to the payment service. Once the user has created that payment, then the payment service will send back information. It might be a redirect of some kind, maybe an HTTP redirect or something else that comes back to the user's browser and causes the user's browser to send a message on to the merchant from the payment service saying, it looks okay so far. And then later, the payment service will directly send a confirmation saying that yes, in correspondence with this transaction ID that you, the merchant, created, the following amount was spent, that this is fully confirmed in the Bitcoin blockchain, and the payment service will confirm that it's giving you the money at the end of the day. So once that happens, now the merchant knows that the payment is confirmed, and they can go ahead and allow whatever the item is that this user bought to be shipped out to the user. And then the user will eventually get the item, and everyone is happy. So this is a typical kind of flow. The details of the flow might work a little differently depending on which payment service you're using, but that's the idea. From the merchant standpoint, what happens is they include this blob of HTML in their website, that eventually they get this tentative okay, things are going ahead, and eventually a firm confirmation from the payment service. They use this transaction ID to match up the purchase of this particular Snuggie by this particular user in their accounting system, and they use the confirmation to know they got paid. And now the final step is the one in which the payment service actually gives money to the merchant. Okay, so the end result of this whole process is the following: that the customer pays Bitcoins, some number of Bitcoins, that the merchant gets dollars. That's what the merchant wanted. They wanted to sell that item for a particular number of dollars or whatever their local fiat currency is. The merchant gets the number of dollars they asked for minus a small percentage. The payment service is going to take a small percentage as a fee, maybe a couple of percent. And the payment service does everything else. The payment service receives the Bitcoins that the customer paid. It pays out the dollars. Maybe at the end of every day, it makes a deposit into the merchant's bank account of all of the payments that came in that day. And of course, it keeps a small percentage, and that's how it makes its profit. And the payment service absorbs all of the risks involved in this process. It absorbs the security risk, so it has to have good management of the Bitcoins, of its cold storage and all of that. It absorbs the exchange rate risk because it's receiving Bitcoins and paying out dollars. If the price of dollars against Bitcoins fluctuates wildly, the payment service might be unhappy. Then again, if it fluctuates wildly in the other direction, the payment service might be happy. But that risk, that uncertainty is part of, and absorbing it is part of what the payment service does. One thing to note here is that the payment service, if it's operating at large scale, is receiving large numbers of Bitcoins and paying out large numbers of dollars. And therefore, it's going to have a constant need to exchange the Bitcoins it's receiving for more dollars so that it can keep this whole cycle going. And so a payment service is going to be an active participant in the exchange markets that link together, in this case, the dollar economy and the Bitcoin economy. And that's another thing that they need to worry about, not just what is the price of exchange, but how can we manage to exchange currency in this large volume. But in exchange for doing all of this stuff, the payment service gets their fee. And so this is potentially a lucrative business because it solves the mismatch between the customer's desire to pay Bitcoins and the merchant's desire to just get dollars and concentrate on selling goods. In segment 4.6, we'll talk about transaction fees. This is a topic that has come up before in a previous lecture, and it will come up again later in a later lecture. And transaction fees are one of the bits of how the engine room of Bitcoin works, if you will. And it touches a bunch of different topics. So what I want to talk about here today is the practical details of how transaction fees are set in Bitcoin today. We've talked about storage in this lecture. We've talked about payment services. We've talked about exchanges. But bottom line is, whenever a transaction is put into the Bitcoin blockchain, that transaction might pay transaction fees. Now recall from a previous lecture that a transaction fee is just defined to be the difference between the total value of coins that go into a transaction minus the total value of coins that come out. The inputs have to be always at least as big as the outputs because a regular transaction can't create coins. But if the inputs are a little bigger than the outputs, then the difference is deemed to be a transaction fee. And that transaction fee goes to the miner who recorded this transaction, the miner who made the block that records this transaction. The economics of transaction fees are interesting, and we'll come back to this in a later lecture. But what I want to talk about today is how transaction fees are actually set in Bitcoin as it operates as of the time of this filming. These things do change from time to time, but we'll give you a snapshot of what's going on right now. Okay, so why are transaction fees exist at all? Well, the reason is that there's some cost that someone has to incur in order to relay your transaction. The nodes in the Bitcoin peer-to-peer network need to relay your transaction, and ultimately a miner needs to build your transaction into their block, and it costs them a little bit of computational effort to do that. And the time that they spend calculating a block that's slightly larger because it contains your transaction is time that they could otherwise have spent trying to make a block and get a block reward. So there is a cost both to the peers in the peer-to-peer network and to the miners of incorporating your transaction. So the idea of a transaction fee is to somehow compensate people for those costs that they incur because your transaction exists. Generally, you're free to set the transaction fee to whatever you want it to be. You can pay no fee or you can pay a high fee. But as a general matter, if you pay a higher transaction fee, it's natural that your transaction will be relayed and recorded more quickly and more reliably. Okay. So the current consensus transaction fees are as follows. First of all, no fee is charged if the transaction is less than 1,000 bytes in size, in total size, if all of the outputs of the transaction are 1/100th of a Bitcoin or larger. That's currently worth about $5 or $6 US, and if the priority of the transaction, according to a certain formula, is large enough. The priority formula works like this. You look at all of the inputs to the transaction, and for each one you add up the product of the age of that input times the value of that input in Bitcoins. You add that up over all the inputs, then you divide by the transaction size. So if you meet these three requirements, then no fee will typically be charged, and your transaction will be relayed, and it will be recorded in the blockchain without a fee. Otherwise, a fee is charged, and that fee is about 0.0001 Bitcoins per 1,000 bytes. And that's a fraction of a US penny per 1,000 bytes. Now, just as an aside, the approximate size of a transaction based on the number of inputs and the number of outputs is about 148 bytes per each input, plus about 34 bytes for each output, plus about 10 bytes for other information. And so a transaction that's of small size has maybe 2 inputs and 2 outputs. Its size would be 400 to 500 bytes. All right. Now, the current status quo is that most miners enforce the consensus fee structure, which means that they will either not service or will service last transactions that don't meet the consensus fee structure. So if you don't pay the consensus fee, your transactions will typically take longer to be recorded. It's worth noting that if you pay a small fee, that because of the way the priority calculation works, the priority includes age of your Bitcoins. The longer your transaction sits without being recorded, the higher its priority will get because its Bitcoins get slowly older. But in any case, if you haven't paid the consensus fee, your transactions will probably take longer to find their way into the blockchain. Maybe that's okay with you. Most miners prioritize transaction based on the fees that are paid and based on the priority formula. And I'm not going to go into the details of how that works, but if you pay more or if your priority is higher, according to the formula, then your transaction probably gets memorialized first. Now finally, I said this was the consensus and that most miners do it. But in fact, there are other miners who don't enforce these rules and who will record and operate on a transaction even if it pays a smaller fee or no fee at all. So if you make a transaction that doesn't meet the fee requirements, it will probably find its way into the blockchain anyway. But the way to get your transaction recorded more quickly and more reliably is to pay the consensus fee. And that's why most wallet software and most payment services include the consensus fee structure in the payments that go on. And so you'll see a little bit of money raked off for transaction fees when you engage in everyday Bitcoin business. In segment 4.7, we're going to look at currency exchange markets. That is, markets on which you can trade Bitcoins against fiat currencies like dollars and euros, etc. We've talked earlier about Bitcoin exchanges and other types of businesses that are involved in trading between Bitcoins and fiat currencies. But now we want to look at this as a market. We want to look at the size of it, the extent of it, and how it operates, and we'll look a little bit at the economics of this market. The first thing to understand about this, if you're new to it, is that it operates in many ways like the market between two fiat currencies, like the market between dollars and euros. The price will fluctuate back and forth depending on how badly people want to buy euros versus how badly people want to buy dollars on a particular day. So in the Bitcoin markets, we can look at data. And in fact, there are sites like Bitcoin Charts. This is the Bitcoin markets page on Bitcoin Charts, which shows exchanges that trade dollars against Bitcoins. And you can see there's a list of different exchanges or different places where you can trade dollars against Bitcoins here, from top to bottom. Up here at the top, we have Bitstamp, which on this particular day had the highest volume. For each one, there's the current price. For Bitstamp, on the day I took this screenshot, it was $582.54. You can get graphs, you can look at the average, the volume, etc. You can look, the 24-hour average price was $585. The volume was about 6,100 Bitcoins, or about $3.6 million over the previous 24 hours. So you can see there's a lot of trading here. And if you go to this site live, you can see the prices move in real time as trades get made. So this is an active market, it's a liquid market, and there are plenty of places you can go to buy or sell Bitcoins. Another place you can go besides an online exchange, if you want to buy or sell Bitcoins, is that you can use sites that help you meet people to trade Bitcoins in real life. So here I went to localbitcoins.com. It's an example. I said I want to buy Bitcoins in Princeton, New Jersey, United States, and it gave me a bunch of results. A bunch of people who on this particular day were willing to sell me Bitcoins for what price and for how many. And so I could then contact these people. I could arrange to meet them at a coffee shop somewhere or in a park or wherever it is, and I could give them dollars, and in exchange they would give me Bitcoins. And so this is another way to do it. You can just find a person near you, or you can find somebody you know. The very first Bitcoins I bought from one of my students who owned some Bitcoins. I just gave him some dollars, and he paid some Bitcoins into my digital wallet. Another thing you can do is you can go to a physical place. There are some places in the world, or some regular meetups, where it's known that people go to trade Bitcoins. And so you can go to a certain park, a certain street corner on a particular day, and you know that there will be people standing around wanting to buy or sell Bitcoins, and you can do business with them. And here you see a bunch of people at one of these meetups looking at their phones with their apps to transfer or verify transfer of Bitcoins. And so these are all the ways that you can trade, or the popular ways that you can trade Bitcoins against dollars. Okay, now this is a market, as I said. And the market matches buyers who want to do one thing with sellers who are willing to do the opposite thing. It's a relatively large market, meaning millions of US dollars per day pass through it. It's not like the New York Stock Exchange, or it's not like the dollars to euros market, which is vastly larger. But it's relatively large so that there is a notion of a consensus price, and that a person who wants to come into this market to buy or sell a modest amount at least will always be able to find a counterparty. The price of this market, this consensus price, like the price of anything in a liquid market, will be set by supply and demand. That is, what is the supply of Bitcoins that might potentially be sold, and what is the demand for Bitcoins by people who have dollars. The price through this market mechanism will be set to the level that matches supply and demand. But let's dig into that a little bit more. First of all, let's talk about what is the supply of Bitcoins. The supply of Bitcoins, that is the Bitcoins that you might possibly buy in one of these markets, is first of all equal to the supply of Bitcoins that are in circulation. Currently, Of course, there's a fixed number of Bitcoins in circulation. At the time of this filming, it's about 13.1 million. And the rules of Bitcoin as they currently stand say that this number will slowly go up and hit a limit of 21 million eventually. But you might also sometimes include demand deposits of Bitcoins. That is, if someone has put money into their account in a Bitcoin exchange, and the account doesn't keep a full reserve to meet every single deposit, then you'll have demand deposits at that exchange that are larger than the number of coins that the exchange is holding. And depending on exactly what question you're asking about the market, it might or might not be correct to include demand deposits in the supply. So when should you include demand deposits? Well, basically, you should include demand deposits in a market analysis when demand deposited money can be sold in that market. So for example, if you're talking about exchange of dollars for Bitcoins that can happen in an exchange, if I have Bitcoins demand deposited in an exchange, I can trade those for dollars. And so if that's the scenario you're looking at, it would make sense to include demand deposits in that exchange as part of the supply. It's worth noting as well that when economists conventionally talk about the supply of a fiat currency, they typically include in the money supply not only the currency that's in circulation, that is the actual paper and metal money, but also the total amount of demand deposits. And that's for the logical reason that people can actually spend their demand deposited money to buy stuff. And so although it's tempting to say that the supply of Bitcoins is fixed at 13.1 million currently or 21 million eventually, for some purposes we have to include demand deposits where those demand deposits function like money. And so the supply might not be fixed in the way that some Bitcoin advocates claim. And we need to look at the circumstances of the particular market we're talking about in order to understand what the proper money supply is. But let's assume we've agreed on what supply we're using based on what market we're analyzing. Let's now look at demand. There are really two main sources of demand for Bitcoins. There's demand for Bitcoins as a way of mediating fiat currency transactions, and there's demand for Bitcoins as an investment. So first, let's look at mediating fiat currency transactions. So here's the scenario. Imagine that Alice wants to buy something from Bob or wants to pay some money to Bob. And Alice and Bob want to transfer, let's say, a certain number of dollars. But they find it convenient to use Bitcoin to do this transfer. Perhaps they're at a distance. Alice wants to be able to email the money to Bob. Perhaps they like the fact that they can have very low transaction fees in Bitcoin and lower than some other service. Whatever the reason, they want to use Bitcoins to mediate this transaction. So the way that works is this, that first Alice buys Bitcoins for dollars. Alice then sends those Bitcoins to Bob as a Bitcoin transaction. Once that transaction is recorded in the blockchain and it's confirmed to Bob's satisfaction, Bob will sell those Bitcoins for dollars and get the dollars back. So Alice starts by putting in dollars, Bob ends by getting out dollars. But the key thing for the purpose of Bitcoin demand is that the Bitcoins that are mediating this transaction that are bought by Alice in step 1 and sold by Bob in step 3 have to be taken out of circulation, and they're devoted to serving this transaction during the time that the transaction is going on. And that creates a demand for those Bitcoins. If there are a lot of people who want to mediate transactions like this, whether those are fiat currency transactions or other transactions, if they want to mediate transactions, that will generate demand for Bitcoin. So that's the first source of demand. The second source of demand is that Bitcoin is sometimes demanded as an investment. That is, somebody wants to buy Bitcoins and hold them in the hope that the price of Bitcoins will go up in the future and that they'll be able to sell them. So to the extent that people are buying and holding those Bitcoins are out of circulation, but there's a demand to buy Bitcoins, at least depending on the price. When the price is low, you might expect a lot of people to want to buy Bitcoins as an investment. But if the price goes up very high, then the demand for Bitcoins as an investment won't be as high. So that's the second source of demand. Now, we can do some simple economic modeling to understand how these markets will behave. And I'm not going to do a full model here, although that's an interesting exercise. What I want to do is look specifically at the market at the effect of this transaction mediation demand and what effect that might have on the price of Bitcoins. And we can build a simple model for doing that. So here's a simple model of the demand that's driven by transactions by transaction mediation and what it tells us about what the price should be. So we're going to assume some parameters here. First, we're going to say T is equal to the total transaction value that's going to be mediated via Bitcoins by everyone who's participating in the market. And that's going to be measured in dollars per second. We're going to assume for simplicity that the people who want to mediate these transactions have in mind a certain dollar value of the transactions. Or if it's some other fiat currency, we'll translate it into dollars for simplicity. So there's a certain number of dollars per second of transactions that need to be mediated. We're going to say D is equal to the duration of time that Bitcoins need to be held out of circulation in order to mediate a transaction. That's the time from when the payer buys the Bitcoins to when the receiver is able to sell them back into the market, and we'll measure that in seconds. And then S is going to be the supply of Bitcoins that are available for this purchase. And so that's going to be all the Bitcoins that exist, that is all of the hard currency Bitcoins, all of the 13.1 million or eventually up to 21 million Bitcoins, not including those that are held out by people as long-term investments. So at any point in time, there's some supply of Bitcoins that are sloshing around and available for this purpose. Okay, and now we can do some calculations. The first thing we'll do is we'll calculate how many Bitcoins become available in order to service transactions per second. Well, there are S Bitcoins in total that are used, and because they're available because they're taken out of circulation for a time of D seconds, then every second about 1/d fraction of those Bitcoins will become newly available because they'll emerge from that out of circulation state. And so on average, S/D Bitcoins will become available for mediating transactions every second. That's the supply side. On the demand side, the number of Bitcoins per second that are needed to mediate transactions, well, we have T dollars worth of transactions to mediate. And in order to mediate $1 worth of transaction, we need 1/p Bitcoins. That is, we need to take this T, which is measured in dollars per second, and divide it by the price in dollars per Bitcoin, and the result we get is Bitcoins per second. These are the number of Bitcoins per second that are needed in order to serve all the transactions that people want to serve. Okay, so if you look at a particular second of time, for that second, there's a supply of Bitcoins of S/D, and there is a demand of T/P. And now, if you think about the dynamics of this market, it behaves like many markets, in that the price will fluctuate in order to bring supply into line with demand. If the supply is higher than the demand, then there are Bitcoins that are going unsold. And so the people who are selling Bitcoins will be willing to lower their price to try to sell those Bitcoins. And so the price will come down if supply is higher than demand. And when the price comes down, that will cause demand actually to go up because P, the price, is in the denominator of demand. So if supply is bigger than demand, then demand will be pulled up. On the other hand, if demand is higher than supply, that means that there are people who want to get Bitcoins to mediate a transaction who can't get them because there aren't enough Bitcoins around. And so those people will bid more in order to get their Bitcoins. They'll have to bid more because there'll be a lot of competition for the limited supply of Bitcoins. And so if the demand is higher than the supply, the result is that price will go up. And when price goes up, then because price is in the denominator of the demand, that means demand will come back down. Demand for Bitcoins will come back down as the price goes up. So if you have supply here and demand here, then the demand will be pulled down toward the supply. Right? And so if the supply is at some point, that the demand, we've argued, will always be pulled toward the supply. And in fact, the two will come into equilibrium. And so the equilibrium condition, the point where you'll end up in this market, is where this supply, S/D, is equal to the demand, T/P. And so if you set those two expressions equal to each other, and then you solve for P, the price, what you get is this, that in equilibrium, the price should be equal to T times D divided by S. All right, so what does this mean? Well, one thing we can conclude about this is that if you think of D as being, D, the duration, as not changing, because probably the duration that you need to hold a Bitcoin to do a transaction is not going to change. So if D doesn't change, and if S, the supply, is not changing, then what this tells us is that the price is going to be proportional to the demand for transaction mediation as measured in dollars. And so if the demand for transaction mediation in dollars doubles, then the price of Bitcoins should double. And we could in fact graph the price against some estimate of the demand for transaction mediation and see whether they match up. And when economists do this, they do tend to match up pretty well. So we could graph the price of Bitcoins against the demand for transaction mediation as you can best estimate it in dollars per second. And those things should tend to be proportional over time. And when economists do that, they do tend to match up pretty well. The other thing we can note is that supply is in the denominator here, and that supply includes only the Bitcoins that aren't being held as investments. And so what that tells us is if more people are buying Bitcoin as an investment, the result will be that coins are withdrawn from this status where they're available to mediate transactions, and so the S that we're using here will go down. So that if investors are buying a lot of Bitcoins, it will drive down S, and therefore P will go up. And so that makes sense. If there's more demand on the investment side, then the price that you need to pay to mediate a transaction will go up. Right? Now, this is not a full model of the market. In order to have a full model, we need to take into account the activities of investors. We need to bear in mind that investors will demand Bitcoins when they believe that the price will be higher in the future. And so we need to think about investors' expectations. And investors' expectations, of course, have something to do with what is the expected total transaction value demand in the future. And we could build a model that's more complex. I'm not going to do that here, but you get a flavor of the kind of thing that you can do. So the bottom line here is that there is a market between Bitcoins and dollars, or Bitcoins and other fiat currencies, that market has enough liquidity that you can buy or sell in modest quantities in a reliable way, although the price does go up and down, and that it's possible to do economic modeling and get some idea of how supply and demand interact in this market and predict what the market might do, as long as you understand unknowable things like how much are people going to want to use Bitcoin to mediate transactions in the future. That kind of economic modeling is important to do and very informative, and I'm sure that there are people who are doing it in some detail today. But a detailed economic model of this market is beyond the scope of this course.
All right, welcome to the 5th lecture on Bitcoin. Today is going to be all about mining. So to recap, what have we learned about the miners so far? Well, we've heard about the miners quite a bit, and we know that Bitcoin depends on the miners pretty heavily to perform a couple of important roles. Of course, they validate every transaction, they build all the blocks, and we know that the miners earn some reward. Who are the miners? How did they get into this? How do they operate? What's the business model like for miners? What impact are they having on the environment? We're going to get to all those questions in today's lecture. So we'll start by talking about what Bitcoin miners actually have to do in order to be miners. And maybe before we get into that, we'll talk about some historical miners. So if you're thinking about becoming a Bitcoin miner, I wouldn't want to completely discourage you, but I'd be remiss not to tell you that this is not a get-rich-quick scheme. This is a very long haul. So looking back at some historical gold rushes, they're full of stories of young people rushing off hoping to find fortune, a lot of them losing everything that they have, some of them making it really striking it rich, but a lot of hardship along the way. This is probably my favorite example from the Klondike Gold Rush in Alaska in 1898. This gold rush all happened within a matter of 6 months, so there was a huge rush to get there for the one summer mining season. And all of these people are trudging up this snowy mountain pass with all of their equipment at the same time. Doesn't look like the easiest way to get rich, and I'll argue that Bitcoin mining is starting to look like a similar proposition. So what do you have to do to be a Bitcoin miner? In 6 easy steps? Well, you join the network, you become a Bitcoin node, you listen for all of the transactions that people are broadcasting. Of course, you have to validate them. You listen for new blocks that people have found, you maintain a view of the current blockchain. Of course, you want to validate all the blocks and all the transactions that are in those blocks. You start to assemble new valid blocks based on the transactions that you're hearing. Then you have to work really hard in step 4 here to find a nonce that will make your block considered valid. That's the really difficult computational step where all of the difficulty really happens for the miners. Finally, if you're lucky enough to find a block, you have to hope that all of the other miners accept your block, that they validate it and start mining on top of it, and that they don't accept some competitor's block instead. And if all of that happens, in step 6, you finally get to profit, currently to the tune of over 25 bitcoins per block, worth about $15,000 US. And so a couple of these steps, all of the validation in particular, are what's actually useful to the Bitcoin network. So that's why we have mining at all. Miners perform this validation step. The rest of it, the profit and the race to find blocks, that's all just incentive to encourage the miners to do the validation which is necessary for Bitcoin to function as a currency. So what does the process look like for finding a valid block? Well, we'll have to look back to the data structure that we introduced 2 lectures ago and recall that there are 2 main hash-based data structures here. There's the blockchain, where each block header points to the previous block header in the chain. And then within each block, there's this Merkle tree, this hash-based binary tree of all of the transactions included within that block. So the first thing that you do as a miner is you assemble all of the transactions that you have from your pending transaction pool into this tree. You create a block with the right header that points to the previous block. And then you have to start searching over this nonce field to try to have the hash of the block header start with the required number of zeros. So you may start with a nonce of all zeros. That's a 32-bit integer. And when you try that, you'll get a hash that's incorrect. So you'll say, okay, let's move on to the next nonce number 1. The hash is also incorrect. Step forward one more time, try hash 2, also incorrect. So you can see where this is going. And in a lot of cases, you'll try every single possible value for that 32-bit integer, and in no case will the hash be correct. So at this point, you're going to have to make further changes. And you'll notice that there's this parameter in the Coinbase transaction. And remember that the Coinbase transaction is where the miners are actually minting new coins and claiming them for themselves. There's also this extra nonce parameter in there. So after you've exhausted all possible nonces in the block header for the extra nonce in the Coinbase transaction of all zeros, you'll step the extra nonce in the Coinbase transaction up to 1, and then you'll start searching nonces in the block header once again. And it's important to realize that when you change that one parameter in the Coinbase transaction, the entire Merkle tree of transactions has to change. So that change will propagate all the way up. Changing the extra nonce in the Coinbase transaction is much more expensive than changing the nonce in the header for that reason. So you do that as the outer loop, and the inner loop where you're really working hard is changing the nonce in the block header. Okay, but once again, our first try didn't work here, so we'll have to keep stepping that nonce. And again, this is a really difficult computation, so the vast majority of nonces that you try aren't going to work. But eventually, if you stay at it long enough, you'll find the right combination of the extra nonce in the Coinbase transaction and the nonce in the header, and you'll find a block with a hash that starts with enough zeros to be considered valid. And this is when you want to announce it as quickly as you can and hope that you can profit from it. So I said it was difficult. Exactly how difficult is it? Well, as of today, this is the mining difficulty target. So the hash of any valid block has to be below this value here. And this is a 256-bit hash output. We're using SHA-256, the hash function, which is appropriately named. It's 256 bits. Currently, at least the first 64 bits of the hash of any valid block have to be set to 0. Overall, the current difficulty is about 2 to the 66, which is a really huge number. If we try to write it out in decimal, that's what we get. That's 84 quintillion. And this number is so big, it's difficult to even imagine. One approximation for it that you can think about is it's about the population of the Earth squared. So basically, if every person on Earth was themselves their own planet Earth with 7 billion people on it, the total number of people would be close to this number. Or another way to think about it is that if all 7 billion people on Earth shook hands with each other, fewer than 2 to the 66 total handshakes would have to take place. So this is an incomprehensibly huge number. So where did this number come from? How is the mining difficulty set? It's actually chosen again every 2 weeks based on how efficient the miners were over the previous 2 weeks. So you simply take the amount of time that it took the miners to find the previous 2016 blocks, and you divide that amount of time by 2 weeks, and then you multiply that ratio by whatever the previous difficulty value was to get the next difficulty value. So you're just scaling it to keep a constant property true, which is that blocks should be found by the network on average about once every 10 minutes. That's the fixed constant that was chosen at the beginning of time for Bitcoin, and every 2 weeks the difficulty is reset to ensure that that property is maintained. So you can see that over time the mining difficulty keeps increasing. It's not necessarily a steady linear increase or an exponential increase. It depends on activity in the market, how many new miners are getting into the game, which may be affected by the current exchange rate of Bitcoin. But generally, more and more hash power comes online, more people are hashing, blocks are found faster, and the difficulty is adjusted up so that it again takes 10 minutes to find blocks. And you can see that in the red line on the graph here. There's a step function of difficulty. Even though the overall network hash rate is growing smoothly, because you only reset every 2 weeks, the difficulty steps up. Another way to view this is to look at how long it takes to find a block on average. So here you can see a graph of over time how many seconds elapse between consecutive blocks in the blockchain. And you can see that this gradually goes down, and then it jumps up again, and then gradually goes down. And of course, what's happening there is that every 2 weeks the difficulty resets, and the average block time goes back up to about 10 minutes, and then more and more power goes online. The difficulty stays the same, so the miners are finding blocks faster and faster. And then 2 weeks pass, the difficulty resets back up to 10 minutes, and the process starts all over again. So in actuality, even though the goal was for a block to be found every 10 minutes, on average it's more close to about every 9 minutes, and at the end of the 2 week cycle it will get down to about every 8 minutes. All right, now we're going to talk about what hardware miners use to achieve this computation, which I've just spent time telling you is really, really difficult to do. So first of all, what exactly is this computation? So we've mentioned hash functions and we've mentioned SHA-256 in particular. What exactly is SHA-256? Well, it's a general purpose cryptographic hash function. It's actually part of a bigger family of functions that was standardized in 2001. It did come out of the NSA, which has led to a couple of interesting conspiracy theories by some people about its relationship to Bitcoin. But it's generally considered a fairly strong hash function. It's not broken cryptographically, although there are some theoretical weaknesses that are starting to show up. As a result, the replacement, the SHA-3 family, has already been picked, actually, and it's in the final stages of standardization today, but it wasn't available at the time Bitcoin was designed. This was a good choice. This was the strongest general purpose cryptographic hash function available at the time. It is possible that it will become less secure over the lifetime of Bitcoin, but for now it's pretty good. So what does it look like? This is a diagram of what the SHA-256 state looks like. And we don't need to know all of the details of this to understand how Bitcoin works, but I'll just give a high-level overview to give an idea of the task that needs to be solved by the miners. So there's a 256-bit state in SHA-256. It's split up into 8 32-bit words. So this is very much optimized for 32-bit platforms. And in each round, some of those words are taken. There's 4 different tweaks that are applied to those words that are at the bit level. So each one of these is 2 or 3 bits being flipped or ANDed together, basic logic operations. And then a number of words in the state are taken, some with these tweaks applied, and added together mod 32 in a pipeline here. And then the result of all of these additions is wired over to the first word of the state, and the entire state shifts over. So some of the design here, some of the design ideas date back to classic linear feedback shift registers, which was one of the earliest approaches to cryptographic design. So all of this happens. This is just one round of the SHA compression function. And a complete computation of SHA-256 does this 80 times for 80 iterations. And in each iteration, there are slightly different constants applied at that one step there so that every iteration isn't exactly the same. So this is the task ahead of miners, to compute this specific function, only this, as fast as possible. And so you can see that to do this, you need to be able to deal with 32-bit words, you need to be able to do 32-bit addition, and you need to also be able to do some bitwise logic. So the first generation of mining, when Bitcoin was originally proposed, was all done on general-purpose computers, general-purpose CPUs. In fact, it was as simple as this code here that simply searched over nonces in a linear fashion, computed SHA-256 in software, and checked if the result was a valid block. And one quirk, which I haven't mentioned yet, this is probably a good time to mention it if there ever was one, is that for reasons that aren't completely specified, you actually compute the SHA-256 function twice. So it's just doubled up. That's a fact of life that miners have to live with. So how fast will this run on a general purpose computer? Well, if you're doing pretty well, if you have a high-end desktop PC, you might be able to do this at about 2 to the 24 hashes per second, which would be, about 20 megahertz. Remember that even though hertz often are applied for processor speed, the basic idea of hertz is it just means something that you're doing that many times per second. Okay, so if you're hashing at a rate of 20 megahertz, what does that get you with today's difficulty? Well, it would actually take you over 100,000 years at this rate to find a block. So we talked about how mining was going to be a difficult slog. If you're mining on a general purpose PC today, it's a really, really big hill to get up because it's going to take you that 140,000 years. So as a result, today, and even for the last few years, anybody trying to do mining on a CPU probably didn't understand how Bitcoin worked, and were probably pretty disappointed that they never made any money doing it. So CPU mining was the first generation of mining. The second generation, when people started to get frustrated with how slow their CPUs were, was to try to use their graphics card, their graphics processing unit, or GPU. So what is a GPU? Almost every computer now has a GPU built in for high performance graphics. They're designed to have high parallelism, which does help with Bitcoin mining because you can parallelize and compute multiple hashes at the same time for different nonces that you want to try. And they're also designed for high throughput, so there's a highly pipeline design in graphics cards. And around 2010, the first implementation came out, written in a language called OpenCL, which is a general purpose language to do things other than graphics on a GPU. And it's a high-level language, so it took a little while before people started tweaking the code even further to run quickly on specific graphics cards. So what's the advantage of using a graphics card? Well, for one thing, they're easily available and they're easy for amateurs to set up. You can order graphics cards online. You can buy them now at most big consumer electronics stores. So they're just the most accessible high-end hardware that's available to most people. They also have some properties that make them specifically nice for Bitcoin. They're designed for parallelism, so they have a lot of arithmetic logic units, ALUs, that you can use in parallel to do different SHA-256 computations. And some of them also have some specific instructions to do bit fiddling that work out quite nicely for SHA-256. They also have the property that you can drive many graphics cards from one motherboard and CPU, so you could take your one computer and attach multiple graphics cards to it if you want. Most graphics cards can also be overclocked, which is a property that gamers demand, so you can run them faster than they're actually designed for if you want to take the risk on. And with Bitcoin mining, it might be a good idea to run the chip much faster than it was designed for, even if you introduce some errors into the process. So there's a measure of mining success called goodput, which is the throughput, how quickly you're finding blocks, times the success rate. How often does the computation actually have errors? And an interesting observation is that it may be worthwhile to go much faster even if you make a large number of errors if it leads you to find valid blocks more quickly. So if you can tweak one knob and run your graphics card 50% faster, even if you have an error in the SHA-256 computation 30% of the time, you just multiply 1.5 times 0.7 and you're still finding blocks faster than running the chip at normal speed with no error. So this is something that people spent a long time optimizing, exactly how much should they overclock the chip and what errors it would introduce. So people started trying to scale this up. They said, aha, I have a graphics card, I'm mining faster than I was on my CPU. What's better than one graphics card? Lots of graphics cards. And you started to see these really interesting homebrew setups like this one here, where people hand-built their own racks. They had their own custom cooling setup, which was often as simple as buying a bunch of fans or a bunch of air conditioning units, and trying to run as many GPUs as possible in their basement or whatever other room was available to them. So this was obviously in the early days of Bitcoin when it was still mostly hobbyists who didn't know a lot about running a modern data center, but they came up with some quite ingenious designs to pack a lot of graphics cards into a small place and try to keep them cool. Now, what are the disadvantages of doing this? Well, GPUs actually have a lot of other hardware specifically for doing video. Specifically, they have floating point units that you don't use at all in SHA-256. So you're actually wasting a lot of the hardware from what the factory built. They also don't have the greatest cooling characteristics when you put a lot of graphics cards next to one another. They're not designed to be run all in a row like I showed on the previous slide. They're designed to be run one graphics card in one box doing graphics for one computer. They can also have a fairly large power draw, so a lot of electricity is being used by these relative to a computer. And initially there was the problem that you had to build your own board or buy expensive boards to actually house multiple graphics cards. So what's the upshot of this? What kind of performance can you get? Well, on a good card, a really high-end graphics card with a lot of aggressive tuning, you might get as high as 200 megahertz. Which is about 2 to the 27 hashes per second. So that's up to an order of magnitude better than you would be doing in the CPU case. But even with that improved performance, and even if you're really aggressive and you say, I want to get 100 graphics cards together for my mining rig, that setup would still take you 174 years to find a block at the current difficulty. So it was a fun era while it lasted, but graphics cards for Bitcoin mining is basically dead. So what replaced graphics cards? Well, around 2011, people started to use FPGAs, or field programmable gate arrays. That was around the time that the first implementation of Bitcoin mining came out in Verilog, which is the hardware design language that's used to program FPGAs. And FPGAs are something that maybe you've programmed before if you've taken a hardware design course. They're designed to have hardware-like performance, but to have customers or the owner of the card being able to customize it or reconfigure it in the field, unlike a chip which is made in a factory and does the same thing forever. So they do offer better performance than graphics cards, particularly on some of the bit fiddling operations. That kind of stuff is very easy to spec out in an FPGA. And if you know what you're doing, you can get the cooling to work out better with an FPGA. You're wasting a little bit less of the card than you would be with a graphics card. And you can pack more of these together and drive them from one central unit. So just like with the graphics cards, people said, once I have the FPGA working, why don't I try getting a lot of FPGAs? And now this doesn't look quite as messy as the graphics card setup looked. This is a relatively neat rack with neat wires. You don't see the cooling setup here. You still needed a cooling setup with air conditioning or with fans. But it was possible to build a big array of FPGAs a little bit more neatly and cleanly than you could with graphics cards. The disadvantages of using FPGAs are that they were being driven harder for Bitcoin mining by being on all the time and working as hard as possible than a lot of consumer-grade FPGAs were really designed for. So a lot of people found a number of errors and malfunctions in their FPGAs as they were doing Bitcoin mining. It turned out to be difficult to optimize the 32-bit add step, which, as we said, is critical for doing SHA-256. They were also just less accessible for people. It's harder to buy an FPGA. You can't buy one at most stores. There are fewer people who know how to program FPGAs or know how to set them up. And it turned out that the cost, even though the performance on FPGAs went up, the cost per performance was only an incremental, very marginal gain over using graphics cards. So it was a pretty short-lived reign, whereas people were mining on graphics cards and graphics cards were king for maybe a year or so. It was a much shorter matter of months where FPGAs were a popular solution for Bitcoin mining. But if you were using an FPGA and using it well, you might get up to about a gigahertz. And now it sounds like we're making some real progress. We're doing 1 billion hashes per second. But even with a 1 gigahertz setup on an FPGA, and even if you had 100 boards, so again, even if you bought a lot of FPGAs and shoved them all into your amateur mining rig, it would still take you 25 years to find a Bitcoin block at that rate. So this is still not looking like a really attractive thing to jump into. And you might be asking, if all of these solutions are so intractable today, what are people actually doing? Well, mining today is essentially dominated by Bitcoin ASICs, or application-specific integrated circuits. So these are chips that were designed and built from scratch to do nothing except mine Bitcoins. They were fabbed out at a factory, packaged up, and sold to a consumer solely to be Bitcoin miners. And if you go online today, you can find a lot of people willing to sell you Bitcoin mining ASICs. There's a couple of big vendors that now do this as a full-time product. So these companies have sprung up in the last 2 years, and the main product, in some cases the only product that they sell as a business, is Bitcoin mining ASICs. And now you'll notice when you're buying an ASIC, you have a lot of options. You can choose between slightly bigger and more expensive models, more compact models, and they'll throw a lot of numbers at you in terms of what the performance is going to be, the cost, how much power it's going to use. But the most important thing to look at in a lot of these cases is how quickly they're going to ship to you. So a lot of ASICs have a pretty strong disclaimer that you have to pre-order them before they're even available, and they don't make any firm guarantees on when they're going to be delivered. So again, since these are new companies selling the ASICs, they've had to be funded as they went, which means they need to essentially pay for the production run of ASICs with consumers' pre-orders. And that means there's a lot of pressure on on consumers to pay before the chip is ready. In a lot of cases, the chips have been shipped late, and this has caused considerable consternation and heartache for customers. There are a lot of dramatic complaints and stories and tales of woe of people who spent good money on a Bitcoin ASIC and were hoping to really strike it rich when the thing came in the mail, only it came in the mail later than they were expected. Like I said, these are special purpose. They're designed to be run at full speed constantly for life to do nothing other than mine Bitcoins. They require a lot of expertise and a long lead time to design, so much more complicated to actually tape out a chip than to just write an implementation in OpenCL or in Verilog. But the amazing thing about Bitcoin ASICs is that as hard as they were to design, analysts who've looked at this have said this may be the fastest turnaround time essentially in the history of integrated circuits for specifying a problem, which was mining Bitcoins, and turning it around to have a working chip in people's hands. So this was really a rush job. People realized the need to have Bitcoin mining ASICs and the fact that they could sell them for a lot of money. They designed them extremely quickly and started shipping them to consumers. And as a result, you can probably expect there were a lot of bugs in the first few generations of these things. Some of them didn't deliver In fact, most of them probably didn't deliver quite the performance that they were promising. Some of them, in fact, are quite buggy, but it's evolved a lot over the past year, and there are now fairly reliable ASICs being shipped. So what does it look like if you actually want to buy one of these things? So here's just a case study of something that's been available for about 6 months now, so it's already a little bit out of date. But this TerraMiner 4 is this nice big fancy box you see here. And this hashes at about 2 terahertz, so it's 1,000 times faster than that hypothetical array of 100 really good FPGAs that we were talking about previously. So you'd have to pay about $6,000 for this. And even with this incredible performance, it would still take 14 months on average to find a block. So even if you think that you're investing in a fairly nice piece of hardware, it's still extremely difficult to mine a block. And the market dynamics are really interesting here. So most boards that have been coming on the market since ASICs came out have been effectively obsolete in maybe 6 months. And on top of being obsolete within 6 months, the bulk of the profits are made up front. Often in the first 6 weeks is when you'll make half of the expected profits in the lifetime of a mining rig. The fact that such a high proportion of the profits are made in the first 6 months means that there's an incredible premium on shipping speed. If your thing ships a week late, you may have lost 1/6 of that optimum time. In fact, you'll have lost the most valuable week in the lifetime of the ASIC because its value is only going to go down over time as mining gets more and more difficult. And this is really the motivation for why so many companies require pre-orders. The fact that there's so much competition to get the ASICs first, and there's a lot of speculation that some companies have actually manufactured the ASICs, tried to run them themselves for a couple of weeks before shipping them, and then ship them off to consumers. So the dynamics of this are still very unfavorable to the small miner who wants to go online, order an ASIC, and start making money. And in fact, in almost all cases, people who have placed orders for mining hardware should have lost money based on the calculation that they made at the time. Except for one thing, which is that the price of Bitcoin has been rising for most of the history of Bitcoin. It has leveled off a lot in the last 6 months or so. But during the period when prices were rising, the rising prices often bailed out miners who would have lost money if prices had stayed constant. So in effect, buying Bitcoin ASICs has been an expensive and convoluted way to simply bet that the price of Bitcoin would rise. And a lot of miners, even though they've made money mining Bitcoins, would have been better off if they had just taken the money that they were going to spend on mining equipment, invested it in Bitcoins, held them while they appreciated in value, and then sold the Bitcoins at the end. And now we're firmly in the era of professional mining. So the details are often pretty scant because companies doing this don't want to share exactly what their setup is. But it is known that there are some professional mining centers popping up around the world now. And here's just one picture that's been made available of one that came online in the last couple months in the Republic of Georgia. So if you want to open a professional Bitcoin mining center, where should you go? You basically need 3 things. You need cheap electricity, you need good network connectivity so that you can hear about new blocks as they're announced and not miss out. And ideally, you'd like a cool climate so that you don't have to pay too much in your cooling bill to cool all this equipment down. So in addition to Georgia, places like Iceland have been popular destinations for people to try to start their Bitcoin mining data center. So if we zoom out a little bit and we think about the evolution of mining, we can see really interesting parallels between Bitcoin mining and gold mining. Or really any other kind of mining, but especially gold mining because it's led to the same kind of gold rush mentality when initially a lot of young amateur folks wanted to get into the business. So whereas with Bitcoin mining we've seen the slow evolution from CPUs to GPUs to FPGAs to now ASICs, with gold mining we saw the evolution from individual people with a gold pan to maybe a small team of people with a sluice box, to placer mining, which was a big group of people blowing away hillsides with water, to modern gold mining, which is a giant open pit extracting tons and tons of raw material from the earth. And in both cases, the friendliness to small people trying to jump into this has gone down, and there's been a consolidation with large companies owning most of the action over time. So a couple of questions for the future are small miners out of Bitcoin mining forever? Is there any way to make it as a small miner in this game? And does that violate the original spirit of Bitcoin? Does the existence of these ASICs and these large mining centers go against the original vision of Satoshi Nakamoto, which was to have every individual in the network being a miner running on their own computer? So some people who think that this has been a violation of the original vision wonder, would we be better off if there were no mining ASICs? If the only way to mine Bitcoin was using your CPU like in the good old days? Well, we're going to have a lecture later on in the series, which I'll point forward to a number of times in this lecture, where we look at alternative formulations of mining that might be possible. So I won't say anything more about how we could design mining to be less friendly for ASICs here, but that will be a topic that will come up in the future that will be quite interesting. So in the last section, we ended by showing how large professional mining data centers have taken over the business of Bitcoin mining. And we showed the parallel to traditional mining with those open pit mines on the bottom, which you may know have been a huge source of concern for environmentalists over the years, asking how much damage are these pit mines doing to the environment. Now, Bitcoin is not quite at that level yet, but as I said, it is a very difficult computation with a lot of large players interested in competing now, and it is starting to use a significant amount of energy, which has become a topic of discussion. So in this section, we'll talk about how much energy Bitcoin is using and what that might mean for the currency and for the planet. So to start with, we'll talk about why computation inherently requires some energy. So there's a principle developed by Rolf Landauer in the 1960s that any non-reversible computation must use a minimum amount of energy. So this is derived from basic physics. And we're not going to go through the derivation here, except to say that every time you flip one bit in a non-reversible computation, there's a minimum number of joules that you have to use. And of course, if you remember some fundamental theorems of physics, energy is never destroyed, it's only converted from one form into another. In the case of computation, it's mostly that energy is transformed from electricity, which is very high-grade energy, into heat, which is dissipated into the environment. Now, of course, SHA-256, being a hash function, which is the basis of Bitcoin, is not a reversible computation. And if you remember all the way back to lecture 1, this was a basic requirement of hash functions that they're not reversible. So since I told you that any non-reversible computation has to use some energy, and SHA-256 is not reversible, energy consumption is an inevitable fact of doing Bitcoin mining. And it is worth saying that the limits provided by Landauer's principle are far, far below the amount of electricity that's being used today, by over a factor of 1,000. So we're nowhere close to the theoretical optimum efficiency of computing. But even if we did get to the theoretical optimum, we would still be using some energy to perform Bitcoin mining. So why does Bitcoin mining require energy? There are 3 steps in the process that require energy. First, you have to manufacture your Bitcoin mining equipment. So that requires both physical mining, digging up things out of the ground, especially rare earth metals and copper that go into integrated circuits. And then you have to manufacture it into a Bitcoin mining ASIC. So it takes a lot of energy to run fabs and to tune out chips. So all of that energy is called the embodied energy. As soon as you receive a Bitcoin mining ASIC in the mail that you order, you've already consumed a lot of energy, including the shipping energy, of course, just to get that to you before you've even turned it on and tried to mine Bitcoins. Then you'll plug it into the wall and turn it on. And of course, it will be drawing electricity constantly while it's on, and that's the electrical energy consumed in mining. And that's a step that, no matter what happens, has to be consumed because of Landauer's principle. So hopefully over time the embodied energy will go down as less and less new capacity comes online. Fewer people are going out to buy new mining ASICs. They're being obsoleted less quickly. The existing fleet can last a long time. The embodied energy will be amortized over years and years of mining. But the electricity consumption, even though it will go down a little bit because rigs will get more efficient, that will be a fact of life forever. The other thing about both electricity and embodied energy is that both are probably less if you're operating at a large scale. If you're running a huge mining data center, you can do it more efficiently. It's cheaper to build chips that are designed to run in a large data center, and you can deliver the power more efficiently because you don't need as many power supplies. You can deliver all of the electricity to one place, and so on. But there's a third important component, which is cooling off your equipment to make sure that it doesn't malfunction. So if you're operating your equipment in Antarctica, maybe your cooling budget is very small, but almost anywhere else you're going to have to pay extra, usually electricity, to cool off your equipment from all the waste heat that it's generating. And the interesting aspect about cooling is that cooling actually costs more the bigger your scale is. So if you want to run a very large operation and have a lot of Bitcoin mining equipment all in one place, your cooling budget is going to increase because cooling that big mass is going to be much more difficult. There's less air for the heat to dissipate into surrounding your equipment. So how much energy is the entire Bitcoin network using? There are two basic approaches to trying to estimate how much energy the Bitcoin network is using. Of course, we can't compute this precisely because it's a decentralized network with miners operating all over the place who haven't documented exactly what they're doing. But we'll start with a really simple approximation strategy, which is to take the fact that about $15,000, and again that's 25 Bitcoin, of reward are created with every block, which is found every 10 minutes. So if we convert that to revenue per second, we get about 25 US dollars per second that are being minted and given to the mining community. Now, if the miners are turning all of those $25 per second into electricity, how much can they get? Well, at US industrial electricity prices, and this will vary from state to state or certainly from country to country, but we'll go with about 10 cents US per kilowatt hour. And kilowatt hour is kind of a funny marketing unit, so we'll go to the more standard scientific unit of the megajoule. So if the miners took those $25 that they earn every second and converted it purely into electricity, they would get about 900 megajoules every second. And of course, joules per second are just watts, so those 900 megajoules per second are 900 megawatts, or 900 million watts. A second way to estimate the same figure is to do a bottom-up approach, and to say, let's look at how many hashes the miners are actually computing, which we know by observing the difficulty of each block, and what is the best hardware that miners might be using. So if you look online at mining rigs that are being sold commercially today, one of the best performance figures that you'll see is rigs that are able to turn 1 watt of electricity into about 1 gigahertz of hashing. So they perform 1 billion hashes per second while consuming about 1 watt of power. And the total network hash rate is about 150 million gigahertz, or 150 petahertz. Of course, that excludes all of the cooling energy and all of the embodied energy that's in those chips, but we're doing an optimal calculation here. So if the entire network was running at about the efficiency of generally the better chips on the market, what would we get? If we just multiply these two together, we would get about 150 megawatts to produce that many hashes per second at that efficiency. So again, last slide I said at a high end, using the top-down approach, we estimated about 900 megawatt. And using the bottom-up approach, this is a lower bound, about 150 megawatt. So maybe for the whole network today, somewhere between 100 megawatts and a gigawatt of electricity are being consumed. In reality, of course, it's probably somewhere in the middle and it's going to evolve over time, but that's a useful ballpark to think about right now. So how much is a megawatt? Well, we can look at what big power plants produce. So one of the largest power plants in the world, the Three Gorges Dam in China, is a 10,000 megawatt power plant. It actually has slightly higher capacity than that, but that's the average rate of power that's being produced. Whereas a typical large hydro plant is more like 1,000 megawatts. If you're interested in nuclear power, we can look at the largest nuclear plant in Japan, and that's about a 7,000 megawatt plant, whereas the average nuclear power plant is more like 4,000 megawatt. Or back in the carbon-heavy way of producing electricity, we can look at a major large coal-fired plant, and you might get 1,000 to 2,000 megawatts. So again, our high-end estimate was still that Bitcoin is consuming less than 1,000 megawatts. So the whole Bitcoin network is consuming less than a large power plant's worth of electricity. So it's not nothing. It still means that we have to essentially run a large power plant purely to power Bitcoin and not any of the other things that we need electricity for in the world. But it's not yet to the point where it's a large amount of electricity compared to all the other things that people are using electricity for on the planet. And it's certainly worth pointing out that any payment system is going to require energy and electricity. So when we look at traditional currency, a lot of energy is consumed moving gold bullion around, guarding the gold bullion, running ATM machines, running coin sorting machines, running cash registers, transporting the money around in armored cars. All of that is energy consumed by the traditional money system. So sometimes people have a tendency to think that Bitcoin is wasting energy because the energy is being expended in this SHA-256 computation that doesn't serve any apparent purpose. But you could also look at all of the energy used in a traditional currency system and say that it's also wasted and that it doesn't serve any other purpose besides maintaining the currency system. So that's a really important disclaimer, I think, that just because Bitcoin uses electricity, it's not necessarily wasted. If Bitcoin is a useful currency system, then the electricity is essentially being used for that purpose. But we still might think, is there something better that we could do with this electricity, rather than just heating up air which is sent off into the atmosphere? And one pretty interesting idea is, what if we tried to capture the heat that we're turning that electricity used in Bitcoin mining and use it for practical purposes? So this is called the data furnaces model. And the basic idea is that you would go down to your local hardware store, and instead of buying a traditional electric heater to heat your home or to heat water in your home, you would buy a Bitcoin mining rig that you would plug in both to the electricity outlet and also to your internet connection. And your heater would essentially be doing Bitcoin mining and using the heat produced as a byproduct of that computation to heat your water or to heat your home, which is hopefully useful. And it turns out that the efficiency of doing this isn't actually that much worse than just buying an electric heater. So this seems to be a great idea, and maybe it's a promising avenue to explore for the future. There's a couple of challenges here. For one, electric heaters are still much less efficient than gas heaters. So if you're in a really cold climate where people really need heat, hopefully they'll have gas heating in their home anyway. It's also not clear what the ownership model is here. If you buy the Bitcoin data furnace, do you own the Bitcoin mining rewards that you get? Or does the company that sold them to you? Most people don't have any interest in Bitcoin mining and probably never will, so it might make more sense to buy this as an appliance and have the company that sold it to you keep the rewards. And then there's the really basic question of what happens if everybody turns off their Bitcoin mining rig in summer? Will the capacity of the Bitcoin network go way down seasonally based on how much heat people need? Will it go way down on days that happen to be warmer than average? This would be really interesting if the data furnace model actually caught on. So a couple of open questions related to Bitcoin's energy consumption. Does the fact that Bitcoin provides such a good way to turn electricity into cash mean that countries that have strong electricity subsidies will have to rethink that model? So right now in many countries around the world, the government actually subsidizes electricity, particularly industrial electricity. And one of the reasons they do so is to try and encourage industry to be located in their country as opposed to other countries. Now, if one of the main things that Bitcoin miners need to be successful is cheap energy, and you can mine Bitcoins basically anywhere, it may not be stable to have countries subsidizing electricity heavily, because all that will mean is that you're paying for a lot of Bitcoin miners to move into your country. There's also the interesting question of, will the fact that you can turn electricity into money easily with Bitcoin mean that people have to start guarding their power outlets, particularly around universities and corporations, large buildings with a lot of power outlets? Will they need security cameras to make sure that employees or students aren't trying to mine Bitcoins by plugging into unmonitored power outlets and just letting them run? And you might ask, would we be better off if we didn't have this electricity consumption? Could we make a currency that didn't have proof of work and didn't have to use so much electricity? And again, I'm not going to talk about that directly today, but that's going to be a topic that we'll talk about quite a bit in our future lecture on alternative mining. Now we're going to talk about mining pools. So what is a mining pool? Well, let's look at the economics of being a small miner. So say you're an individual who spent $6,000 of your hard-earned money to buy a nice shiny new Bitcoin mining rig. Now, you expect that you'll find a block in about 14 months with this fancy new rig. And remember that a block is worth about $15,000 at today's prices. So if you amortize that, you could say that the expected revenue of this box is about $1,000 per month. And now maybe once you factor in electricity and your other costs of operating it, if you actually got a check in the mail every month for $1,000, that would make it worth it for you to buy this $6,000 mining rig. But remember that mining is a random process. You don't know when you're going to find the next block. It's a completely random search, and you could find your next block at any time. So if we look at the distribution of how many blocks you're likely to find in the first year with that hypothetical 1 terahertz box, the variance is pretty high because the expected number of blocks you're going to find is so low. So if we just look at the distribution, and this is a Poisson distribution, there's over a 40% chance that you won't find any blocks in the first year, in which case you might really be in trouble if you haven't earned any revenue in an entire year of running that $6,000 box that costs a lot of electricity to run. There's about a 36% chance that you'll find one block in the first year, in which case maybe you're barely scraping by. And then there's a slightly smaller chance that you'll find 2 or more blocks, in which case you'll really be making a profit with this thing. So again, on expectation, you might be just doing okay, enough to make a return on your money, but there's a big chance that you'll make nothing at all. So that means that for a small miner, mining is essentially a big game of roulette. Now, historically, when small business people faced a lot of risk and they wanted to lower the risk, they got together and formed mutual insurance companies. So farmers would get together and agree that if any individual farmer's barn burned down, they would share profits with that farmer so that that farmer wouldn't go bankrupt. And the question is, can we have a mutual insurance model that works for small Bitcoin miners? So that's what a mining pool is. Now, the goal of a mining pool is that a group of miners will get together, form a pool, and they'll all attempt to mine a block which pays the Coinbase, the newly minted coins, to the same recipient. That recipient is going to be called the pool manager. So no matter who actually finds the block, the pool manager will control the rewards. And then the pool manager will take that revenue and distribute it to all of the participants in the pool based on how much work each participant actually output. Of course, the pool manager will also probably take some kind of cut for their service of managing the pool. So this sounds like a great idea. You can see why it would be attractive to Bitcoin miners to join a pool to lower their variance. But how does the pool manager know how much work each of the members of the pool is actually performing? Obviously, the pool manager doesn't want to just take everybody's word for it, because everybody would say that they're performing more work than they actually did. So there's a really powerful idea, which is that miners can prove probabilistically how much work they're doing by outputting shares. And shares are blocks that are almost valid. So whereas it's pretty rare to find an actually valid block that starts with all 66 required zeros at the beginning of the output hash, there will be a lot more almost blocks that start with a lot of zeros, but not quite the 66 necessary to make it a valid block. So a common choice might be, say, 40 bits or maybe 50 bits, depending on what size the pool is designed for. Now, if miners participating in the pool send in a bunch of these near-valid blocks, the rate at which you're finding those near-valid blocks should give the pool manager a very good statistical idea of who's doing how much work. And the other nice property of this is that there's no way to fake it. Because of the properties of the hash function, there's no way to find almost blocks without also finding actual blocks at the expected rate. So how does this whole setup look? So to start with, in each round after the previous block is discovered, the pool manager, which will be collecting transactions and assembling a block, will tell all of the participants, here's the next block that we're all going to work on. So they'll assemble the block header, they'll assemble a Merkle tree of transactions to be included in that block, and in particular, they'll make sure to put into that Merkle root of transactions the Coinbase transaction, which creates new coins and assigns ownership to the pool itself. And now this block header will be sent to all of the participants in the pool, and this is what they're asked to work on. And they have to prove that they've been working on it by sending in shares showing that they've been hashing this block. Now once that gets sent out, all of the miners go about and do their work, and they'll all slowly find almost valid blocks or shares, until finally one of the miners, hopefully in the pool, finds a valid block that will then be published. Now, after this happens, all of the participants will send in all of the shares that they found to the pool manager, which should be pretty efficient for the pool manager to verify are valid shares that they found. And then the pool manager will take all of the revenue earned from that block that was published and distribute it back to the participants based on how much work they actually did. Now notice that this miner all the way on the right here, who did happen to find the block, actually receives less revenue than that miner on the left there, who didn't find the ultimately valid block, but they did find more shares. So there's no bonus for this miner on the right here that they actually found a valid share. They would have been better off if they just mined as an individual, because they would have gotten to keep all of the revenue from that block. But of course, for the miner on the left, they're sure going to be glad that they joined this pool, because they would have gotten nothing if they just mined on their own, because they happened to not find a valid block. So there are a bunch of variations on this model of exactly how you determine, based on shares submitted, how much money each miner should get in mining rewards. So a couple of common ones. There's the pay per share model, where the pool manager just announces, I'll pay a flat fee for every share above a certain difficulty that you're willing to send me based on this block. In some ways, that's the best for miners, because that's a guarantee. Every time they find a share, they'll get a certain amount of money. The pool manager is essentially absorbing all of the risk in that scheme. Of course, as a result, usually with pay per share, you pay the highest transaction fee to the pool manager. Another way to do it is a proportional model, where instead of paying a flat fee per share, the amount per share depends on whether or not the pool actually found a valid block. So every time a valid block is found, the rewards from that block are distributed to the members proportional to how much work they actually did. So in this case, the miners still bear some risk proportional to the risk of the pool in general. So if the pool is large enough, the variance of how often the pool finds blocks will be fairly low. Proportional can still be a good approach, and it will provide lower risk for the pool manager. And it gets around a problem that's inherent to pay per share, which is that with pay per share, the miners actually don't have any motivation to send in valid blocks. They don't have any motivation not to, but miners have the option when they find a valid block of just keeping it a secret. Now they're hurting the pool by doing that, so this is purely an act of vandalism, but they have no real motivation since they get a flat reward per share to actually send in the valid blocks. Whereas with a proportional scheme, the miners certainly want to send in the valid blocks because that triggers revenue coming back to them. And a final variation that I think is interesting and was popular for a while is that the pool owner actually collects no fee, but miners can't receive any revenue out until their balance is over 1 Bitcoin. So basically, this means that new entrants to the pool don't make any money for a while, and then they make money at an even rate without paying any fee to the mining pool manager. So essentially, once you're established in a pool with this approach, it's a great place to be, but they're harder to break into. So this has become pretty advanced now. There are quite a few protocols to run mining pools, and it's even been suggested that these mining pool protocols should be standardized as part of Bitcoin itself. So just like there's a Bitcoin protocol for running the peer-to-peer network, these protocols are an API for communicating from the pool manager to all of the members when to work on a new block, what that block should be, and for the miners to send back to the pool manager the shares that they're finding. Another reason why this is so important is that some mining hardware actually supports these protocols at the hardware level. Now this makes it very simple to buy a piece of mining hardware, plug it into the wall, both the electricity and your network connection, choose the pool, and then it will start immediately getting instructions from the pool, mining and converting your electricity, hopefully, into money. So mining pools first started around 2010, actually way back in the graphics card era of Bitcoin mining, which is several generations ago. And they were instantly very popular for obvious reasons because they lowered the variance for the participating miners. So by 2014, the vast majority of all miners are mining through pools. Very few miners mine on their own anymore. And a very interesting thing happened in June of this year, where the largest pool, called ghash.io, got so big it actually had over 50% of the entire capacity of the Bitcoin network. Now this is something that people had feared for a long time, but essentially ghash offered such a good deal to all the participating miners that everybody wanted to join. Now since then, ghash has gone down a little bit, partly by design. They've made their fees a little bit less attractive to try to get smaller. But you can see in this pie chart of the largest mining pools, they still have about a third of the power. And it's basically only 2 mining pools today that control about half of the power in the network. And then there's a nice smattering of other pools thrown in there. So are mining pools a good thing? Well, the advantages of mining pools are that they make mining more predictable for the participants, and they make it much easier for smaller miners to get involved in the game. Whereas the variance would simply make mining infeasible for economic reasons if you didn't have mining pools, you can operate a much smaller mining rig profitably if you're part of a pool. Another advantage of mining pools is that since there's one central pool manager who's sitting on the network and assembling blocks, it actually makes it easier to upgrade the network, because by upgrading the software that the mining pool manager is running, that effectively updates the software that all of the pool members are running. The disadvantages of mining pools, of course, is that this leads to centralization. It's an open question how much power the operators of a large mining pool actually have. Of course, miners are fairly free in theory to move between pools as much as they like. If you're making profit on one pool, you'll likely make very similar profit in another pool because the fees that they pay out have converged. They all offer about the same deal today. But in practice, miners don't switch very often, simply because they're lazy and it's easier to keep using the pool that they've already signed up for. And another disadvantage of mining pools is that it lowers the population of people actually running a fully validated Bitcoin node. So previously, small miners all had to run their own fully validating node. They all had to store the entire blockchain and validate every transaction. Now, most miners offload that task to their pool manager. And this is one reason why a couple of lectures ago I said the number of fully validating nodes may actually be going down in the Bitcoin network. So if you're concerned about this level of centralization, you might ask, could we redesign the mining process so that we don't have any pools, so that everybody has to mine for themselves? And once again, that's going to be a very interesting topic that we'll talk about in our lecture on alternative mining approaches. So the last topic in this lecture about mining will be mining incentives and strategies. So what do I mean by mining strategies? I've spent most of this lecture talking about how the main challenge of being a miner is to get some good hardware, get some cheap electricity, run as fast as you can, and hope for some good luck. But it turns out there's also some interesting strategic considerations that every miner has to make before they pick which blocks to work on. So in particular, miners get to choose which transactions they want to include in a block. The default strategy is to include any transaction that includes higher than some minimum transaction fee. Miners get to decide which block they want to mine on top of, and the default behavior there is to choose whatever the longest current chain is that's been announced. Miners have to choose how to decide between two colliding blocks when they get announced. So if two people find blocks around the same time, miners have to decide which block to extend because both will be the longest chain in history. And miners have to decide when to announce new blocks. They can choose to find a block and wait before actually announcing it to others. So in each case, there's a default strategy, which is what most miners are currently doing because they run the default Bitcoin client. Remember, it's about 90% of fully validating nodes run the default client. It's not clear what proportion of mining power that represents, but it's safe to assume that it's probably a majority. So most miners are doing this default strategy. So what if you want to change some of those decisions? Can you make more money as a miner if you implement some other strategy besides the default one? Well, it's all going to depend on how much mining power you actually have, and we'll express that with the parameter alpha from 0 to 1, which is the proportion of all the mining capacity in the world that you actually control. Now, it turns out that for some alpha, yes, you can make more money by implementing a non-default strategy, although the analysis is still ongoing. So this is very much new, under development stuff. So the simplest attack is a forking attack. And the idea here is to perform a double spend. So we have a valid state of the blockchain here, and the miner will send money to some victim, Bob. So it may look as if that transaction sending money to Bob is in the valid longest chain. Now this forking miner is going to then work on an earlier block, and to do this in practice it would need to be about 6 blocks earlier based on the standard number of confirmations that people usually wait before accepting that a payment is final. And then the miner will insert an alternate payment where they keep the money for themselves by transferring it to a different address. Now at this point that block won't be valid since it builds on an earlier point in the blockchain. It doesn't represent the longest possible chain of blocks. But if you have a majority of hash power, if alpha is greater than 0.5, eventually your alternate chain will be longer than what was previously the longest chain. And at this point, your longest chain now becomes the valid blockchain. So you've rewritten history, you've removed that payment that you made to Bob, and you've now kept that money for yourself. And if your target had given you something in exchange for those bitcoins, preferably real currency or some kind of goods in the real world that they can't easily take back, then you've swindled them. And this is a way that you could profit if you have a majority of power in the network. So like I said, this attack is certainly possible if alpha is greater than a half, if you have the majority of the mining power. It might be possible in practice with a little bit less, because of things like network overhead and the fact that as one mining pool, you shouldn't be working on colliding blocks in your alternate chain. So sometimes people talk about a 51% attacker in Bitcoin, but it's a mistake to think that that's a magical threshold where as soon as you cross it, all of a sudden you can do this attack. In reality, it's more of a gradient where the attack gets easier the further over 50% you go. It's important to realize that this attack is detectable, and it's possible that if you were doing it on a large scale, that the community would decide to reverse it by refusing to accept your alternate chain, even if it was longer. So it's not clear in practice that this would actually work, and it is also possible that doing this would completely crash the exchange rate of Bitcoin. So it might be that once a miner started trying to do this, people would lose so much confidence in the system that they would not want to buy into it, and the amount of dollars that Bitcoins were worth would go way down. In fact, if this was done on a large scale, it's possible it could destroy the currency completely by a dramatic loss of confidence. So who would want to do this? The conceivable scenario where people are worried about an attack like this has been referred to as a Goldfinger attack, named after the famous villain in the James Bond movie, of course, whose goal in the movie was to irradiate all of the gold that the US government held at Fort Knox to make it valueless. So if your goal was to destroy Bitcoin, then you might be willing to do this forking attack in order to specifically to tank the market, make Bitcoins worthless, and possibly profit because you had either shorted Bitcoin or because you had significant holdings in some competing currency. So beyond that threat model, it's not clear in which scenarios we would have to worry about a large-scale forking attack. Although it's possible that the attack is easier than achieving that alpha greater than 0.5, all that hash power, by simply buying it. So whereas it would be really expensive to buy enough mining capacity to have more than everybody else in the world, it might be possible to just bribe the people who do control that capacity to work on behalf of you. So there's a couple of ways you could pay the bribe to them. You could try to do it out of band. You could hand them an envelope full of cash, say. You could declare yourself to be a new mining pool and run it at a loss. You could say, I'll pay out 1.01 or something that clearly wasn't sustainable, but enough to get miners to join your pool at the expense of all other pools. Maybe that would push you over 50%. And there's some other subtle ways you could try to get people to work on your alternate chain, say by leaving big tips in the blockchain. But the idea is that instead of actually acquiring all the mining capacity yourself, you just pay the people who already have it to work on your fork. Now, it might be a bad idea for those miners to actually participate, because by doing so, they would be hurting the currency that they've invested so much money in mining equipment, hoping will stay sustainable. So why would anybody be subject to such bribery? Well, it would be an incentive problem. All of the miners together have an incentive in keeping the Bitcoin currency solvent, but individual miners would have the incentive to defect and accept a bribe if they thought they could make more money in the short term. So this would be a classic tragedy of the commons from an economic perspective. Now, this hasn't happened. This is pure speculation, but it's an open problem if a bribery attack like this could actually be viable. So one defense that does exist in Bitcoin against forking attacks is checkpointing. So since 2010, each version of the default Bitcoin client ships with a specific checkpoint and will refuse to accept versions of the blockchain that don't date back to that version. And it's usually several hundred blocks before whatever the current longest chain is. So there's some questions about the implications for this in terms of how decentralized this is, because this now means that essentially a central party, the developers who maintain the core Bitcoin client, are deciding something about the value of the valid blockchain. But this does serve as a good practical mitigation against the risk of a deep fork in the blockchain. Another type of attack that's quite interesting is a block withholding attack. So the idea here is that you don't want to announce your blocks right away as soon as you find them. Instead, you're going to want to try to get ahead. What do I mean by get ahead? Well, you want to do a little bit of mining and hopefully find 2 blocks in a row before the rest of the network finds even one. And you keep these blocks to yourself as a secret. Now, why would you want to do that? What would you gain from keeping blocks secret? Well, as long as you have those 2 blocks that are being held secret in your back pocket, the rest of the network is going to be trying to extend what they think is the current longest blockchain, and all of that effort is going to be a waste for them. So while you're ahead by 2 blocks, all of the mining that you're doing is essentially unopposed. And the reason is that as soon as the rest of the network actually found a valid block, they would publish it and everybody would accept it, but then immediately, boom, you can drop the 2 blocks that you had in reserve, and that would instantly be the new longest valid blockchain, and that block that the rest of the network worked so hard to find would immediately be orphaned and cut off from the longest chain. So this approach has been called selfish mining, which I think is a little bit of a misnomer because all mining is inherently selfish. At least at this point, now that the hobbyist interest in mining has largely died down, mining is a business and people are in it to try to make money. So we should say that it's all in the game for miners to do this if they think that they'll make more profit. So what happens if you're trying this block withholding strategy and you're ahead by 1 when the rest of the network finds the next block? So instead of being 2 blocks ahead, you just have 1 secret block held in your back pocket. And then the rest of the network announces what they think will be the next valid block. Well, if this happens, you're going to want to immediately push your secret block out the door. And now there's 2 versions of potentially the longest chain, and every other miner is going to have to decide which version they want to work on, and we're in that race condition. So you basically have to race as soon as you hear somebody else finding a valid block to get your secret block out the door and hopefully get more miners to hear about your block first. So the viability of this block withholding approach is going to depend really heavily on your ability to win these races. So when is it a good idea to do a block withholding attack? Well, if you assume that you can win every race, every time there's competition for the next valid block, the rest of the network is going to accept yours, then no matter what alpha, no matter how much mining capacity you have, it's better to try selfish mining. By selfish mining, I mean this block withholding strategy that I've just described. So how would you try to win every race? Well, you could just fight really hard to have a good network position. You could try to peer with every node so that you'll announce to more nodes ahead of the legitimate flooding algorithm. Or you could try bribing people. And again, you could bribe by including small tips in your block so that it makes it more attractive for people to mine on top of you rather than the competing block. So if you assume that you only have a 50% chance of winning these races, which is about what the natural chances would be if you're competing fairly, then this block withholding strategy is an improvement if alpha is greater than 0.25. And again, this is a theoretical attack, which is very interesting, but it hasn't actually been observed yet in practice, and it should be something that you'd be able to tell by monitoring the blockchain and when miners are announcing new blocks. But even though it hasn't been observed in practice, it's very surprising that this is possible, and it's contrary to the original idea of Bitcoin that without alpha over 0.5, without a majority of the network, there was no better mining strategy than the default. So the very existence of this attack shows that it's not safe to assume that a miner who doesn't control 50% of the network doesn't have anything to gain by switching to an alternate strategy. Another interesting case is if miners want to do punitive forking. So specifically, if miners want to blacklist transactions from a specific address, which would freeze the money held by that address forever, they could announce that they'll refuse to mine on any chain with a transaction originating from address X. So the reason this is an extreme strategy is that if you have less than a majority of the network by announcing that you'll refuse to mine on any chain that has the transaction from X, as soon as a chain exists that the majority of the network accepts that has that transaction from X, then you will have cut yourself off from the longest chain forever, and all of the mining that you're doing is essentially wasted. So you could do this strategy, but very quickly you would just be mining on an orphaned fork, and it would be a waste of all of your time and electricity. But there's a much more clever way to do punitive forking, which is called feather forking. And the idea here is that instead of announcing that you're going to fork forever as soon as you see a block that has a transaction from address X, you announce very publicly that you're going to fork, you're going to try to mine an alternate longest chain if you see a block that has a transaction from address X, but you will give up after a while. Typically after 1 or 2 blocks confirm the transaction from address X, you'll go back to the longest chain. So your chance of actually pruning that block or orphaning that block that has the transaction from address X, if you give up after 1 confirmation, is alpha squared. And the reason is because you'll have to find 2 consecutive blocks to get rid of the block with the transaction from address X before the rest of the network can find the next valid block. So alpha squared might not be very good. Say you're a 20% miner, alpha squared is going to be quite low. It's going to be only a 4% chance of actually getting rid of that transaction that you don't want to see in the blockchain. But you might motivate other miners to join you. Now, why is that? As long as you've been very public about this, other miners know that if they include a transaction from address X, they have an alpha squared chance that the block that they find will end up being orphaned because of your feather forking attack. And if they don't have any strong motivation to include that transaction from address X, and it only has a very low transaction fee, that alpha squared chance of losing their mining reward might be a much bigger incentive than including the transaction. So those other miners might rationally say, we have this person, this miner doing feather forking. It's in our interest to join them and just do the blacklist that they're demanding rather than run the risk that they'll feather fork away from the new block that we've just found. And the cool thing is that you can now enforce a blacklist even if alpha is less than 0.5, if you have less than a majority of the mining capacity. And your success in doing this is going to depend really heavily on how convincing you are to the other miners that you're definitely going to fork. So ideally, what you would want to do is say, I've burned this into hardware, I have no choice, I have to do this, so no matter what you do, I'm going to be feather forking. In which case the miners would say, well, this miner really is going to go through with it, so maybe we should just give them what they want and do this blacklist. So why would you want to have a blacklist? Well, like I said, there's the ability to freeze money held by an individual, and if you're blacklisting successfully, you can keep them from ever spending that money. So maybe you could profit off of this by some sort of ransom or extortion, demanding that the person you're blacklisting pay you in order to be taken off of your blacklist. It also might be something that you might want to do for legal reasons. Maybe certain addresses are designated by law enforcement as being bad. Those assets are demanded to be frozen, in which case some proportion of miners, say those operating in the jurisdiction where the asset freezing has legal authority, will say, well, we really have to enforce this blacklist we're being demanded to by the government, therefore maybe we should feather fork to try to make it happen. But a much more interesting case is if miners do this to try to enforce a minimum transaction fee. So instead of a blacklist against a specific address, you want a blacklist against any transaction that doesn't include some minimum transaction fee that you think is fair to you as a miner for your hard work. So we haven't talked a lot about transaction fees in practice yet. We've said that they exist, and we've said that there's the capacity in Bitcoin to pay transaction fees. But what are transaction fees? So this is the default policy for transaction fees, taken essentially right out of the Bitcoin code. Transactions are assigned a priority, which sums over all the inputs, the value of that input times how old the transaction is, how long ago that input was put on the blockchain, divided by the size of the transaction. So this basically means transactions that are larger, transactions that are spending older coins that haven't been moved in a while, and transactions that are smaller have higher priority. And by smaller, I mean smaller in size of the transaction, which means they don't have a long, complicated script. So the idea is to prioritize large transactions, people who don't move their coins very often and who do it in a simple way. Whereas if you want to move money quickly, if you want to move small amounts, or if you want to do complicated scripts, you have to pay a higher transaction fee. And currently, by default, there's a magic number where miners accept with no transaction fee if the priority is higher than 0.576. And if you're sitting there thinking that seems pretty random, where did that number come from? I'd say you're right. It's a very arbitrary choice, but it's in the default client. So that's basically what you need to pay if you want to move Bitcoin. So currently, transaction fees don't matter that much. And the reason is that block rewards provide the vast majority, well over 99% of all the revenue that miners are making. But keep in mind, we mentioned earlier, that the size of mining rewards is going down constantly over time. So every 4 years, it's halving. So eventually, in the distant future, the mining rewards, the fixed rewards by creating new coins, are going to be much lower, and transaction fees are going to be the main game for miners. It's going to be where they're making all of their revenue. So it's an open question in that new world where transaction fees are everything for the miners. They really depend on transaction fees for their revenue. Are miners going to be more aggressive about enforcing minimum transaction fees? And how are they going to enforce that? Will they need to form a cartel to enforce minimum transaction fees? Is that something that market concentration provided by mining pools will make easier to happen? These are really interesting long-term open questions about how Bitcoin will evolve. So in summary, miners are free to implement any strategy that they want, although in practice, in the wild, we've seen very little behavior of anything but implementing the default strategy. And I should stress that there's no complete model for miner behavior that says that the default strategy is optimal. We've seen that in a world where most miners do choose the default strategy, Bitcoin seems to work fairly well. So it seems to work fairly well in practice. We're not sure if it works in theory yet. But even though it works in practice so far, the facts on the ground are going to change for Bitcoin. They're changing slowly because of more network hashing capacity. The miners are getting better and better. There's more centralization and professionalization of the miners. But even beyond those trends, they have to change in the long run because of the transition from fixed mining rewards to transaction fees. So overall, I'd say you should stay tuned to this space. Things might be about to get a lot more interesting for Bitcoin mining. And currently, it's a very interesting research topic to try to play out using what we know from game theory. How is this going to evolve in the long term? So that's all on Bitcoin mining for now. A few lectures from now, we'll have another lecture about mining, but about alternative models for mining. How could we redesign Bitcoin mining to have different properties? But before we get to that, in the immediate next lecture, we're going to look at anonymity in Bitcoin. How much anonymity does Bitcoin provide? If I use Bitcoin, will people be able to link my Bitcoin transactions to my real name? And what technologies are there to try to either strengthen anonymity in Bitcoin or design an alternate currency with more anonymity? That's all coming your way in the next lecture.